Had a great slate yesterday, and I look forward to what we have presented today. Everybody doing okay? We enjoyed the social event last night. Some more than others. I did see a lot of in the restaurant still, so hopefully they'll be coming soon. But we're starting off with our own CubeSat simulation, our simulator, CubeSat sim project update with Alan Johnson. So I'm going to hand the mic back to him. Thank you.
So thanks, Robert. Good morning, everybody. I'm Alan Johnson, KU2Y. I'm AMSAT's Vice President for Educational Relations, and I'm also an Associate Teaching Professor at Villanova University in the Electrical and Computer Engineering Department. So nice to see everybody this morning. Good to see the early risers here. I'm actually going to give two presentations today. First one is my usual update on what the CubeSat simulator team has been up to and what's been happening in AMSAT education for the past year. And then the second part, I'm going to do something a little different. I've talked a number of times about the CubeSat sim hardware. This time I'm going to talk about the software. So we'll see how that goes. My code for it is not exactly documented, which means it's not documented. And it's a little bit complicated because there are multiple processes going on, and some code is in C, some is in Python, some is in Bash. So I'm going to talk about that a little bit. I'm not going to get into the details of the software architecture, but I am going to talk about the function. I'm going to use a systems diagram to go through it. So we'll see. Hopefully that will go well. It's also been fun to hear other mentions of the CubeSat simulator. You were here yesterday. You heard more than a few mentions of it. It's been around the world in various places and Comic-Cons and the like. So that's great. And you know, if you ever come across the CubeSat sim in the wild somewhere, or you are bringing it somewhere to show off, make sure you share it on social media and use our hashtag CubeSatSim to spread the word here. So for my first presentation here, I'll talk about what the CubeSat sim is and what's been going on with it. And there has been a lot going on in the past 12 months. And I'll do a demo here because I brought a couple of simulators here. So we'll attempt a live demo. And then I will move on to the second part of the presentation. And I'll try to leave time at the end for Q&A. Because in the past, I've gotten some really good feedback from folks in this room. So make sure that I leave time for that. So I want to start out by acknowledging the CubeSat simulator team. There's lots of us, as you can see. This is not a one-person effort. And some of the people are here in this room, including Chris. So thank you for your work with Fox Telem. Also want to point out that we lost Paul Graveline this year, Silent Key. He was a key contributor to this project and also a number of other AMSAT activities as well. So he is deeply missed. So what is the CubeSat simulator? It's basically the core of our educational outreach, our science, technology, education, and math. And we use it in university engineering programs. It's used in high schools, used in the amateur radio community. And we also hope to get it into sort of non-traditional places like maker fairs, Comic-Cons. There you go. That's a new one to add to the list. Libraries, museums, things like that. So it's a low-cost satellite emulator. So it's fully functional. It has all the functions of a real satellite. It's got working solar panels, rechargeable batteries, transmits real telemetry in multiple modes. It does everything except if you put it in space, it would die in about 1 second. Right? It's just a 3D plastic printed frame. The software is just written, is just, you know, the very basics. And nothing about it is designed to survive in space. It's designed to be super low cost to build and also very easy to build as well. And we've had many college students, even high school students, put them together. So it uses a Raspberry Pi, but it has a 3-board custom stack. And it also has, in addition to a Raspberry Pi Zero 2, it has a Raspberry Pi Pico microcontroller on board. And it's got voltage, current sensors, and various environmental sensors as well. And it transmits real radio telemetry. This photo here shows AMSAT's Fox Telem software, which we use for our satellites that are on orbit. And it transmits exactly the same format. It does either, for Fox Telem, it does either the frequency shift keying data under voice, which is what our FM satellites do. And it also does BPSK, binary phase shift keying, which is what our more advanced CubeSats do, what Golf will do, and what our LTM CubeSats will do, like MESAT that you heard about yesterday. And in addition, it does standard slow scan TV. It also does APRS and CW. And the CW it transmits, it actually uses the AO7 format. So I guess AO7 doesn't transmit telemetry anymore, but back when it did, it used the exact format that we use today. So that's cool. Okay, so the major announcement for this week is that we've finally moved out of beta and we've released the version 2 of our hardware and software. This has been a over 12-month effort by the team to do this. It was a major redesign of the hardware. The redesign basically began during 2020 when things became unavailable, and we were basically forced to redesign or put the project on hold for a couple of years until things could come back. And since then, we've used the opportunity to improve things and to address some of the issues. And we actually did a survey of anybody who had bought blank boards or otherwise interacted with us at AMSAT, and got feedback from them. And in the end, we ended up actually, one of the questions we asked was, what don't you like about it? What are some of the issues that you've had? And our redesign actually fixed the majority of those. So we're pretty happy with that. We also got very positive feedback on that survey, which is encouraging. So we do have the new version 2 hardware and software, as you can see here, and we've made the new frame to be modular. So you'll be able to make a 2U here. We have this connector piece, basically just allows you to connect additional frames. So with another connector piece, we could make it a 3U. So it could be a golf ball. So we haven't actually released this connector piece yet. We're getting very close, but the frames that are available today are all ready to do it. You notice they have at the top of the post there, they have the holes all ready to go for that. So that's kind of fun. And if you build the 2U, one of the things you can do is you can, for example, put in 2 battery boards, which is great because with 2 battery boards, this will run about 7 or 8 hours under battery, which is good for an event where you just want it to run all day. In addition, you have extra space, so you can put in extra boards for sensors and the like. So that's fun. We also, this year, for the first time, we made kits available. So for a number of years, we've sold the blank boards, right? These are examples of the blank boards. This project is fully open sourced. All the code is on GitHub, and all the STL files and all the Gerber files for PCB fabrication are there. So anybody could just download the Gerber files and have them made. However, fabricators have minimum quantities, right? 5 is typically the smallest. So to get 3 boards, you'd actually end up buying 15 boards, which is more than most people need. So by us doing them in bulk, it saves people doing that. Also, we get them made. There are a couple of surface mount parts on there. And so if you buy the boards from AMSAT, those surface mount parts are on there. And I don't know about you, but with my steady hands and failing eyesight, I'm happy to have someone else do the surface mount parts. All the remaining parts are all through-hole parts. I sometimes get asked, is it a good first soldering project? And I would say no. You don't want to start on something like this. Your first soldering project should be some kind of a blinky lights, buzzer kind of thing. We build one at Villanova, and we call it the roommate annoyer. It's just something fun like that, and something where you can bridge all the connectors together, and put everything in backwards and all that kind of thing. So we recommend some other solder kit first, and but then your second project could be this one. So. However, with making kits available for the first time, we have had this is one of the kits here, and it's actually one of the it'll be one of the prizes tonight. So one lucky person is going to walk off with it. And what we did was we had the boards. We basically had the boards made by our fabricator. And the board is mostly surface mount. A few of the components are through hole, like switches and LEDs, but most of them are surface mount. So we had all three boards fully assembled, and in addition, the kit includes the 3D printed frame as well, and it's basically all ready to go. So that's the battery board there with the batteries already in it. The SD card is already programmed. The Raspberry Pi Pico has already been flashed. So it's about 45 minutes of work to put it together, to assemble it. And for the first time, so the kits that we did 20 kits, and we sold some of them at Hamvention and some of them at on the AMSAT store. On the AMSAT store, I think they sold out within 3 hours. I was putting them up there. But those kits had a small amount of soldering. You had to solder the wires on the solar panels, and you had to solder two of the sensors, the BME 280 sensor and the MPU 6050. But these boards, actually, we got our fabricator to do it, and they also soldered the leads onto the solar panels. So these are actually the version 2 kits, which will be available on the AMSAT store sometime in November, are actually no solder. So all you need to do is just put it together.
So it's a perfect first solder kit.
Yeah, yeah, that's right. Perfect first solder kit. Yep. So anyway, so we're looking forward to those kits. It's still a lot of work getting them made, even though someone else is doing it. It's still a lot of work putting them together. So we're looking into options for how we can make the kits more available, because I think there's going to be a pretty good demand for them based on what we've seen. And it will really get the CubeSat simulator into a lot of places where it's never been before. So that's ultimately why we do this. We're not doing this to make money or anything like that. We're doing it because we want to get the word out. So a little bit of details about the CubeSat sim, although probably most of you are familiar. We've actually upgraded for version 2. We recommend now the Pi 02. You can still run it on the Pi 0, but it's really at the limit of its CPU processing. And that's primarily because we now do command and control. We use the FM transceiver, which is a new piece of hardware on the board. And we take the output of that and we run Direwolf on it and do DTMF and APRS decoding, which I'll hopefully demo for you. So we now recommend the Pi 02. The Pi 02, it only adds another $5 to the cost, so it's really not that bad. And in addition, now we plug in a USB sound card into the Pi 0 because it doesn't have any audio in capabilities. So that's you can see the on-the-go cable down the bottom there. So the main board is where we have the Raspberry Pi Pico. We have the FM transceiver. Also, we have, you can see here, this little red thing here is a quick connector. It basically allows you to connect other I2C sensors without soldering. Right? You basically daisy chain them. I guess SparkFun invented it a few years ago, and it's extremely popular. And the software is designed so that it actually already supports adding additional sensors. There's just one piece of code which just has placeholders in it right now. And so you just drop in your initialization code, you drop in your loop code, and the first 3 telemetry numbers that your code puts in will actually get included in the telemetry, and it will get displayed even in FoxTele. So it's very easy to add sensors to it. And I mentioned the survey earlier. That was actually one of the items in the survey. People said we want to make it easier to extend it and add new sensors to it. And it's something that I've been having my students do for years, but it's always been a little tricky. But it's much easier now, and actually my students were successful doing it. And you just need to use the Arduino IDE to do it. Eventually, it might be fun to make it so you could add sensors using something like CircuitPython, since that's very popular these days. But for now, it's you still have to write the C code in the Arduino IDE. So the solar board, this board has all the current and voltage sensors. There's one per side of the CubeSat simulator. And that allows you to actually tell which side is facing the sun, or if you're doing a desktop demo, which way is facing your lamp or your window. And there's actually 2 connectors per side, wired in parallel. So as long as you have the same voltage on your solar panels, you can connect 2 of them. And if you do a 2U, you can use much bigger, much more powerful solar panels, which is fun. And the battery board, this board actually has a major redesign to it. We switched to these much more robust battery holders, not the old springy ones that look like they're from the 1970s or whatever. Having CubeSat Sim loaners for many years that I ship out to people that are using them. And if any of you are interested in taking a CubeSat simulator somewhere, just contact me, and I will ship it to you for a couple of weeks for you to use. And it's a Pelican case with the simulator, the ground station, the turntable, the lamp, and instructions. And anyway, most of the repairs that I did related to the battery. Basically, batteries were popping out, battery connectors were breaking, things like that. So these battery connectors are much more sturdy. Also, in place of zip ties to hold the batteries in, we now use clips. And these clips, they really lock the batteries in, which is good. We actually moved one of the voltage and current sensors from the solar board onto the battery board. So if you can run just the battery board, and you will get telemetry showing you the battery voltage and current. And this is useful if you're using the CubeSat Sim as a balloon payload, where you're not going to run solar panels, right, for a short balloon flight where you're trying to minimize weight, but you do want telemetry showing how your battery is doing during the flight. So that's a nice improvement on that. The ground station that we use is the key to it is FoxTele, but we also have Direwolf, and we have QSSTV as well. And we recommend the Fox in a Box Raspberry Pi software. And I actually have it running. It's running in the back, and I'll show it to you on my screen later. The nice thing is, if you do that, all you need is like a Raspberry Pi 4, which you can get them now for $35, $40. And with the SD card, you plug it in, and all the software is installed. There are scripts for running all of them, and they've all been tested such that they work together and they play nice. And if you've ever worked with SDR software, you know that in general, they don't play nice. You install one piece of software, and every other piece of software breaks for it, and it just takes so much time. So Fox in the Box, all the different applications, they all play nice together. You can switch with an easy script between them, and it's great for demos. On the other hand, you can also install all the software on your PC. And in our survey, we discovered that a majority of people were actually doing that rather than using the Raspberry Pi. So I guess you all are a very adventurous lot, and you like installing software and using your own computers. So we're going to make sure that we provide plenty of support for that in the future. But I really do recommend using using the Fox in a Box because it's so much easier. So these are the 5 different telemetry modes that I've demonstrated over the years. There's actually 2 additional modes listed down the bottom here. One of them is we're calling the transmit commands. This is where the CubeSat Sim in this mode, instead of it transmitting telemetry, it transmits commands to another CubeSat Sim mode. So I'm going to demonstrate that. And we also have an experimental repeater mode where it listens on one frequency, and if the squelch is broken on the FM, it retransmits it on another frequency. It's not 100% reliable right now. Sometimes the recording mechanism gets locked up, and the only solution is to reboot. But once that gets reliable, I'm looking forward to that, and that could be fun to demo. So Frank Bauer of ARIS mentioned this yesterday. I just wanted to highlight it as well. The CubeSat Sim has found its way onto this ARIS STEM outreach program called STAR, Space Telerobotics with Amateur Radio. And it's basically a way of controlling an Arduino-based rover. And ARIS has developed the software to do it using Discord, where you connect using Bluetooth by your computer, so you can do it remotely. You can also do it using APRS commands. And we've basically added a CubeSat Sim Lite onto the top of it and a Pi camera such that it transmits slow scan TV images as you drive it around. Now that's an addition to their other mode where you can simulate the Martian terrain in a 3D way. So as you drive it around the simulated Martian surface, you see different views, which is kind of cool. But it's also cool to see the actual thing that it's showing. And of course, it takes 30 seconds to get the image, so it gives you this feeling of delay, which you have if you're doing telerobotics, which is fun. And that's the picture there. And so this is the new Lite version 2. I haven't released this yet. It still has a few problems. But basically, the Lite board, it does the same thing as the CubeSat Sim, but it's got no battery, no sensors, no solar panels. It's really just a transmitter. But in this case, because we have the FM transceiver on it, it's also a receiver as well. So when you add the USB sound card to this, not only can you, for example, transmit slow scan TV images, but you could also receive APRS commands directly on the rover itself. So I think that's something that ARIS is going to do in the future. So if you read my paper, I have some of the details of where the CubeSat Sim has been in the past year in terms of in the classroom and events. And some of you were at those events. Thank you, Dennis, for taking it to Hamcation and helping out at Hamvention. It's been fun. My favorite thing was that CubeSat Sims ended up at DEF CON. So that was really exciting. And you'll hear from Rachel soon about that. So I'm looking forward to hearing that. And in terms of in the classroom, they've been in high schools at Villanova. We keep building them every year, and the students have fun with that. Johns Hopkins University is using them. They've been ordering blank boards in quantities of 10 for their students in one of their master's courses. And there was also a workshop at the University of Texas, Dallas, and they had participants build CubeSat Sims over a 3-day period. So it's pretty good. It's been a good year for activities. Okay, so let's try our demo here. We'll take the remove before flight out for this one here. So this 2U has been running. Yes, yeah, that's been facing you there. So let's check in. There we go. That's it. It's interesting. We're getting some interference here.
Microphone.
Wow. Yeah, I tested with the microphone before. Wow. 4.9.
I know what it is.
Randy knows what it is.
I know what it is.
You know what it is?
Sorry.
Ah.
And we have a coordination process.
Yeah, exactly.
There we go. Fixed.
Nice.
All right. QRM was done. So right now it's this 2U CubeSat sim here is transmitting in FSK, data under voice, and you can see the signal here. You can hear the that lovely rumbling sound that you get with it. And if we take a look here in the health tab for FSK, screen updates here. So you see the data updating in real time. Now this is a very latest release of FoxTelem that Chris Thompson put out for us. Thank you, Chris. It's version 1.13E1, I think is the right version. You can get it if you go to his testing directory as it. It's only very minor changes, but if you look here under computer software, it says that command and control is enabled. It's set to DTMF or APRS. There have been 13 commands received lately, so I've been testing it a few times. And also, if you look here, it's got the battery telemetry here. It says 3.92 volts and 159 milliamps. And then down here is battery 2. So 3.89 volts and 151, because this is the 2U here that has two batteries in it. And so they're both reporting telemetry. So the batteries are wired in parallel, so the voltages will read the same, plus or minus whatever error there is. And they may or may not deliver the same current. That depends on the health of the batteries. I only recommend doing two parallel battery packs if those batteries are in the same condition. You know, you don't want to mix old batteries with new batteries. Fortunately, though, we use nickel metal hydride batteries in the CubeSat simulator, which are extremely tolerant. It's really hard to damage them. And if you do damage them, they don't, for example, turn into flamethrowers like lithium-ion batteries. So they're very safe when you're working with students. So you can do things like just, you know, wire battery packs in parallel, which you would definitely not do with lithium batteries. Okay, so that is running there. So I'm going to attempt to do some command and control here. So should have a stand here. So I'm going to first use DTMF.
Stand is on the floor.
I know it's too short. Yeah. So let's see. I'm going to initially switch to APRS mode here. So APRS is mode 1. So I'm just going to transmit 1 and then pound. Let's give it a try here. Oops. Get on the right frequency here. And did it blink? Okay, good. That's a good sign. If it did blink, then yeah, the telemetry just shut off. And if I switch back here, we should hear an APRS packet. When the blue LED transmit LED comes on, we should hear the LED packet. Hear the APRS packet when it comes in. So yeah, so right now this command and control is completely without security, which of course is not how you do command and control. You can add PL tones, so you can program transmit and receive PL tones for the FM modes, and that gives you, a tiny bit of security. Right? Someone has to guess which subtone frequency you need to set. Did we get it? Oh, there we go. Oh, that's there's the CWID. There we go. Okay, we have APRs, so that's good. But now all the pieces are there to do command and control. It's really just a small amount of software to add some kind of security, to add a password, to add a hash, for example. I get a lot of inquiries about cybersecurity for satellites is a really big topic, and the Hackasat at DEF CON is extremely popular. And so in the past, I've had to say, no, you really can't use the CubeSat sim to simulate any of that because it has no command and control. Well, now it does have command and control. So I expect people are going to extend it. Yes.
No questions now or at the end?
Preferably at the end. Yeah. But so please hold the questions. Okay. So let's see. Let me try one more thing here. So I'm going to use this CubeSat sim here to try to send a command to that CubeSat sim. So I have this in the transmit commands mode. You notice that it doesn't have the LEDs on there. And when I do the push button here, instead of that normally changing the mode of this one, it should change the mode of that one. So let's give it a try here. I'm going to try to put it into slow scan TV, which is mode 4. So let's see. Hold, 2 blinks, 3 blinks, 4 blinks, and then release. All right, did anything blink here?
Mm-hmm.
Yeah, okay, that's a good sign. All right, so we can check back in on that in a minute and see how that does. So I will switch to slow scan TV mode if it will let me. So we can see the images and which way is the camera facing here. Face the audience here. And that, let's see if I can switch. Okay, we'll come back to that. So if you're interested in the details of the command and control, this wiki page has it. And in addition to DTMF, you can also use APRS packets, which is what that just set there. Okay. Oh, there we go. SSTV. So that's working there. Let's check in on the box here. Yeah. For some reason. So I just switched to SSTV here. Turn that down because it gets annoying fast. And so you can select different frequencies for all this. So for example, if you want to receive slow scan TV during one of the ISS events that ARIS does periodically, you can use this for that. Okay, so that's doing the stored image. We'll check in on that later once it gets going. All right, so I'm going to use the next couple of minutes here to talk about the software on the CubeSat sim. So the background that we just did the version 2.0 release, and that replaces the version 1.2 that's been around for a couple of years, and it's based on the beta 1.3, which we've been testing for the past 12 months. And thank you to everybody who's helped out with that. And all of our code is on GitHub. It's a GPL license. So our target hardware is the Raspberry Pi OS. And we actually use the legacy Debian version 11 Bullseye. We don't yet support Bookworm because Raspberry Pi broke a bunch of stuff when they did that, especially with Python. It's a real mess. So we haven't cleaned up that mess yet. So but we will support that soon. And these days we do recommend the Pi 02, although you can run it on a Pi 0. There's various ways you can get the software. You can download a zip file from GitHub. You can clone the zip repository, which is the best way, because that way you can always get updates to the software. And you can also view beta branches and different things. We also make a Raspberry Pi image available that you just download right to your SD card and you plug it right into your Pi and it just works. So there's four main components to the software, and I'll talk for a couple minutes on each of them. There is the main housekeeping code, and that runs that's C code running on the Pi Zero, and it reads the sensors. It also monitors the battery voltage, and if the battery voltage drops below a certain point, it switches to safe mode. And if the battery voltage drops below another point, it does a safe shutdown of the Pi. There's also the transmitter code, which is done in some Python code. And there is command and control code, and there's also separate code that runs on the microcontroller on the Raspberry Pi Pico. So those are the four main components. Let's just check in here. Okay, so we're getting on here. So the latest software, it overlays the call sign. I'm using W3ZM, AMSAT's call. Gives the battery and current. That will be us, perhaps. Mostly it's the ceiling. There we are. Okay. And actually, most of the time, the camera is supposed to blink when it takes a picture, but some of the Pi camera, the LED doesn't work. I don't know why. And it's random. Some of them work, some of them don't. So there you are. Okay, so I'm going to talk to this very busy diagram here, but I'm going to zoom in on each part here and explain what's going on. So if I start with the housekeeping here, so there is a piece of software, and the software is actually in Python because there's an issue with the C libraries for the INA219. I'm sure Burns is familiar with problems with libraries. So I actually use a piece of Python code that feeds the results to the C code, and it reads the voltage and the current of the solar panels, the batteries, and it also connects to the quick connector for additional sensors. The housekeeping software drives the green LED, which tells you that the software is running for that. It receives telemetry over the serial port, over the Pi serial from the microcontroller for the additional sensors. It generates the telemetry data and sends it to the transmit code, which is used to actually generate the RF. And it also reads all the different configuration files and settings in order to figure out what to do. So that's the basics of the housekeeping software. So here is the transmitter. And there are two transmitters. One of them is the FM transceiver board. The other is the RPi TX library, which is an all software library. And if the low pass filter is present, it will transmit. If there's no low pass filter, it just transmits the CWID and then stops. And then down here is the command and control software. And it either operates off of Squelch. You can do simple Squelch command and control where you just do a carrier and it detects it, or you can do Direwolf software on the audio, which comes in through the sound card. And then finally down the bottom here, this is the payload code. This is what runs on the Raspberry Pi Pico. So this is completely separate C code. And it reads in the built-in sensors, the BME, the MPU, and also any additional sensors, the quick connector, any sensors you attach there. It has software for an external serial GPS module. If you plug a GPS module in, it'll just work and start giving you that. And it transmits that telemetry over the port there. Oh, and I think I also forgot to mention that the transmitter software, it also programs the FM transceiver using a serial port as well. So it configures it with frequency, Squelch, NEPL codes, and that kind of thing. And then finally, there's another piece of software, the Pi power button, and that basically monitors for the push button when you want to change modes and the like, and blinks the LEDs. So that's basically the main components of the software. If you want more details, you could read the paper. So I would encourage you to get involved in the CubeSat Sim project if you're interested. You could borrow a loaner. You just need to get in touch with me and let me know what dates and what your event is, and I can ship it to you. You can also build a kit if you want to. If it costs about $300 if you want to buy all the parts and solder it together. To do the whole kit from scratch, it's about 10 hours altogether to do that. Or these days we do have the kits available, although they're going to be in small quantities until we figure out how to improve that. Okay, so I think I still have a couple of minutes for questions. Yeah.
Just elaborate a little bit, Alan, on when the kits will be available on the AMSAT store.
Yeah, so so I need to finish putting them together, and then we'll get with Bruce, get everything ready to go, and then we'll announce it at least a week in advance, and we'll say at this date and time they'll go on sale. We'll announce that on ANS, probably the mailing list, and probably on social media too. Also, I have a list. I actually have a waiting list of people that wanted to direct email from me. So if you want that direct email it to me, and I'll put you on that list too. Yeah. Yeah. So Chris, back to your question.
Yeah, I have a question or a comment about the security.
Yeah.
I'm not a huge fan of, especially getting people to do education around that. But to include some sort of health warning that says depending on your country and your licensing conditions, any form of security may look like encryption as your licensing.
This is true. Yeah.
I think you can get around that because if the key is actually
Correct.
published somewhere, then
Correct.
you can do it. And teams trying to break that or play with that don't necessarily themselves need to know the key at that moment. So
Right.
you can do all the education around that, but we don't want people sending
Correct.
encrypted stuff as part of the ground state. And in many countries, you can't even send it to private space.
Yeah. Yeah. No, that's a very good point. So Chris is pointing out that encryption is something that governments and regulators are very interested in, and it might break local laws to.
Particularly in amateur radio.
Oh, right, doing encryption over amateur radio frequencies. Yeah.
That's the key.
Gotcha.
Even if you just need to root out, they generic checks on it. Okay.
Yeah, this is true. Yeah. Yeah.
The key is published for that. It's not enough.
Correct.
So that's fine. The education can happen.
Right.
You need a health warning as to what you're going to do.
Yeah. Yeah, no, that's a really good point.
Fall foul of your local radio.
Right. Yeah, I don't plan to do that myself, but I suspect others will. But if we put in this recommendation for them as to how.
Some words.
Yeah. Okay. Thanks, Chris. All right. Other questions? Yes.
You said the build from parts is around $300.
Yes.
And what about the package from the?
Oh, the kits are $400. Yeah, because it turns out the kits are remarkably cheap. It's just difficult in terms of labor to put them together. Any other questions? Okay, well, thank you very much.
Very nice.
Thank you. Okay, we're running a little ahead of schedule. Get a break 20 o'clock. Ready?
Yeah.
Get a HDMI port.
I do.
Sorry.
I even brought a cereal.
Oh, old school.
I was prepared.
Do you have paper handouts?
Yeah, I thought about it, but it took me a long time to actually get to Tampa. It's entirely my fault.
We don't know how to read, so it's okay.
Okay, this is Rachel Jones, and she's here to talk about the integration of the AMSAT CubeSat simulator for education and research.
Well, thank you guys so much for having me. Hopefully my presentation appeared. Excuses, technical difficulties.
We were ahead of schedule.
It's plugged in. Beautiful.
Try it.
Wasn't in.
Perfect.
Good.
All right. As he said, my name is Rachel Jones. I am a PhD student at the University of North Dakota, but I also have worked at Spanner River National Lab as a space scientist. There's a lot about me, but probably what you guys need to know most is I'm an ARIS ambassador, and I am an amateur radio extra and the president of our student government amateur radio club. So today's discussion. What I'd like to do is I'd like to walk you through 3 different scenarios where we've actually utilized the AMSAT CubeSat simulator and 3 different methodologies and teams that have really tried to integrate it for education. While I appreciate everything that can be done, and I do think that you guys are doing an amazing job, we do have some suggestions that we'd like to make, and we hope that they'll be taken positively, because we'd all like to see this program expand, because I must say this has been an amazing educational tool. I apologize that my co-authors could not be here. For some reason, did you know traveling from like North Dakota is expensive? My God, there's no direct route. We do have to build the road. Did you know it's 30 there? I'm gonna die. So the first case study I'd like to kind of introduce you to is how I use the AMSAT CubeSat simulator to train my undergraduate interns. Being a young scientist, one of my favorite things is really passing on that information to a new generation. This past summer, I've had 3, and I was so thrilled to be able to, I want to say corrupt their minds, but I think it's more professional to say inspire them to greater understanding. So I had a mechanical engineer, an aerospace engineer, and a cybersecurity policy and analysis expert. And these 3 individuals were from 3 drastically different fields. They were from, I had a senior, a junior, and a sophomore. Whew. So they were at various learning stages of their lives. And how do I combine them all together to get their knowledge together was kind of a nice, fun problem to really develop. One of the things I try to train them in is how to be a research scientist. No matter what their discipline is, learning the basics of research and that foundation is amazing. And I actually have 2 different simulators in my office. I have the AMSAT CubeSat simulator, which is, okay, I would say it's more like $500. I mean, prices are coming down, but like, it depends on where you buy it, and how you buy it. But I also have the ISAT simulator, which is about $10,000. Oh, believe me, the government bought it. I'm so glad that I didn't have to buy it. But these 2 different simulators play different roles, and there's some advantages and disadvantages between using each one. My paper will go into a little bit more detail, but this perspective is written from one of my interns, which you might know already. Her name is Olivia Bellion. She is a senior mechanical engineer at New Mexico State University. And what's really phenomenal is that her goal is now to go to grad school for aerospace engineering. I like to think I did that. So her first year, this is actually her 2nd year interning with me. And you might have seen the AMSAT article that was about her first year interning with me. When she first came to me, well, she's done welding, she's never done soldering. And I'm like, well, about that now, we're going to see if we can expand that. And the AMSAT CubeSat simulator really gave me the opportunity to not only insert what CubeSats are, that was a lovely explanation, but also give her that hands-on skills that I thought she would need desperately in her field to come. So this is from her first picture, or her first year, where she's actually learning to solder. Oh, she did all the solar panels herself. It was amazing. But you know, this year, of course, we've got to step it up a notch. And look, new toys for the lab. So this is my Ritwik Swama. He is another undergraduate, and Olivia Bellion. They're playing with what we call an RF glove box. Now, really, I wanted just to have an aluminum foil box with an alligator clip and call it an antidote, you know, an RF chamber, but the lab's like, oh, really? How do you calibrate that? I'm like, I don't know. So we went and purchased this new RF glove box, and what it allows us to do is it allows us to be able to send and understand signals within an isolated chamber. So we really isolate this chamber here. And they did a lot of experiments when they built the simulators, having them talk to each other. How do you establish that connection? How do you establish the connection to the ground station? And that was phenomenal for them. And of course, if you notice this slight cord right here, I actually had a spectrum analyzer here to make sure that the box did not leak at any time. So I really felt like the setup was amazing. Olivia, as you know, probably during her first summer, what she chose to tackle, what I love being able to do was giving them the freedom to kind of find what they wanted to contribute and what they wanted to do. So in this picture, you can actually see a new casing she designed for the AMSAT CubeSat simulator. She felt that the various pieces of the current simulator was too mechanically unsound, so she made a jar device which would reduce the number of joints. It's an interesting perspective. I thought it was very creative and kind of got her thinking in the right direction. But this year, she was thinking in a much further direction. So I don't know if you guys know this, and believe me, people were surprised when I told them. Did you know 16 CubeSats have been interplanetary? 16 CubeSats. CubeSats that are so small, they're now actually being sent to other worlds. And I'm not talking just low Earth orbits. I'm talking out of Earth orbits. All right, 16 has been it. And this flyer here is actually from NASA. Yes, it looks pretty. So whenever we have visitors, we put it up. I'm like, look, science. But this is NASA showing what their goals and their ambitions are. And NASA has communicated in various conferences lately that they're thinking CubeSats are the way to explore interplanetary. They're cheaper, they're lighter. Well, how are we going to get them? Olivia decided she wanted to take her CubeSat adventures to a new level. So what she designed was a way, I'm going to try to get this right. It is her invention. It's called Star Trucker. And it is a large bus that carries 36 U CubeSats with it. And her goal was, she did the orbital mechanics to get that bus to Jupiter, and then she was going to disperse the CubeSats to the various locations so we can get different pictures, more measurements from various aspects, and then the CubeSats would come back to the main bus before moving on to the next location. Wow.
Ambitious, yeah.
Can you say senior mechanical engineer? Oh my gosh. So the CubeSat simulator here has really changed her and allowed her to grow in a different way. Some strengths that she developed while learning that is soldering, of course, basic mechanics, how it functions, how it works, what's needed in the CubeSat. But some things that were a little challenging is that I actually think the new models will meet is how do you get a little bit more advanced CubeSats? How do you build on that? You know, going from 1U to 3, oh my gosh, I cannot wait. I think that's really the next avenue here. So that is Olivia. And I really kind of wanted just to show you what she's been doing and what I really felt that the CubeSats really helped her learn. Now, the other person I wanted to introduce you to, I don't know if you guys know her. This is Mary White. She is actually just got promoted, so forgive me if I ever reference her as the amazing STEM teacher that she was. She is now the Director of Digital Integration and Innovation. Ooh, that's a mouthful. But she actually works at Augusta Preparatory Day School, which if you haven't heard of it, don't worry. It is, I don't want to call it small, a good sized, about, I would say about 400 plus students from pre-K through 12th grade. It's a private non-sectatory school in Augusta, Georgia. And what her role is how to bring STEM to the classrooms. Now, how did she get involved with all of us? Well, it's all thanks to the ARIS program, and she got selected for an ARIS contact. And that really kind of, I have to say, the space bug was a lit in that school. They've decided, oh my gosh, this is now the coolest thing ever. So We did amazing things. We did fox hunts. We built, you know, the tape measure antennas. We did Morse codes. We did all these things that, you know, kind of got a baseline for the students to learn amateur radio. And they're like, well, what else can we do? What's next? Well, that is where AMSAT came in for what's next. The school actually decided that they would like to try to build and launch their own CubeSat. It's an amazing endeavor and one that's going to take multiple years. NASA actually has a program that will help students launch CubeSats, but it's very competitive. And one of the things that they wanted to do was they wanted to establish teams in order to help further this endeavor. How were they going to do this? How are they going to put together a satellite on their own? Well, that is where the AMSAT CubeSat came into play. This is a group. There's actually two groups. They meet during their lunch break, which the school doesn't have a cafeteria. They all just bring their lunch. Kind of nice, I don't know. And they go into the library once a week. And this is the middle school team here. They have decided they want to launch a CubeSat. Now, what they're actually going to do with that CubeSat still up in the air. Let me tell you, you have never, ever heard some of the wonderful suggestions for what to do with the CubeSat than if you talk to a middle school group. I think some of their more creative suggestions was they wanted to use a CubeSat as a Roomba and go collect space debris. I tried, I didn't want to crush their hopes and dreams. Like, oh, I think you might have some physics issues here. But that's, you know, that's where they're thinking. And I love that. And I never want to discourage where they're thinking. I actually think what they want to do now is to send memes down from a CubeSat to classrooms. Well, NASA's already done that. NASA's done the cat video, so we're trying to think outside the box here. They had some very interesting ideas, and this is going to be a multiple year project. So we actually purposely started it with a group of sixth graders because our goal is to hopefully train them for a few years and then actually start once they're in high school. So this is the group that they hope to see all the way, but the high school students not going to let them do it alone. They're like, oh, we want in this. We need this. So the high schoolers were, you know, of course, wanting to get involved. And this is our high school team. And what some of the strengths and disadvantages of the AMSAT CubeSat simulator is they were able to, you know, decide on a plan. We're going to do this. And then there was some, maybe some supply issues. Maybe. Okay, that's putting it lightly. One of their biggest problems is they decided and started these clubs the first week of school. You know, they got done with Eris and they're like, we need it now. We're going to establish a school club. We're going to have the, you know, satellite contacts. We need this to go out now. So they started trying to buy the supplies in August. They finally got the supplies in April. So one of my biggest, and this is my personal suggestions, please don't associate these with anything else. I will make them any fallback or feedback. Please blame it on me, not them. But one of my personal suggestions is that AMSAT establish a special purchasing route for schools and universities. Right now, you know, he heard those full kits sold out in 3 hours. I guarantee you teachers are not going to be at their desk waiting to buy something. They've got classes to teach for some strange reason. They're busy, but I do think there should be a special pathway for, you know, schools like this to be able to purchase these full kits, because these middle schoolers and high schoolers, I feel like the kits will benefit them the most, and having them facilitated directly to schools could be a positive direction. But as I say, please don't shoot the messenger. These kits did do a lot. Now, while they were waiting for the kits, of course, they learned to solder. They divided their teams into different groups. I think we had a systems engineering team. We had a project management team. We even had an artistic design team. Oh my gosh, they're planning the colors of this CubeSat before they've even built it. But don't worry, the CubeSat colors have meetings, and they will tell you all about them. So they didn't waste their time this past year.
but they were slightly delayed more than they would have preferred. So they're moving forward, they're enthusiastic, and I cannot wait to see what this group of students is going to do in the years to come. Now, the other group I need to talk about, whew, I have been a distant student for most of my time and during my PhD program. The University of North Dakota has a wonderful distance program that allows working professionals to be able to do their job and do school on the side. But because of amateur radio, I was able to receive a wonderful scholarship. My husband and I decided, can we afford this? All right. So this year, I have been able to be in person for the University of North Dakota. And it's been a busy year. My gosh, last week I just finished my written comprehensive exams. If you don't know what that is, equated to torture. Written torture. I do my oral exams November 13th, and hopefully I'll do my dissertation proposal on November 15th. But while coming to this university, I must tell you that I feel like I'm the dog that caught the car. I do not know what to do. Now, let me explain this a little bit more, because that's a weird statement to make. And I will apologize that my co-presenter could not make it. Don't know if you are familiar with my professor, Dr. Ron Febick. While on the right is his professional picture, I really like this picture of him helping the Girl Scouts on the left a little bit more, and that was just recently. And what I'm bringing him up and my university is up is because we just got, what was it, $4 million to build a satellite fabrication lab. And I'm telling you, this is everyone's, like, your dream of what you want, if you like listed out things, is in this lab. I have an anechoic chamber. I don't even know what to do with it. I'm so excited to have it. I've never had this before, and I have one. Wow. Or at least access to one. Minor detail on that. We've got a clean room. We've got a full vibration test board. We've got a thermal testing room. We got a full soldering room. We have everything you need to build a satellite. Well, cool. Now what? Well, we have put together what's called our Sat Lab team. And this is a club at school with, let's just say, I think my professor used the term, their enthusiasm is palpable. Palpable. Great. They're enthusiastic and they want to do things. Well, what are they going to do? It's how do you get them from 0 to hero? What are the steps you take, and how can you really develop that talent? So one of the first things, of course, we're going to do is the other professor that involved in this program is Dean Ryan Adams. I don't know if you know him. He's part of the IEEE Antennas and Propagation Society, and hopefully AMSAT soon. We've got to work on him. But we taught him what a CubeSat was. I loved that they still have these what dry erase boards, and they use markers. Oh my gosh. But we went over what a CubeSat was, and our next step, don't forgive my misspelling, but that was the Reggie, the presidents and them, is to actually buy some AMSAT kits and get them working with the tools, because we've got to find a way to economically develop a workforce and develop a skill set that's not presently there. And how we do that is very difficult, because for some reason, did you know schools can't just buy 13K ISAT CubeSat simulators? That's might not be in the budget, but hopefully we can sell enough popcorn in order to buy a few of these kits and be able to get these guys started. But that's kind of the different perspectives of what's going on in 3 vastly different groups. If you actually read the conference proceedings, there's going to be a paper. And what was really nice is I've included narrative sections from each of the 3 that I presented on, Olivia, Mary, and Dr. Febick, about what their thoughts are, how they use AMSAT, how they use those tools and resources and their ideas for possible improvements. While there's a lot of strengths, including cost, capability, what people are doing, there's also some things that we think could be improved. One other matter that I actually threw in here at last minute because, someone actually mentioned it, put me on the spot a little bit, to bring up one of the other things, ideas for improvement. I'm going to talk about my presentation at DEF CON a little bit. So who here knows what DEF CON is? Ooh, I was not expecting that. Oh my gosh. Awesome. So as you know, DEF CON is one of the premier, I would say, what should I say, hacking, or should I say cybersecurity conferences? Ooh,
Hacking's good.
it sounds more professional if I say it the other way. So I actually presented in the Aerospace Village. Oh my gosh, I love the Aerospace Village. I could have lived there my entire time, but I had to bounce between that and the Ham Village. So priorities. And we were able to present on cyber space projects for students. And this is my presentation team. If you don't know some of these people, we got Dr. Rizzi on the far right there. He just graduated from Dakota State University in cyber operations. And then Tim Fowler. I don't know if you know him, but I guarantee you probably will soon. He runs courses on the cybersecurity of CubeSats. So he is the guy who was like, you see his back wall and there's like 15 different CubeSats, like that company makes this one and this company makes this one and this one. And I'm like, what in the world? My gosh, if you need details on CubeSats, that's the guy. And the three of us put together presentations on individual projects for students at various ages. Some of the things I liked about our presentations, of course, we went over SSTV, gotta love it. We went over other projects for decoding and actually getting to hear satellites using the software-defined radios. And then we also, of course, we had to throw in a few other tidbits for it. But one of the things that I thought was really valuable was Tim actually went back step by step. We borrowed a CubeSat sim from AMSAT, got it sent to the conference. I hope you wiped it afterwards. I don't know if I trust it after being in that area. But he went over step by step of him building the AMSAT CubeSat simulator. And what was really interesting was his perspective of different ways. It's like, I noticed problems in this part of the Wikipedia. I think this could be improved. And I was talking and communicating that with other teachers and professors, and like, wow, I wish I knew that ahead of time. So, and builders such as Tim, who's an adult, and my undergraduates feel like the wiki article, how to build it, AMSAT CubeSat Sim, is significant and thorough, but some builders, like the middle schoolers, didn't find it that way. They found it difficult to understand, hard to read. And one of their suggestions was they'd actually like YouTube videos of a person that would go through with them how to build it. They wanted to be like, please forgive them. They're like, what are resistors? I don't know this. They would like more of an educational video of like, these are resistors. These are how they're used before they actually put them in the board. They kind of want that person, because I'm not going to speak poorly about teachers in schools, but not every teacher in school knows what a resistor is. And the goal of this product, I think, would be more valuable if anyone could use it. You have a teacher that might not be an expert in the subject, or might not have gone through any of the training, and be able to, like, if your club wants to support this, I'm behind you and I will keep you safe and won't let you hold a soldering iron like a pencil. But allow a little bit more research into it. So one of their suggestions, the middle schoolers, I might add, was to actually have YouTube videos. Originally they suggested TikTok, but I convinced them YouTube would be better. On explaining a little bit more in depth, and something they'd like to see. So that's one of the ways we would actually want to see some improvements going in. I'd love to answer any questions. I was definitely hoping, to get more feedback during the presentation. We started early. We still have a lot of time. What do you got for me? Helen.
Rachel,
First, thank you for coming. Thank you for giving this presentation. It's terrific. My question for you is, how do we find more people like you? How do we find more people like you? Right? How do we find people who want to bring STEM and amateur radio and satellites into schools?
Well, I'm doing my best to corrupt as many as possible, but I do think expanding kind of our medium outputs. One of the things is there is a gap between finding what GitHub is. I have to say, and I don't mean this in a bad way. I do feel like satellite building is interdisciplinary, and it involves skills that some disciplines are like, of course, GitHub, cyber. That's what we got going. And an engineer or someone else that might not be familiar with that might actually feel, I've never heard of this. What is this? So trying to find ways to connect those displacements that you might find in interdisciplinary fields and find a way to say, we know you're smart. You got this. Here's what you might not know. Here's how you connect what you do know to what you're doing. And I think that's really how we grow. And also increasing our median outputs, like having a cool YouTube show or having videos or having different ways to interact with the students directly.
Great, an interesting idea of doing YouTube videos. As you well know, AMSAT's an all-volunteer organization. My question is, would it be possible, for example, for people who are YouTube-centric, who are involved in the program, to somehow develop a YouTube program that AMSAT might be able to share with others? It's a challenge to have this material created in social media. And so it's somebody stepping forward that has the enthusiasm to do it and the ability to create a decent YouTube video to provide that material, because it's all volunteer.
Well, I do think that there are many ways to get volunteers. If I wasn't doing my dissertation right now, I'd be like, ooh, I'll try it. But it's how do you get that continuous volunteer? Because as you know, we have different iterations and those change constantly, right? So how do you get that participation? And I think a little bit is asking for it. You know, what if you made an exchange? You had a school that couldn't afford it. It's like, well, would your students like to make us a YouTube video on this? If there was a program where they could exchange, you know, YouTube videos and presentations and improvements for actual education materials, if you guys would be willing, I think that would be a good trade. And if you grow it small, I think that eventually it will snowball into something greater. You might not, you know, you might have a 5-minute presentation on what is a resistor or how to solder for the first time from one school, but you also might get here's how we did this piece from another school. And if you grow that a little bit each time, I think eventually you'll get there. You also have, I hate to say it, certain people like Tim Fowler that are very prolific on YouTube and very prolific in growing their business and what they do. So you also have a group of what I would say professionals that could step in too. But I think there's a good value to both doing the non-professionals and the students actually making the videos for themselves and also having the professionals in there.
Rachel, congratulations on finishing your comps. Well, you mentioned your dissertation. What is your dissertation topic?
Oh my gosh. All right. So I like space cybersecurity. That is my dissertation topic. But my goal is right now there's a lot of regulations and a lot of materials that are aimed for higher level professionals that are developing satellites. So there's a NIST document on how to, you know, protect your satellite, but that might not triculate or go down to the lowest levels. So I would like to look at a design process and pose critical responses on what they need to do to protect their satellite during each different phase of the design. How do I take that knowledge that, you know, for us, of course you do that, to a person that might not have been exposed to those concepts. And for not what I'm calling non-professional, but really is geared toward university satellite designers.
Thanks. Nate?
We had two. Can I get?
This is just kind of asking your opinion, but don't you think that, yes, there are the professionals that are in a different generation than the people you want to catch with, this is a resistor, this is how you solder for the first time. Don't you think it would go over better and get more users and actually looking at it if it were younger people doing those videos?
I do. And to be honest, I think in my personal opinion, the professionals' videos that they do initially will be a good guiding force for the younger generation to do their videos. They can kind of see, what they need to include and how to do it. And they will lead the example for those younger students, because while they've got a lot to learn, if they have good resources that they can access, it'll make a difference.
So I think that the schools that you were showing, you said were private schools. And I'm just wondering if you have any thoughts about how to get more into public schools where there's far more students and far more diversity of students.
I agree with you there, and that has always been a challenge. I have done or approached and taught in many public schools, but it's usually in the form of a club after school or an additional program. And that is because the teachers, depending on the state, are very, I don't want to say rigid might be a good word, but they are taught what they have to teach, and there's little flexibility.
Or none.
I've actually, the only time I thought about, protesting in front of a school was when my niece, she was, I think 10 at the time, they decided to cancel science class in order for test prep. And I'm just like, you did what?
Yeah.
Why? I nowadays the teachers are under incredible pressure to make the students perform, have the students perform to this message, and take this test.
Teach to the test.
Teach to the test. So for public schools, the biggest success I've had is in getting a club after school, having a program, being involved in things like Civil Air Patrol, and being able to guide them in a different way. And I've had a lot of success that way. I wish I could change the world and redesign the public school system, but that's probably a few years away, if that were at all.
I will comment that one advantage that Augusta has is that the kids are in that school for 12 years. And supply chain issues cost the lives, as you demonstrated in your presentation. So they may miss 8 months, but they got 8 more years to get it done. So that is one significant advantage, that you could actually create an entire program from elementary school through high school, that they can just grow through that entire process if that interest continues.
I agree, and with the way those kids are going, they're already planning their NASA careers at this point.
Yeah.
They are online, on track. I'm having to struggle to keep up with them with their various interests.
Just a comment about public schools, engineer, not a school teacher. I just went to an after-school club, like you say. The teacher was sent to the ARRL program this summer.
Wireless Institute,
And
yep.
she came back and she has kids, and she actually is STEM, but she's doing code students in a after-school club, and we just build kits with them, and she's trying to pull them into radio, and so that might be something you could do locally, is find the teacher in the schools that do the STEM and volunteer to help them with their club.
And I agree. Having or sponsoring a student, or even just letting teachers know about the ARRL's Wireless Institute is valuable, because I kind of feel like it's another way to get them trained up. One of the biggest things is we don't really want a school club that doesn't have a licensed facilitator. So getting a teacher license can make the difference between success and failure.
Yeah, if it's any consolation, it's exactly the same in the UK. Teaching of the test, and everything sounds totally familiar. No help.
I was hoping it'd be different.
After school clubs. Equal rights.
Rachel, I tell you a little bit of experience from the higher education perspective. Where I spend my my days working on university students. And you know, we see the downwind pipeline from the US. So we're looking forward to you know, the getting another crop of students that are a bit more savvy. And it's a couple of thoughts. One is, I don't think it's fair to ask AMSAT to teach everyone, all the kids out there, what this is. There's so many other interests. I mean, so in my particular case, I deal with chemistry undergraduate and graduate students, and I'm an instrumentalist, and I've done a lot of work in RF engineering and RF instrumentation. And so kids come up to me all the time, going, would you teach me all about electronics? No. The short is no. I don't have the time to. So my standard line these days is to tell go out and get an amateur radio license. You'll learn an awful lot, dude. And that starts that's much later than you see them, of course. It starts in a pipeline that they can't turn back. You know,
You try and you try.
we have a lot of, you know, some of us work, are successful in raising some financial resources. I buy a lot of kits, a lot of those little, I think Alan mentioned before, like kits, you know. Great. Yes, yeah, you gotta know which end of the soldering iron to pick up. That's the first.
We did learn that one.
You know, you try to save a couple of fingers. So, we appreciate that, appreciate the efforts and keep up the good work. Like I say, let's see the use of those logos.
Is there any effort in your program to get the kiddies licensed? I mean, is there a local radio club in your area that does VE testing?
Okay, not only is there a local radio club, there are 4 local radio clubs. We've actually hosted a student VE testing session, and of those, many of the students got licensed through that effort.
Okay.
We've seen a dramatic increase in younger members joining amateur radio because of their interest in space.
And my wife and I do VE testing online, and we're from the Daytona Beach area, and we've got Embry-Riddle Aeronautical University in our backyard. So, and they go in clumps, you know, groups of students that want to get a license because they need somebody licensed. Because, as you said, there's only usually one professor or instructor that is licensed, and none of the kids get licenses. So, you know, it would free up the instructor if one of the kiddies or a couple of them had.
And while I do agree with that, I think I'm very much of a risk averse approach, and I apologize for that because I guess maybe working with younger students too long, even if the students have a higher license classification, I'd still want a professor or an instructor to have their license too.
Well, most schools require that anyway.
But I really have enjoyed working with them, and I see a lot of growth in that area and enthusiasm for it. I just want to make sure I can keep feeding them the right materials at the right time to keep them interested. And that is building on the CubeSat, I think is the way to go, because that gives them a little more each time, and we can kind of increase their level of difficulty as they go through. All right. Any more questions? If not, I will turn it back over.
Thank you.
Thank you very much. I appreciate you making the trip all the way to North Dakota. I know that's a long way. So, all right, we're a little bit ahead of schedule, but we got a break coming up. Let's be back in here at 9:45, and we'll see you in a little bit.
Way to turn that one. It's just a lot of
We were having a problem with the streaming camera, that's too bright. We might have to protect our own.
Oh.
See, amazingly.
I don't know why we couldn't make it work, but
Don't jinx me.
I know I did one other time. I keep doing, uninstalling all these other softwares, because we got a bunch of icon stuff.
It's fun to do 15 minutes.
Yeah, could be.
Sit out here, I was so fidgety. Not a sit in one spot person, and I didn't understand.
Oh, nice. Yeah. If they want, put that on your
Somebody else taking the over responsibility.
Yes. The new box. The new box up.
Yeah.
This is just the second time.
Oh, yeah. It's
I,
Yeah, yeah.
There's a couple of files out for presentation. I'm trying to decide what would be preferable for me to use my computer or use the in-house computer.
If you have an HDMI, we'll pop it in yours.
I do.
It's fine.
I do.
No problem.
So
It's just the cable's not very long, so it kind of has to be.
that sitting there is good. And there is a base point.
Yeah.
Yeah.
And not every- that's, Can you get a tan on that thing?
Yeah.
Nice. I like just like the large diameter. Okay, I'll bring it up.
I say for her, it's the retirement kickoff. Got her room, she got to sit out on patio and by the water. Yeah.
Weather but still be nice to eat on.
Yes, yes.
It's starting to cool off where we are. When we got first frost, that will be some.
We had frost actually. Yeah, we had a real cold thing, with the cold whoosh like this and, they were saying cover stuff, some
We
here.
had a near frost, they had frost.
Yeah. Yeah.
We're gonna get, let's take out. We're gonna get.
On shipping and yeah. Oh, yeah. Chili. Kill some bugs. Set some buds on some of the vegetation. Move you into fall/winter pretty good.
Yeah.
Yeah, I was gonna say,
Oh, bird under.
Yeah, it's one stop. Yeah, you can stop.
Win one.
Yeah, stop one and the other one is still.
Yeah.
No.
Yeah.
Cool. Yeah, there would be a film on top of
Yeah,
that.
I was
but
gonna
it's not-
say.
You'll see it actually.
They go ahead and put that filter. Yeah. You can see the board. Oh, so I asked. Oh, yeah. So they have stairs. 3 months later. Yeah. Oh, yeah.
And it's interesting, it's another two on the station or one? Only one on the station.
They have. We wanted to send up the other one. Now we're up in I can't believe I don't have it in my bag, but I have so few things that use it. And when I threw the radio, I thought, oh, I got one in there singing for sure. But all it was that stuff. Power bank. No, 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 no. Right. Must be micro, right? You know what it is. I just can't believe it, man. I started taking out a bunch of cables that I knew I didn't need, and that one is like very rarely needed.
My daughter started.
Thanks, yeah.
Well, I put your boards over here.
Oh, very good. Yeah, I totally forgot. No, no, no.
You like
That's right. Reset. That's really. Oh, there you are. So that's the SR-105 unit.
Oh, so the top.
It's a whole module and it's orange. It's pretty nice. And they're $7 each. Yeah, unfortunately, it's $40 shipping from China. But when we buy it in bulk, it doesn't matter.
This one's all.
That is fantastic. I might have to build one of your boards just to
Yeah.
To
Well, if you look at the bill of materials, you could just, because you can, I mean, you can hand solder these. I've actually just soldered wires onto them.
Right.
So you don't have to put it on.
I've been practicing very small soldering lately.
Okay, yeah. Surface milling.
Yes. Yes.
These are big surface.
I have a microscope.
Yeah, I know. You got your hand, you're trying to.
Yeah, yeah, exactly.
Are you? When I was talking, because I had a wife, and I wanted to think her, and I thought, y'all, I was in like, couldn't identify anybody mode, you know? Oh, just like.
Fine, so I'm gonna.
They're not here anymore. But they might be ready, but doesn't.
This is the demo.
Really important.
And then half on land, the spec.
Sarah?
I knew.
All right. Got a cameo with a sad.
Nice.
Thinking about, auctioning that off later tonight.
Oh, you're auctioning this?
The real size. This is what it looks like. This isn't this one live.
What do you think it is?
Yeah, this one's not something.
Yeah,
That's
I've got a
my jewelry
battery.
box. It's a jewelry box.
I found a different one. Yeah, I don't know if it's any better, but.
I've used it so much.
Different.
Gotcha. But what Alex had, where you got.
Yeah, good. Thanks for the email. Yeah, well, yeah, not usually, but for whatever reason we woke up, yeah.
I have a wire. But he had it work.
You have an AMSAT.
Yeah.
This is good.
Yeah. Yeah.
They said it was 9.5. It's like 3 meters.
Yes.
Oh, I tried for the last hour and a half with two different little cables and we both came to, anyhow, finally tried the third cable and now it's working. Yeah. Yeah. I guess we're a little late. We're trying to, I wanted to capture some slow scan directly.
So,
Yeah, yeah, it does. It definitely. So, yeah, yay for us. Finally got it going. Good work.
this is huge.
Yay. One more thing. It was. You got your king back? Yeah, that was happening. Just like we wanted to. Our and these little things sometimes you have to make this.
You couldn't see this 1,000 miles away.
You think that's it? Oh, yeah.
Hey, I would check that. I'm going to. I was at Marshall.
Yeah, oh, wait, it's on the side van.
And
He's transmitting that, but yeah. Next one.
I didn't want to.
There's, shit, now you can put the numbers in. It's obvious how much.
All the, like, I don't use the hard grab.
I gotta get
back
right there.
I'm not.
Same thing.
Get out of here.
My neighbor, have all
Ham radio.
I've got like probably
Now, it is audio level over USB. And there's a setting here. You need to back up and go red. Although you could probably do it from the slider here.
Jackson.
So
The time that would be. Huntsville Ham Fest or something.
It's, honestly, it's a presentation show. This device. Yeah. So, I've got 97. Well, it should be. Everybody else. No, I thought I was in just running, seeing a sack control. Controls the age. Oh, it's auto going to the
I want to use it.
the intent is rolling down to around 20. Anyhow, there is an audio level.
This is high speed, whatever high speed shutter. I've seen some of the ones that have gotten the transition, where the ISS is passing from the two.
Sound
And they've got high speed shutter, taking the pictures, have you seen that? Yeah, it's just amazing.
I don't know why it wasn't showing up down here like a picture.
Well, here we go.
Very
That's a lucky shot.
times sideband for
But they only have your high speed shutter.
the Dolphin shifting.
About ready to-
But I am still adjusting my width and everything else. I don't look that thing much of the program, but I've got as much as I can. But I'm still fixing it. Weird. On frequency. No, but if it.
Oh, show Selena this.
I took the goal.
As
close as we're going to get.
And the design.
I mean, you know, we don't need to. Oh, right. Yeah, it was very kind of enjoyable. And I was not gonna quit till I got it. You know.
This guy has the same frequency program.
Yeah. But this makes it all happen. You'll see some pictures of that.
Oh, yeah. I know what you mean. Yeah. But yeah, out of the box, it receives. Yeah, it's pretty nice.
Velcro on the board.
It's all power neutrality. I see about this. It's pretty strong in the dummy leg. It's like the antenna's doing
That's what he's like yesterday about remote, they'll have remote devices.
Yeah. Use it to book. It's a pretty good stored images.
Anytime they have an EVA, can they have one say to shut everything down?
That's sync, and then this is the grayscale. When it sends them to black or white, this is all I want. Already save something. Here we okay, that's what I was gonna say. Usually this only uses default. The good news is shows up as sound card. Scotty. Who is Captain Modes? Get from this thing and use your control house one. Plugging it in. You can figure it out.
Waiting on this to do it.
Feel free to play with it. Yeah, we got it happening. Oh, you know that one? You know, it's about time, it's about space. You know, it's about time. So, last time I was going to have Boston office. I'm not gonna say no, but what is it? Has it got a CubeSat in it? It's got a CubeSat center. I was gonna do it last time, but I said, I do that for my notes. We could always hold it for next year. I wanted to like. We could, yeah, before the prize part or at the end of the prize. Everyone would appreciate it. I mean, that's a kind gift.
Yes,
Yeah,
absolutely.
yeah,
Yeah.
and not even wait to next year. Relevant and working, right?
Right.
Yeah.
All right,
People will enjoy it.
did he turn the stream on?
Oh, I don't know. Yes, I think you did. Yep.
All right, folks, if you guys could return to your seats, we're a couple minutes past 9:45 and we're gonna get started. We can finish up for lunch.
That's a good way to bring back, right?
And the streaming's on. You're good to go.
Thank you.
All right. Is it on? Yeah, it is. It's good to see everybody today, and I am pretty excited about all the stuff I've seen just this morning and the future that we've got going on for us right now. Are you guys hearing me okay? This is
Yeah.
You gotta keep it close.
So today what I'm going to do is go over kind of what we've been working on this past year. Some of it's kind of a little bit from the previous year, so there's a little bit of a gap. And the reason is Ham TV. We received Ham TV and we spent almost a year working on it. And so there's a little bit of a gap from what we were working on before here. But our team actually, I have to say, is a very good team, at least on my staff for the engineering side of it here. So I'm really proud of the guys and the work that they do. Now, I purposely put Frank in front of me to talk yesterday, so I'm assuming I don't have to do more than 1 or 2 slides today. Yeah. So we've actually had a lot of things going on, right? And we worked on a lot of different subjects and so forth. And before I get started, on the last presentation, the students are very important, and that's what I've realized, right? The students are very important. And NASA is very kind. They offered to give us summer interns during the summer, and this year, and just like last year, we had 2. So I had 2 summer interns last year, 2 this year, which was great. And they do a lot of fun things, and They're working towards their PhDs. One of them last year was working on his PhD last year, and the two this year are trying to finish the universities that they're at right now. But it's very important for them. And the education wise, when we talked about the soldering piece of it, I was really surprised because like my summer intern last year, engineering degree, 4 years, now he's working on his master's and going forward for his doctorate, had never touched a soldering iron in those 4 years. And he has an engineering degree, right? I was just totally surprised about that. So what do I do besides giving him math problems and things that he really wanted to work with? I had him learn how to solder, right? Well, that was a terrific idea. I bought a soldering iron off of Amazon. I shipped it to him and everything. And little did I know that I was going to be getting calls every 2 hours about how to put things together and how to solder. And I'm like, oh my gosh. And I'm very busy. I travel a lot. Like this week, I was out in California at one of the national labs, giving a talk on AI. And then I flew back just in the middle of this week to get back here to go to Kennedy to give a talk there too at Kennedy. And last night it was a 3-hour drive getting here. It was terrible. Never do that driving. But I have a lot of fun with what I do and work on, and especially like the cyber and hackasat stuff. I give talks on cyber too. I actually help provide, there's a hackasat event for the Air Force and Space Force that we do every year out in LA. And that is really interesting because the hackers are extremely good, let me tell you. So it's not the way, and you would think of, okay, this is a guy that's just doing coding. But what they do is they organize in a group and they have physics and math and they get like 5 different people that know about different subjects, right? And they get together and they can literally hack a satellite in 24 hours. It just surprises us so how quickly that this happens, that we start off with about 100 groups every year that want to volunteer to try to hack satellites. And then we narrow it down to 7, and then those top 7 really can hack a satellite in 12 hours. It just blows their minds off, right? And to that fact, there was an FPGA that was discovered here a little over a year ago, about a year ago, that was discovered that had a flaw in it, right? 200 satellites are now hackable at this point. It's pretty crazy. So I know Frank gave an update yesterday. I heard that. Frank and I coordinate so well. We didn't even ask each other what each other was presenting. So fortunately for you, I've only got 2 slides on the 40th anniversary. So I'm assuming that Frank did a really good job covering the 40th anniversary and talked about that. So that was great. The part that I did, we gave a full day update with the international folks on what we're doing with hardware and kind of where we're at and kind of the direction that we're going to. And that was a lot of fun, actually. We had a lot of feedback from everybody. We did do a demonstration of kind of the new digital communicator there. We did that. I think we did a little bit of the remote control that Chris has been working on for us. And then we demoed the Lunar Gateway, our first rendition of the Lunar Gateway, which was kind of fun, actually. I'm not sure if Frank gave the numbers on how many school contacts that we did. How many did he give? What did he give? I got probably an update later than what he got, so my number is probably going to be a little bit higher. It's like 1,782 school contacts. It's just amazing, right? And it is so fun to see the kids' faces and then things that happen. And when we hired Tanya as the director for our education piece, I was like, well, that's great. I'm really happy that we have somebody that's in charge of that, but she's been doing a fantastic job and bringing together. I think Frank talked about it maybe yesterday or not, but we have like 30 educators that are together that's working with her right now, which is amazing. And now she's probably got as many people as I've got, actually. I've got close to 30, 40 people worldwide that help a little bit, with our era stuff and kind of what we're doing, which is great. I have a core set of engineers here locally in the U.S. that's about 17 that counted the summer interns that I've got. And I'll talk about that more in a second. But the school contacts, it's really important for the education piece of it. One thing that Frank probably didn't talk about was the mentors, right? And who are the leaders? And it's amazing. Some of these guys, Sergey's done 246 schools. That's amazing, So I don't know about you guys. You've probably done like 50 or 60 schools each, right? I feel really bad that I haven't helped more than seeing this. I'm like, wow, this is great. So we need to start helping more with the school contacts and so forth. But this year we had a lot of school contacts, and just recently, because of the astronauts that were up, we had a lot more contacts that were going on, especially with amateur radio, just direct contacts between ourselves here. You know how many call signs the ISS has? Just take a guess.
5.
That's close, close to first. 7. I didn't realize it. I didn't know that till recently myself. So that was interesting. Now, there's only 2 call signs we primarily use most of the time, and that's NA1SS and RSO ISS. But I didn't know that we had 7 call signs. That was really new information that probably very few people know about. The space station this year got really cramped, right? The Starliner got up there, and we had 11 astronauts almost all the time on the station. And the fun fact is that, well, at least for us, you know, it's pretty small and crowded, right? So there's not a lot to do. And when you got extra astronauts, you know, like, what are you going to fill in your time, right? Well, like Matt, Dominic, and a few others, they were on the radio a lot. I couldn't believe how long they were on the radio, or how much they were, that is. And that was pretty fortunate for us. And now Sunny is the commander of the space station, right? She loves talking to schools and everything. So it's really fun.
Construction.
Oh,
repairs outside, so.
Yeah. Crew 8 just left and they just returned, right? So that's to me, it's too bad because we had a lot of them. We had a lot of hams up there in space, so that was really cool.
Yeah.
But the school contacts, I know Frank went over that. But Harbor Creek was really probably one of our best ones because we had a lot of publicity in that and capabilities of that. But we do have a website you can go to. I'll just cover it in case Frank didn't miss that, and I keep possibly look at that up too. But the nice thing about Harbor Creek is they're having follow-ups, right? They want to get ham TV working, the DVDS working. So we have been working with them on the station and some of the equipment that they need to put together and so forth. So they haven't stopped with what they're doing, which is great. And I'm glad that they're doing that. They had some really good kids there. I was looking at the accomplishments since I came on board about 2.5, 3 years ago, being the director here of engineering change. And there's actually about 22 here. But the fun thing is that it kind of segments in 3 different areas. One is the student mission control mainly, and then ham TV, and then we started work on Caviar. And so just think about what Caviar might need. Does anybody know what Caviar stands for? Wow. Good. All right. So I've got some new stuff for you. So the student virtual mission control, you know, that was where we were going to have a virtualized mission control. University of Berkeley was working on the software for us. They've actually stopped working on it now because their grant money ran out. But we're going to pick that up and continue with it. That's our goal here at this point. And we have the sensor boards. I think I showed last year. We got the, not sure if I showed you the boards last year. It might have been a different conference, but I have the sensor boards now, the alpha models of them, and we got to 90% of that they're working, which is great. And it's pretty exciting. So we'll have to certify the boards, send them up to the ISS, and connect them to the iOS that we call the interoperable radio system. That's this power supply over here with the Kenwood radio that they send 710. We have 2 of the 710s up there. We have multiple 700s up there on the space station today. We only have 1 of the power supplies. We actually have 7 of them built. And there's 11 total we have parts for. But Kerry got tired of building, I think. The power supplies have been pretty complicated. And Kerry is a terrific engineer. The reason that we were going to give one to the Russians, right? But Frank and I had some discussions about that. It's not that we have a problem with them. We want to share everything we've got, and if they ask for it, we'll give it to them, right? But they currently are saying they're using their own power supply, and that's what they want to do, and that's fine. So what we thought about doing is that we're going to save the other 5 or 6 that we've got that are available right now for commercial space stations, because we are working very hard on commercial space stations right now to be on board. 3 of them right now that we're working on, and then we've got landers that are going to go to the moon too. We've got 2 different companies we're working with landers also. And one of them said that they're interested in maybe putting the amateur radio equipment onto it, right? You know, if we do that, you know, it depends on how long the equipment will survive. Typically, it's only like 2 weeks, you know, it's less than a month. But, you know, it'd be fun to say, hey, we made it from then. That's that a lot of fun. So we received the ham TV a little over a year ago in November. we ran it through our tests, and when Kerry did the spectrum analysis, I'm like, we're gonna die. We're not gonna make it through, because I already knew that NASA was Kathy Sham, she was we had some problems. I can't go into detail on them because it was some frequencies that we were covering up on some of the things that they were doing. But we had some RF problems. We took it to JSC, and it was like watching paint dry, because it did 1 hertz at a time all the way up to 3 gigahertz, and it took a whole week for that, right? Fortunately, I had other meetings at NASA, and poor Carrie had to stay in the room and watch the paint dry. We did get through that, and I'll show you some pictures that of the RF and how bad we were. But what really ended up was we had to wait for their report to see what they were going to say and shoot us down, right? And we thought, well, we did the testing in December. You would think you'd get the report back, well, after the holidays, like in January. We didn't get the report till almost June. It was the end of May before they gave us the report back. And it was like, we were asking every couple of weeks about it. And it is really amazing how much stuff that you go through. But the guys that are doing the engineering at JSC and the safety, they have real jobs too, right? So they are buried all the time. And the safety guy, for instance, like with Boeing, we have some other pieces of the ham TV that I'll talk about in a second, but we're going to send up too. But didn't hear from him for almost 3 months, from like June through late September here. And Sean, it was to the point where I was like, okay, I'm going to come down. I'm going to sit at your desk until you show up, right? And I did that. I drove down a couple of weeks ago. I was there at his office at 8:30 in the morning, waiting for him, right? And because I'm badged, I can go any place I found it. And he showed up, and he realized what was going on, because he knew that I'd been leaving him messages, hadn't heard from him, and he had a really good excuse, and I feel kind of bad about it. And everybody's got good excuses, right? But you're right. I did feel bad about being there, because I wanted to get our stuff done, and he did sign off on it that day while I was there, which was great. Yeah, so he was busy with the Starliner, right? The Starliner was at the top of NASA's problems, and then he had a baby too, so it compounded on that. So I'm definitely going to give Sean a break on that, and he was a really good guy. We had a laugh because he knew Sonny real well, and he told me a joke about Sonny Williams that they're both SEALs, right? And they were underwater one time, and I think if you saw Sunny here just a few weeks ago about Ohio, right? She made this big symbol while she was up on there about Ohio. So he was laughing we were laughing about that. And he goes, yeah, I did that stupid ass symbol while we're underwater. And she tried strangling me underneath the water, which was pretty funny. So anyway, Sean was pretty good. And I actually went to the Payload Developers Conference in Huntsville a week ago. And that was, I had real low expectations, because I didn't think anything was, I wasn't going to be involved with anything, right? And I was just going to go there and listen and receive information and come back. Well, the keynotes had like a panel and so forth. They had an astronaut up there, Woody, and I'm texting Kenneth back at JSC. He's doing our operations for us. I'm like, Kenneth, does Woody have his amateur radio license? And I waited about 10 minutes. If I came back, goes, yeah, sure he does. I go, well, did he do any school contacts? And the answer was yes, right? And I'm like, okay. And they had question and answer period right after that, right? So I got up in the middle of it to thank Woody for helping out with the schools and everything while he was up on the station. He talked about Matt Dominic too, right? And how they were teasing and going back and forth and doing stuff and trading stuff on the radio. And so he's talked for 5 minutes. It was really funny because he didn't have very much time, but he talked for a long time up there about amateur radio and work. And so that was really good, and that was recorded. And so I felt that was a good thing for myself to mention that. I'm glad I showed up there. Well, there was there was an AXICOM meeting and a safety meeting. And I went to the safety meeting because I felt bad about being at Sean's office. And, Sean was there at Huntsville too. And we got praised 5 times in an hour. I couldn't believe it. Because of the stuff we did with the ham TV and the way we took it through, and we showed them every bit of every piece of the equipment, and we resolved the problem. I have to mention that the ham TV was built over by Casa Italia, which a lot of you probably know. But it was labeled confidential. We can't show anything inside of it. We can't even open the box. And when we learned we had an RF problem, we're like, what are we gonna do, right? And so my thoughts on this, we'll put a filter on the external side of it, right? So we worked for about 3 months testing different filters and looking at them. And that's why it took so long here last year. And we did remedy the problem with the RF filter, which was great. Oh, by the way, during the summer, I had a summer intern who was he was working on his PhD, but he was he got his engineering degree, but he was really focused on math. So the first thing I had him do was figure out, okay, if we're going to talk to the moon, if we're going to be on gateway in the moon and we're running 10 watts with the 5 and dime type thing from the moon, you know, what kind of ground station do we need, right? Go ask AI, chat, and see what it gets back. I already knew the answers because I had Dr. King's Excel spreadsheet that has 20 tabs on it. It's like, God, we must have spent years doing this thing. So I already knew all the answers already. And quite frankly, I do a lot of moonbound stuff and help out. We have in Kansas, I grew up in Kansas, and my friends and myself, we didn't have nothing else to do but do contests. And so we did a lot of VHF, UHF, and then we got into moonbounds. We had a 16-foot dish, and then I learned University of Illinois wanted to get rid of a 30-foot dish, and we volunteered for it, right? I don't have the picture in here, but I can show it later. But Pete has that up the hill. We put it up at the hill there in Kansas, and so we do a lot of with moonbounds and so forth, right? It was really easy for us, and now we started working with a 6-foot dish, a 2-meter dish, and we're actually making signals and receiving signals with 40 watts off the moon, right? With the 6 foot, so it's getting it really good. Oh, it's the FT8. I'll qualify that. But so I asked Bryce to go to look at this, and what ChatGPT came back with was, you need a 1,000-foot dish and several megawatts, right? And I knew that wasn't correct. And the other thing too is this week when we were talking, I was out at Lawrence Livermore National Labs talking about AI because the labs are trying to figure out how to use AI and when not to use it, right, and so forth. Well, one thing that is in particular is that it does not do math very well. So just keep that in mind, that if you're using ChatGPT for something simple things, it's fine, but if you're using it for a higher level math, don't count on it. It'll take you years for that.
Doesn't do poetry well either.
Poetry. Okay. Let's see. Do you guys know what this is? Well, this was some part of AMSAT and SAREX put together before ERAS. This was the plan for going on Gateway. So Gateway, the Lunar Gateway basically is the next space station that will be going around the moon in an L2 orbit on the backside of it. Well, back in 2019, AMSAT/SAREX came up with a concept idea for CAVIAR. And CAVIAR stands for Communication, Audio, Video, and Imaging Amateur Radio. So, well, you know, I could shoot Frank because Frank came up with that acronym. I have everybody asking, what does CAVIAR stand for? And I'm always thinking like, oh, geez. But it's actually pretty fun. So when we got Ham TV and we delivered it right at the end of last year, question was, what are we going to work on next? What next big project are we going to work on? So Lunar Gateway was kind of at the top. I said, hey, well, we've got the 40th coming up. Why don't we put something together for that to do a demonstration with the 5 and dime and what we could do with the Lunar. And Frank's like, you will never get that done. You will never get that done. And we actually did. I am really proud of the team that we have. We came together, and so by February we had a working model of this, and I'll show you some pictures of it here in a second, which is really, really neat. It looks a little bit different, and actually, so it looks like this, actually. I'll just stop here for a second. So this model here actually has, I put both the 5 gigahertz and the 10 gigahertz antennas on this, and it works very well. So we take, it's actually like 3U, basically. So we've got another middle part here that goes in the middle that we have the batteries and so forth typically in it, and the cameras, and then we have 5 and 10 gigs separated out. So that's kind of what this diagram is, and that's kind of where it was going to, right, and how it was being put together. So we actually accomplished it as an alpha demo, and it's working. So we did deliver Ham TV to the space station in April of this year, and that was like awesome. We got to the space station in April. Come to find out, when they were getting ready to install it, somebody took our location that we had on the floor where we were at before. And so, needless to say, that becomes another 6-month delay. Unbelievable how this works out. ESA had an experiment that was going on, and they put it in the same location because we'd been absent for several years, right? And we were up in the station. And okay, well, we're going to do the diagram. So I said, well, NASA will do the diagrams. And they said, no, that ESA is going to do it. They have to do it, right? So we have to wait a month or two. And then they come back and say, well, why don't we have NASA do the diagrams, right? And so then I'm working with somebody down at JSC, Mark down at JSC, and so we work on that. Then he throws the diagrams back over to ESA. ESA looks at them and says, okay, this is configuration that we're close to our thing. So they want to try to keep both Ham TV and their experiment the same place, which is fine. And I'm all, that's fine, that's great. We're all for that. Just means we got to do a little bit of changing with the cables and how it's set up. But that worked out for another month or two. So there's 4 months going there already, right? Then I go down to JSC when I was down talking to Sean, and I'm talking to the lead there. We decided on the diagram we like best for the cable diagram. I go down to Kenneth's desk, and Kenneth actually had found out that this experiment rotates. The experiment that ESA has, which I can't talk about too much, it rotates every 30 days. And so they want our equipment to rotate and move too, all 30 days. And so not only we got one diagram, we got 4 diagrams we got to be working with. So there comes another, so it's almost 6-month delay on trying to get Ham TV up there. So I think we've got it resolved now, which is great. And so we're kind of moving forward with that at this point in time. I do have, I've assembled a fairly good team, and a number of you here have been helping with it. And I don't have everybody's names on this because there's probably about 30 folks here that's helping, Graham and everybody else and the team from UK. And we have a lot of folks that's helping, but this is kind of the core, and I'm starting to build out teams underneath the core. So we have 13, 14 folks here that work on things. Carrie actually does all of the RF stuff, testing for us primarily. John does a lot of stuff with satellites. He does high level communications, which require stringent packets going up to the satellites because he does all the paging. So the company that he actually works for has like about close to 3,000 hospitals in the United States, with all those pagers. So you have to get those synchronized just right to get the right guys and everything. So he's very, very good. He actually designed this at Motorola, and so he's really, really good. And then Karen, of course, most of us know, he's kind of my Raspberry Pi Foundation leader in SSTV. He's been working on all that. Lou is invaluable to everything. Lou saved us so many times, it's not even funny. I'll talk a little bit, but we had an incident where we were trying to get the RF filter through, and we had developed this 3D case to protect the RF filter because of the sharp edges on it. And the material that we were wanting to use, NASA shot it down. I couldn't believe it. And this was in December of last year, and we had to deliver before the holidays, before they shut down. Otherwise, we're out another 6 months. And we didn't know what to do, but it was Lou that kept, because he's worked so long at NASA, he knew that something was up. And he kept saying on the call, you need to check on that. You need to check. When I hear that 3 times from Lou, I know we need to do that. And one of our new engineers, Hunter, he was a mechanical engineer out there. He is fantastic. He throws stuff together. He's now at Johns Hopkins right now, but he was at NASA for a little bit, and he took it to heart. I mean, I swear that night, the next couple of days, he had figured out that material that we were choosing was the #1 material. It was not the one that was supposed to be not used, and I couldn't believe it. And the funny thing was, I was over at Kennedy here the last day. Let's see here. So Thursday evening when I got back in from California, I was up at the Courtyard Marriott there, and there was a guy from Blue Origin there. And so I was talking to him about 3D materials and things that they use and he came right out and told me, oh, they use Altium, right? And I'm like, well, that's what we asked for. And so he knew exactly which material was the best material too. So it's really funny how that gets around to everybody and how they work with that. So that was pretty fun. So I had summer interns, and I mentioned I had summer interns earlier. So last year I had 2, and this year I had 2 more. One of them last year actually worked over in STEM education for us, but these 3 worked on the engineering side for me. It was pretty fun this year because for the final papers, they have to give a talk up at Goddard. And so I had the two engineers with me up there. And so it's a 2-day session. So there's like about 50 summer interns that are giving their papers and talking about the things that they've accomplished. And so the first day we weren't involved, but the second day we were involved in the afternoon. And the really weird thing is that the first day and the first day and a half, there was like 1 or 2 questions from everybody with each one of those papers and presentations that they did. When they got to the amateur radio stuff with what they were doing with the assignments I had given them for putting together the caviars and so forth, there was like 10 questions. And I'm looking at Frank. Frank's looking at me like, okay, what is going on with this? And come to find out, the entire audience, over half of the audience was amateur radio operators in the auditorium there in Goddard. I could not believe it. and when Bryce and or Michael and Caden got done with their talk, they asked, "Do you guys have your amateur radio licenses?" And we wanted them to get their amateur radio licenses. Bryce had actually got his. Michael worked on it. He showed up at the VE session, but the VEs didn't show up. and Caden didn't have. Caden was buried because he had summer classes during the summer, so he didn't really have time. He didn't make that. And they asked him, "Well, okay, well, you guys don't have your amateur radio license. Would you like to get them right after this?" But they were like taken by surprise. We were too. We were like, "What?" They gave a VE session right after that. We left right there from the auditorium at Goddard, went over to another building, and while they administered the test to him, and Michael passed because he had been studying, which was great. But that was really interesting. And the outcome from that is that I work in the industry, right? I'm CTO for a company, and I started thinking about that the other day because there's like a $1.8 billion contract out that we're trying to win right now with NASA. And I remembered one of those papers talked on the subject on the thing that we were most important to. So I went back to look at the mentors and I called up the mentors. And I was up at Goddard a couple of days ago. And the mentors, I got the RF engineer, they're amateur radio operators. I got the RF engineer who did the communications on Orion and Artemis. He's now on board as my engineering team. That's Taylor at the very bottom there. So he's part of my engineering team now, which is awesome. And then Thomas here, he's a software guy that does all the SDR work for NASA for us. He redesigned the Pluto SDR. He has his own board laid out and everything for it, which was really interesting. So it's made me start thinking about this, right? That we need young folks, but I also started thinking about, I need to get folks at different centers, right? Because and I don't know if Hunter's online here, but Hunter, Frank and I have been kind of grooming him because he works and he really loves amateur radio and believes in what we're doing and so forth, right? And he is super intelligent, and I think he's going to be our future, right? And we need folks at these centers, or even like SpaceX and other commercial vendors. So I'm targeting those folks now, right? So I've got 2 guys now with SDR and RF capabilities here, which is super. And I'm so proud that we've got these guys on board. And I'm proud of the summer interns too, because they are very good. They're amazing folks. But I did have a learning experience last year with the soldering thing with Bryce, right? So NASA gives me like a list of several hundred candidates to choose from, right? And I have to go through this. It takes me like 2 months to go through all that stuff. But I decided I'm asking every one of them if they learned how to solder, which is good. So now both these guys actually did. So they actually had, and they did a really good job on some of the things that they built for us here too, which was great. I already talked about the student mission control. I guess we're moving forward with that now. So once we got Ham TV down here, we started refocusing our energies. One of the things that we had stopped with the student mission control was it was during COVID, and we were having a hard time sourcing parts, right, and getting boards. It took us like 6 months to get the alpha boards back too. It was really a long time. But these are the sensors that we were focused on with the student mission control. There's really only about 10, but I added these other 2 for controlling the radio, and that's what Chris is going to demonstrate here after I get done. and also SSTV, right? So Karen actually helped out with that, which was great. And then we did an experiment at the end of last year with SSTV with the ISS, and maybe some of you participated with that. But I asked Chris to put together or help with put together a piece of software we could automate sending out the pictures because the Russian side was down. The computer wasn't working over on the Russian side, and so they've been down for several months, and they've been trying to fix it, but they didn't have it fixed. They do have the new computer up there now, which is working. But we decided to use our ground stations to use the gateway, the crossband link, right? And that's how we did the SSTV mode. So, but working with this piece of software has generated a lot new ideas on things that we can do and so forth right now. And Chris is going to demo some stuff here in a little bit, which is really pretty cool. This is the picture of the alpha board. 90% of it's debugged and working. The couple components that are missing were parts that we couldn't source because of COVID. But we've circled back around now and started refocusing on this and getting ready to move this forward. My plans is that you see the power supply over here. My plans is to have a drawer underneath of this, which has two trays. One tray will have the sensor cards in it, right? And so we'll plug the tray into it. The second tray will have SDRs. So the plan is to have multiple different types of SDRs that we plug into the second tray. We're making it real easy for the astronauts to plug them in and take them out, right? So I think this will be a good test for us. We have 8 antennas on the ISS today, and 2 more patch antennas. They're LS antennas. Each one of them are LS antennas. And we're letting another Italian company right now use them too. And let me show you some pictures of that. For an experiment that they're using with the global navigation. So but having that terrain there is going to allow us to use those other antennas and so forth. And we may do an experiment outside on the ISS too, on the Express rack with a Caviar too. I'll mention that. But while we were waiting, I found on Amazon a card that did like 5 of the sensor things that we did already. And it was like, wow, look how small that baby is. This is the card. And it's the size of the Pi, right? The Raspberry Pi Zero, the exact same size, and it does all of them except for the real-time clock and the ultrasonic microphone, and these others are different. I'll show you this here too. We actually added in the cosmic radiation detector from MIT, which is really pretty cool. This is it here. It's a little board, and Carrie's put this together for it, and it works very well. It has a little LCD panel on it. I wish I had that lit up, but we bought a number of different ones. And I actually bought one off of Amazon. It's this. I think I had it with me last year. I just bought it last year when we were at the AMSAT event. And I went in for a stress test, heart stress test, and they'd shot me with some liquids. And so I took this in, and I asked the nurse before I got there if I could use this when I went in. And she goes, oh, sure. So after we got done with all the questions, I pulled this out, and she goes, oh, that's really amazing. That's so tiny. Her equipment was like huge, really, really old. But, it was showing like 300 some rads or something like that when I put, and it was beeping. It's like, yeah, you're going to die. So I was basically saying. And I was like, wow, that's crazy. And just a couple months ago, because I travel a lot, going through the Air Force, I did an experiment with my daughter a few years ago when she was going through school, and it was collect water from all 50 states. So I collected all these bottles of water, and we tested, and we had this stuff for a science project for her, and which was really cool. So she got recognized for that, which was great. I decided, well, I'm going to take this and I'm going to put this and turn this on to go through the luggage security points at every one of the airports that I go through, right? And I wasn't expecting what I saw, actually. And the first time I went through, it was like 400 microrads here, right? Which was like, okay, that's cool. And here's going through, and they did that test. So then I went out on the internet to look up, kind of where that stood at here, right? And I'm like, oh my gosh, this isn't good at all, right? And I tell you, most of the airports are like 560 to 590. And small airport, I was at the Idaho National Labs, Department of Energy lab about 4 weeks ago. I went through there, and in my mind, I call it like a Kodak airport. It's real small and everything, little tiny machine. Well, they couldn't identify everything in my bag. So what they do, and I wish I had the picture, they ran it back and forth 3 times, right? I'm like,
Nice.
oh my gosh.
Free
Well,
test.
so my tip to you, never lay down that conveyor belt. Oh my gosh. All right, so the HAMP TV is pretty exciting for us. We're waiting for that to get this going. And the reason I'm covering this a little bit more here is because I'm going to show you kind of what we've been working on and what UK team has helped us out with and at BATC. But this was a test that they'd set up in the lab down at JSC and testing it here. You can see how the baseline went from here up to there, and it was like I knew we were going to fail that test right away. So basically, their spectrum analyzer HP instrument, which actually Curie has HP also, went from a minus 127 dB when we turned the equipment on, the baseband raised up about 40 some dB, and that was not good because basically we're wiping out all the other visiting spacecrafts and everything aboard the ISS, and we knew we weren't going to pass at that point. So, but we kept smiling and helping them out as much as we could. And I felt bad about Curie being there for a whole week. You know, that was a long week there for us here. So that was another screenshot here of that. But we built we tested several filters. We tested, and I have to laugh a little bit. So this is a Faraon filter that has 8 cavities on it, and it worked the best. This is the one we're using right now. And Lou says, don't tell anybody, but we got this off the tailgate in the Hamfest, right? It works very well, let me tell you. So we did buy a commercial one, another one that we spent a lot of money on. And then the UK team built one for us too and sent it to us to use. And it was a 4 cavity, and it didn't quite knock everything down. So we decided that it was best if we better go with the bigger one and be safe about this because we don't want to lose anything. Or right now we're a facility on the ISS, which is great. And I'm sure Frank talked about how we were the very first payload on the ISS. So because of the trust that they have in us, we want to keep that, right? We're not going to let anything happen. And it is very surprising how others do, that they don't tell NASA what's inside their equipment or what they're doing with it, right? I'm not a believer of that at all. So we disclose every bit of information, good or bad, and plan for it. So, and the good thing is, I build a lot of trust and relationships with these folks. This is kind of what happens every place. For instance, like with Department of Energy's NREL, which we're building out the new grid for the United States and microgrids and so forth. They asked me to write 3 different grants. I won one grant, which is a microgrids to help out the Eskimos and up there right now, and also in Hawaii on Maui where they had the fire and so forth. So I won that grant. I wrote 2 more for the microgrids here now, and we're waiting on that to see what happens with that. So the labs trust me, and I build the relationship by being open to them and telling them, you know, okay, I may not have the best thing, but somebody does. This is what we should use, right? And so that's working out very well for us. The part that I don't like basically is that NASA's gone to this COTS thing that they'll run things through safety and engineering just as fast as they can because you bought something off the shelf, right? And I don't believe in that personally. I think you should be showing things, and I'll show you diagrams here in just a little bit, but you know, that's where they've gone. And, you know, and maybe that's because of the new commercial space stations and so forth, because I know Axiom and SpaceX, they don't disclose everything to NASA, right? Which is good or bad, but I don't really believe. I think we should share everything actually, just to be on the safe side here. So this is the interface basically from the RF side on the International Space Station, right? So this goes out to the patch panel on the outside from the C brace here and connect that. So we got a lot of cables. It took us about a month to figure out the interconnection on the cables to get this to work. It was very complicated because unfortunately, when the design was done for ham TV, they used military connectors, right? Well, during COVID, we could not get those. And because of the war and everything that's going on, they're being snatched up like crazy. So we couldn't get those. So we had to figure out how to get this to work. We actually borrowed this cable. We commandeered the cable, I guess I'll say, from the Italians because we were supposed to send it back. Maybe we will one of these days. But we wanted to make it work. So it's up on the station right now. And And the good news is that I have payload developers rights, so I can sign off on things going up on SpaceX or Northrop Grumman today, or bring it down. So if we don't get over to Axiom, which is going to be the next space station, it's connected to the ISS. My plans is to request that we on orbit move all of our equipment up to Axiom. We had a meeting with the VPs a little over a year ago, and they were like, they were okay with us being on the station. They realized the value of it, especially for backup, right? Because they have seen what's happened when you don't have something that's completely disconnected to your system, right? If everything's connected to your system, that you could be down. And I think I mentioned last year that the space station, it rolled over 300 to 540 degrees here a while back because some of the engines on the visiting vehicle, the Soviet vehicle, fired, and the astronauts didn't know. They're just floating around up there, right? They have no idea anything's moving or spinning. And they were out of communications for 90 minutes. They didn't have communications for that. And so it was really amazing about that. And we were sending people to Goddard and JSC, get prepared to talk to them. Fortunately, I think the engine stopped or something, that they were able to get back to TDRS because the dishes are on one side, right? We have antennas all the way around the station, which is great. So when anything happens, we can make contact with it pretty much. But anyway, that was one example. And I think you guys know about, I think it was Mirror, yeah. It was out of communications for almost 5 days, and it was amateur radio that saved it, right? And getting it back in communications. And there was an incident, a small incident, I think, with the space shuttle. Frank talks about it once in a while, all the details on that. But so we built the filter, we built a 3D case for it. We passed all the certification pieces of it, which was great. So there's a group at NASA called Hunch, and they are great. They actually, we had them 3D print the cases for us. They're very expensive, but so the idea was I was trying to go around the certification process, right? Because here's a group at NASA that does this type of thing. They charge a lot of money for it, but we get the certification pieces and everything for them. And we had a deadline we had to meet to try to get it up to the station. So that was great. So we did that. We also did the testing that same day with the capabilities of it. And Carrie set this up, and we were doing the testing with it. And Kenneth was our model on the other side. He was helping us out there. So that was actually fun. We actually got it all working. And this was a picture of Kenneth. He had his glasses off. And I was really worried he had to sharpen eye back because we had to make sure everything was smooth on this, right? If there was any piece that was sticking out, that catch, because Sean's using gloves. They have special gloves with light looped cotton, right? So they go over all the equipment. If anything snags that cotton, it fails, right? And of course we had like a couple places that had something, and so Kenneth was actually carving them out, being very careful there with it. So we did get through all that, and Sean passed us, which was great. And so that we received our label. So that's a big deal, receiving your label and having it labeled. And at that point, we had 30 minutes to leave NASA to run over to get into the bonded area. And we run out the door. Well, actually, I'll take this back. I was a little bit worried too, because Kenneth is carrying the ham TV and everything in one hand, going down a flight of stairs. And I'm like, we're dead if he falls down with this. And we get over to that door. And so it has like a little peephole in this door. We're off of NASA's campus down in Houston, and we're at the bonded area. I can't tell you where it's at. And we're pushing the little doorbell button. We can hear it ringing inside. But nobody. This is December 22nd at almost 5 o'clock, right? And nobody was going to be there after that. That was the deadline. And we just kept pushing and pushing that button. Finally, this really, really nice guy, he showed up and he let us in, and we went through. And I can't show you all the pictures. I don't think I have them in here. But I'll show you one picture. The problem was I love taking pictures because I refer back to pictures when I'm gone because I travel so much and everything. I'm taking a whole bunch of pictures and everything, and then I realized there's a sign up that says no pictures, right? And I'm like, oh man, I'm in trouble. But this was everything put together with all the labels on it. We had one label that was missing that they needed, and so we asked the young man, and he He goes, well, if you want, you can write this out. I'm going like, okay, give me the paper. You got the paper? And he goes, yeah, sure. So I hand wrote everything on it. So hopefully it's okay up there. You know, on the ISS today, they use RFIDs, which is really pretty interesting, right? So they got their little scanners that go through and they scan forward, which I thought was a good idea. But they also have the scanner set up at the doorway. So when you carry a piece of equipment for things, you catch where it's moving at on the space station. And that's a brilliant idea, actually. And one reason that's a brilliant idea is that when you have packages like this on top of each other, you cannot get a good ID on what's in that area. So it was a better idea to have set up in the doorways as you go through each one of the things. So we have the space station has new cameras on it that they only have HDMI. Currently, we're using a backup camera for a space lock that still has the RCA NTSC input into it. And that's going to go away. We know it's going to go away, right? I talked to the guys there at Johnson quite a bit, and they've already got all the new cameras up there, and they've got the next generation that they're planning to put up there too. So we had to get an HDMI converter, and Lou and Art had developed a converter and put that together, and it was nice. But the problem is, we know from our experience, it's going to take 6 to 9 months to take it through certification process, and we don't have that timeline to do that, right? And so we went out and bought one that was COTS, and I looked on Amazon for quite a while, and I found one that had 2 inputs, and I'm like, aha. We can use one input for the cameras up on the space station, and we can use the other one for the Pi that we're planning to set up there so we can send pictures, right? So that's our plans right now. And we've actually been signed off on this engineering at JSC. I took it all apart. It was like, and they asked every sort of questions, right? All materials and voltages and the case, what's the case made out of? I had to answer all those questions. And it was difficult. It wasn't very easy. But we've been signed off on that, and we got the labels from Sean. He signed off on that. Unfortunately, because we learned real late here that we have to move 4 times around my USB cable to this thing for powering it, need to be longer. So it needs to be 10 feet long instead of 6. So I've already sent that in, and I did a block diagram for Sean and everybody to show how this is going to hook up. And basically, this is the video input, right? And HDMI interface for it. And then the new USB cable, which is the dotted line here, that's going up and down. It plugs into the power supply on the side. If you look at the side of the power supply over here, there's USB ports on the up to down capabilities for that. So anyway, I think we resolved that. We're kind of moving forward with that at this point in time. So lunar, when I went to the 40th anniversary, I had my slides situated where I was going to talk about the student mission control and everything else on down the line. Oh no. We had to do lunar first. So I had to redo all my slides and put lunar up first. So the one thing we've got to figure out is what do we have for interoperability on frequencies up there? And that actually became a big question and a slight argument, I think, with the international folks, because there was different thoughts on how this really works. And the big problem was the big problem really is behind the moon. And behind the moon in the L2 orbit, there is going to be new radio telescopes back here, right? So we can't transmit on a lot of frequencies, and so we're very limited to what we can do. But we can do the 5 and 10 gigahertz. Our friends over in Italy wanted to do 70 centimeters and 2 meters. Well, we can't transmit on 7 centimeters and 2 meters, actually. So, but I later had this idea, well, we can receive on 70. And I've been doing moon bounce. We've been doing moon bounce with a kilowatt off the moon for quite a while. So we're thinking that we can still use 70 centimeters with receive, but not with transmit, right? So that's actually really good. So that it is becoming a super highway going back and forth to the moon here in the next few years, right? And the capabilities of that. A lot of us going to start transitioning to using laser light for communications. NASA Goddard is very, very focused on that today, on moving away from RF and going to light, actually. So that's fun. And we've been doing a lot of testing on the space station, too. We've been testing that. I also have a supercompute up on the space station. I work for the Hewlett-Packard Enterprise, and I have a couple different capabilities up there, and that capability is actually going to be moved out to Gateway 2 and placed on Gateway. The biggest problems that we have with the new space stations is that they're very limited on power on the capabilities. And Like for instance, the gateway, when I was told we were in a meeting, they said you can only use 200 watts. And I just almost started laughing. It's either start laughing or crying because the CPUs with Intel are like 250 to 280 watts, right? And I'm like, there's no way we're going to be able to do this. That's with like 2 or 4 cores. I mean, we're talking about having 60 or 90 core machines up there, right? And 4 blades. So you take, there's no way that's going to work. Now, on the space station, it's great because we have kilowatts of power up on the space station because of all the solar panels. It's actually pretty neat. So actually fun. The only thing we have to really worry about on the space station is the radiated heat. We have radiators on the compute side of here. But the lunar stuff is pretty exciting for all of us, I think. And we have met with several of the branch chiefs, the deputy chiefs, Frank and I have, over the past year or so here. And we were a priority on the International Space Station. We were one of the very first payloads to be deployed on the space station, right? But that's all changed because communications got evolved a lot better, and now they got the email and everything else, right? And they've got satellites up. So we're not going to be the very first ones. And Frank and I were on a call 6 months ago with 6 deputy chiefs, and there was presentations. And the presentation right before us was a group out of Goddard on global navigation and how they can improve and pinpoint, everything where that's at. It's very, very important, right? And they did their presentations right before us, and they shot them down. And I'm like, this is not good. And because they're not a priority, and we knew that we're not a priority either. So Frank and I did a dance, and we said, well, we don't have enough time for our talk, and we were supposed to have 30 minutes. The head went over because the GNS folks at Goddard was really like trying to push and trying to make sure that they were going to be up on the gateway, which made a lot of sense, and that wasn't going to happen. So Frank and I said, well, let's tail this off to some other time, right? And so they agreed. So it was like we didn't get shot down right away, right? So my approach on this, when you hear something like that, you start working on individuals individually, and that's what we've been doing. We've been working on the engineers and also the deputy chiefs, and we've got a lot of recognition from that. So the interesting thing is that the global navigation folks came back to us and said, hey, we've seen your concept and what you're planning. Can we be inside of that? which is great, right? So there's somebody asking for to be inside of what we're doing, and they know it's important. They're important too. Well, the weird thing was I was down at Johnson Space Center here a couple of weeks ago, and I went through our futures, talking about work, because I wanted to give them a heads up, kind of what we're doing to get everybody on board and thinking about this, because from our experience here the last year or two, it's good to give them heads up, right? Kind of where we're going and the testing that they're going to start thinking about. And one of the guys was a deputy chief for the video communication. He goes, I want to be in that. And I was taken away. I'm like, he goes, can we do something? Because they have low bandwidth. And I'm like, well, I wasn't planning for that, but certainly we can work that out. That's not, so I've got to go back and rethink this a little bit, but there's several teams within NASA that are trying to figure out how to overcome problems, and not besides power, but also how to get the communications going. And I think we're going to be part of somebody's, but right now we have 2 different groups that are asking for our help, which is really amazing. And we do have our design concept is working. I didn't bring it because it's pretty big, and Frank brought the power supply and everything else. So it is actually about 3 U high, and we've not only put this together, but we've put together the ground station too. So our demos actually have the ground station, which does the 5 and dime and communicating, and Chris has done a perfect job with the capabilities of the software for that. So we're moving ahead pretty good at kind of what we're doing here. We have narrowed down the frequencies and so forth and what we could do, and I think we've got the Italians on board, and we're moving forward with that at this point, which is great. This is what Caviar looks like over on the right-hand side. So 5 gig at the bottom, 10 gig at the top, and it works very, very well for all different modes. We've done all different type of modes with it. And there's going to be, so this was a concept design. It's in a 3D type plastic case. The good thing about this is that Hunter, our engineer at Johns Hopkins, he's a mechanical guy. He only works on satellites. He designs and all. So we've got a guy that works on satellites, and we know that he'll put together the nice cage for us and everything to mount this into. This is kind of a block diagram of how it's split out. Today, we're using the analog devices, Pluto inside of it. I have 2 or 3 other vendors that we're working with that one of them flew on Orion because of the radiation up there. The radiation's pretty high up there, right? And equipment won't last very long if we don't get something that's protected. So, and that equipment is actually pretty expensive too. It's not like spending a couple $100. We're talking about $15,000 to $2,000 per SDR. So it's pretty expensive. Anyway, our model set up, and we went to the 40th anniversary, and this model is kind of the second level. It has capabilities of doing the 6 antennas at gigahertz levels here, of course, which is great. We have the Pluto board inside here. At the 40th anniversary, we had 3 of them stacked up inside to manage all 6 antennas, which actually worked out very well on that. And I wrote some pieces of software to make it transition from different types of modulation capabilities here. And that worked out pretty good. And then I worked on another piece of software. So the goal for us was to really figure this out, how we could figure out which direction the signal's coming from Earth, right? And which antenna to use. And that's what this software did. We used our SSI from the Pluto to understand that and decode signals from Earth. And that's what this is doing. So this basically, if this is rotating or this is facing the antenna, you know, this is going to choose the best antenna back. And the demo was actually really good in February at the 4th anniversary. And why it was important, and it showed itself very well because Mike Kincaid, one of the 3rd level people that we coached to Bill Nelson, he was at our event that night, that day, giving a talk that night. And that's when Intuit Machines landed on the moon. Okay. So Intuit Machines landed their lander on the moon, but unfortunately it was at a 30-degree angle, I think, and it wasn't communicating. And so we had 2 large screens at the event, and they're like 20-foot screens. And Mike's like saying, I should be back at God. He was mumbling, he was saying that. And so on the screen, we had the operations that was going on and them saying, we're waiting for communications. We're trying to get communications. We know we've landed, we touched down, but we haven't established communications. And our team, Phil Goon-Healy, was there because he was doing his demo with the next generation stuff. And I asked Phil, is there any way that we can maybe test this out from someplace else? And he said, sure, just a second. So he spent 10 minutes logging in and looking at stuff. And sure enough, he was seeing the signal on his screen. It was like really funny, right? And it was amazing. And I'm like, is it okay for us to put this up on the 2nd screen, right? And Mike and Kate came on, what are you guys doing? I go, well, we're hearing the signal from Intuit Machines. And the other screen's saying they can't even hear it. They don't even know where it's at or what's doing right now. They don't even know if it's alive, right? And he's like, what? And I go, is it okay if we put it on the screen? He goes, yeah, sure. So we put it up on the 2nd screen. So we had 2 screens, one saying we're not hearing it. The other one, we see this signal coming down, which was great. And it was really a high five for us that night. And so that made us stand out with Mike Kincaid, who reports to Bill Nelson. I'm sure that got told to a few people later on, right? And the Gateway folks, the deputy chief there, Blanca, she came to give a talk Friday evening, but they were so impressed with our demo that we had, and I think she heard what happened the night before, but they came back on Saturday. She brought 2 more people that were working on Gateway to see what we had. So the word's getting out, and she's been calling Frank back a couple times, what Frank's been telling me, which is great. So I think, even though we're not a priority today to be on the Lunar Gateway, I think we will be on it. And we have the equipment to do it, and we've proven ourselves, and we have the right people, because when they start asking about the people that we have, and I start showing the list that we've got, and you know, all of us, right? We have backgrounds on lots of different things here that we can solve problems pretty good, and we've done a lot of stuff in the satellite industry. So we need help from you guys, everybody, and whoever else that might be able to. I mean, I'm looking at folks at all the different centers now, thinking like, I need to. I want to try to. I want the best people, of course, but I do want to try to focus on folks that are just starting their careers that they have a great interest in. That's right. And that's really good. So I was at a space conference a year ago, and I might have mentioned this before, but on Artemis, they deploy satellites from Artemis, right? And I think there's a real opportunity for AMSAT. I did talk to the manager there, and he gave the nod at that time saying, yeah, he would help us, right, and work with us, right? And so they can launch up to 20 different CubeSat satellites from Artemis, which is great. Okay. And so it's something to think about. What they do is once Orion's left Artemis, they send Artemis out to a higher orbit towards the sun. That's like, oh, wait a minute. Maybe that's something we could use, right? So that's great. Well, the other thing too that I was talking to Frank about, and I know that you guys have thought about this and worked about this, and we're launching CubeSats off of the International Space Station. I have the authority to sign off on things going up to the space station, and we know we have the Japanese CubeSat launcher. Right? We just got to get queued up for that. But I think the biggest problem that AMSAT had is how to pay for getting stuff up into space, right? And then also controlling the deorbiting. And we've got the engineers working on deorbiting here, but I can get it up to space at no cost. And I can sign off on that. That's the things that we should take advantage of while we have it, because I'm not going to be around very long. But, yeah. So, Art. Chris is going to talk about Art. Let's see, how long have I talked to you?
You're 5 over.
Oh, okay. Well, I thought it was only going to be like 5 minutes today. So I'll stop here. I'll let Chris talk about ARC here, and we'll go from there. Thanks. Oh, I forgot to show you. This is the pico tuner.
You see 2 minutes to set things up.
Oh. This is the pico tuner from VATC. I had the summer interns put this together, by the way. It's about $55, $70. And so if you want to receive the ham TV, I would suggest looking at the VATC site. And we can help you out with that too. There's a lot of good things we can help out with that. Go ahead.
Quick question, and this might be kind of simple-minded, but I noticed you chose the hexagonal shape. Is that to accommodate 6 antennas?
Yes. And the interesting thing too is I go to Department of Defense. So the hexagonal is to accommodate the 6 antennas, and because the spacecraft is going to be moving, right? It's actually a really good idea. And the reason is I go to these Department of Defense conferences, right? I was to the biggest one in San Diego back at the beginning of the year, and I didn't have enough time to show her the pictures here, but a lot of their equipment, they have like surfboards that have a lot of electronics on them. And at the top of it is a hexagonal antenna, so forth. And I was talking to them. They're using the same concept we're using. These things, they got 20 of them out here in floating between Cuba and the US. They're surfboards and so forth, right? And with the antennas on top. And then over in the Red Sea, over in Asia, they've got more of those over there. But the new generation ones of these is when they detect that there's a threat, they actually will glide under the water. It's actually pretty interesting because they're surfboards. I mean, it is just surfboards with solar panels on top of them and so forth. It's really amazing.
Thank you.
You're welcome.
All right, thanks, Randy. So I'm Chris Thompson. Closer. I'm Chris Thompson. Everybody hear me?
Yeah.
Closer.
Yeah.
Does it work? That's as high as it goes. Does that work, or is that not near enough? No, it's not working.
No, you need to be closer to the mic.
All right. I'm Chris Thompson. I live up in Canada now, so I'm VE2 TCP, but many of you know me as G0KLA. And I'm going to talk about the automation and remote control of the interoperable radio system. And when we say the IORS, we sort of mean the whole package. That's the multi-voltage power supply, which is the unit that turns the somewhat dirty power from the ISS into really nice clean power that we use for the radios. And it includes the Kenwood D710 that's on the station. Is that better, Lou?
Yeah.
You're in a signal, Lou, if I get too far from the microphone. So everyone knows what the IRS is. There's somebody that's a picture, I think, just from August 5th.
She did a lot of contacts. It was great that they were stranded on the ISS because she had a bunch of time to do content. Now I think they're officially on their missions. Maybe she doesn't have as much time, but we do the school contacts with the radios, so it's very important to us. If we want to change any modes on the radio, then literally we have to schedule that through NASA to get the astronauts to come and change a mode. I think Frank said yesterday it's $4 million of in-kind support we get from NASA, pushing buttons on the radio and doing the school contacts and so forth. Typically, we need them to do that to go and do a school contact. But if we want to run a slow scan television event, or if we want to change the crossband repeater to do APRS while the APRS is down in the Russian segment, we have to schedule someone to do that. So the idea is, can we automate that? ARC should therefore be able to turn the crossband repeater on and off, start and stop APRS, send SSTV pictures. And in particular, as Randy mentioned, we've got this future requirement to send telemetry down from the student sensor board. So can it also manage that? Can we go into a telemetry mode, downlink telemetry from the student on-orbit sensor system so that that can flow into the student virtual mission control? So we'll take a brief look at kind of what that is, how that's all set up, and I'll try and do a live demo, see how well that works. So the prototype uses a off-the-shelf COTS Raspberry Pi 4. That's the computing platform that I was asked to use. There's some heritage of the Raspberry Pi on the space station through the Astro Pi. It's also obviously a very capable device, and we're in a relatively low radiation environment, so we know that it works on the station. That is powered from the multi-voltage power supply. They have 5-volt out ports, and the configuration we've got, the Pi only draws about 700, 800, 900 milliamps, that sort of range. We connected to the radio through a commercial DigiRig, sound card interface that works very well. We use the OEM Kenwood serial cable, or a newly manufactured one, to communicate through the CAT interface. And the Kenwood has 2 serial poles. We have another serial connection to the head unit of the radio, where it has its real-time clock. We actually use that as our real-time clock, so that the Raspberry Pi doesn't need a real-time clock. Although we've got some discussions as to whether the battery is still good in that head unit on the station. That's a separate discussion. And right now in the prototype, and what I've got here today is a prototype, we've got this SenseHat C board that Randy showed, a little small board that we're using as a proxy for the student on-orbit sensor system. So the hardware is in a 3D printed case, and Hunter designed the case. The terrible 3D print is all my own work. You're not supposed to have a wood grain effect on the top of your 3D printed case unless you've configured your printer incorrectly, but it works. It's got 2 fans inside, so that if one stops running, the other one is still running, because we have no other way to get the heat out in microgravity. We use a high endurance sort of industrial SD card with what's called single layer cell technology. I think it's actually the oldest technology they had for those types of cards. And there's a couple of papers out there talking about the fact that that performs best in sort of radiation environments. So the advice from NASA, if you're going to use that sort of technology, is to use this single layer cell technology. I also make the boot sector read-only, and I use the overlay file system, which technically means we don't write anything to the SD card. So there's no writes to the SD card. All the writes go into basically a RAM disk in memory and get thrown away when you reboot. And that's really important, because the Raspberry Pi doesn't like being just shut down randomly, and this has to be shut down randomly. As soon as there's going to be an EVA or there's a visiting spacecraft, they just turn off the multi-voltage power supply. In fact, they need to have 3 ways to turn it off, apparently, right? And all 3 ways will just kill the power to the Pi instantly, so that it goes off. So we have to make sure there's no corruption there. We use a separate USB drive also with SLC technology, and we will put the writable files onto that. And we set that up so that basically we can fail on write in anywhere. And sort of, you're mostly writing data there when people are uploading data from the ground. So failing to write there is the same as the packet not getting through. It's kind of how you have to think about it. So if it gets shut down right in the middle of somebody uploading a file, it doesn't matter. It's no different than they lost the ISS over the horizon, but sort of think about it that way. So you know, write the code to try and make sure that you don't cause any corruptions. What else? There's the DigiRig, talked about that. There's a spare USB port. So that allows us to have files in orbit coming from a camera on the space station, for example, that can then be broadcast down as slow scan TV images. We physically disabled the Wi-Fi and the Bluetooth. That stops us having to qualify those. It stops us having emissions in those sections, right? It's going to be in a metal case anyway. So we're not connected to NASA. We're a completely separate capability from an emergency communication perspective. And we have an HDMI output, as Randy said, where this connects into the ham TV system, so we can produce test cards or still images. I really liked Alan Johnson's overlay on images that he showed. So I'm thinking I'm going to look at his code, how he's doing it, and it looks very nice. The software, so there is a custom piece of software called IRS Control, a C program that runs from System D, boot, and then that kind of controls everything. That talks to the radio, that starts and stops other applications, that runs an event scheduler, so we can schedule, you know, when to start and stop things like slow scan television. We can, you know, run things like rolling the log files or ending a whole orbit data collection and starting a new file for that and so forth. So we can put all sorts of things in the schedule. We use Direwolf as the modem. That gets started and stopped by IRS control. And the files that we see visible from the ground, we manage through through the PaxSat protocol. So we have a version of PaxSat called HiPaxSat that again IRS control stops and starts. And there's an SSTV processor. But we can have other programs if we wanted to that we can start and stop as well. So the potential concept of operations, the main driving principle is that everything that the D710 does today, it has to continue doing. So the astronauts at any time can pick up the microphone and start talking on the radio to people on the ground. Right? So it's important that we continue that, we allow them to do that. They can go and start a school contact, go into the mode to do that. They have an emergency communications facility where they have a whole bunch of frequencies, many of them outside of the amateur bands. All of that's got to be supported. So the Raspberry Pi sits alongside and can sort of control the radio in the same way that you can as a human, but it doesn't replace or stop any of the things that they can do. And there's a couple of caveats to that. You're probably already thinking about that. That I'll cover in a second about how you stop it interfering with them and then interfering with it. Okay, so we'll come to that in a second. We send commands from the ground. We protect them with an HMAC shard 256 checksum, pretty much exactly the same way that we do with other AMSAT spacecraft. We use a secret key for that, obviously. When we're testing here on the ground, the key is publicly available. We can upload data and files for digital transmission or to change the configuration. We can upload the schedule, for example, so that you've got for your scheduled events. From a data transport layer, you can basically support any mode that the Direwolf TNC supports, but primarily we're using 9600 bits per second packet radio, and we're using FX25 forward error correction. We can also do everything at 1200 bits per second. And you might say, Chris, there's better protocols to use for space communication. Why are you using that? But we're very tied to the fact that we have an FM radio on the space station. That's our transport layer. And by the way, Kenwood optimized that radio for packet radio. Right? It's like it was their flagship packet radio product. And also we have 10 or 20 watts of power, and so it works very well as a packet radio channel to and from the space station. Following sort of the way, if you're familiar with how PACSATs worked, you can queue up commands in advance, and that'll all get sort of automatically done as the ISS comes over your horizon. I haven't done that with every new command that I've implemented so far, but that's the principle. Principle is it's very file-based. You apply commands to files, and when the ISS comes over, it then executes those commands for you. Talked about schedule, and we can patch the software after launch, or at least I got a little star there, not fully implemented. Right now, you can upload new versions that effectively it uses instead of the software. So that is effectively patching the software. To fully patch it, we would have to undo the overlay file system, put the files in place, reading the overlay file system, and so forth. And you've got to offset the risks of doing that versus whether or not you want to just say, use this other binary instead that I've uploaded with this other script. So one question is, how do the crew use the radio without the Pi suddenly deciding now is the time to start the slow scan television event? And they thought they were going to talk on the radio. So the simple way to do that is we gave them a button to press. They will take control. Okay, so they press that button, and the green LED that says the Raspberry Pi is in control goes out, and these two yellow LEDs light up saying that the crew are in control. And at that point, the Raspberry Pi won't make any changes to the radio. The crew can, do a school contact, they can talk on the radio, they can change the modes, they can do whatever they like at that point. And when they're finished, they just long press the button and the Pi takes control back. And if you missed a scheduled event while it was doing that, it runs a scheduled event then instead and starts it. If they left the radio in some crazy configuration, puts it back into the configuration that it was before they pressed that button. And if the crew completely forgets and goes away, the whole thing is running on a timer. So that follows an hour. After an hour, Pi takes control back over and puts it back into the mode that it was in before they did that. So hopefully that makes it very simple for them to do. One of the principles was, because we have a lot of procedures and we train astronauts how to use the radio, the only modification to that procedure is press this button and then do the procedure. Otherwise, everything else remains exactly the same. If they do a school contact, they'll still manually take it out of the crossband repeater mode, go into PM1, put it on the right frequency, do the school contact, and so forth. So hopefully that makes it easy. The only other thing we thought about is if we leave it in some random mode without pressing this button, and now you can't talk to it from the ground, how do you recover from that? And to a certain extent, we have that problem today on the station. If they were to take it out of crossband repeater mode and leave it out of that, right? So we sort of have that problem today. But so what we do is we just make sure you have a scheduled event every day. 4 o'clock in the morning, put it into crossband repeater mode on the known channels. So eventually it just fixes itself a little that evening. So hopefully that makes it easy. And in an emergency situation, unplug the Pi, right? And use the radios as part of your emergency. So we have a file system. Obviously, the Pi has a big file system, but we have a window on that using the PACSAT protocols where we can upload files, log files can be stored there, and we can do that. And I'll demonstrate some of that, so I won't dwell too much on that. The student on-orbit sensor system, we have a prototype for that with some sensors so we get telemetry down if we're in that mode, and we can use that to forward to the students and so forth. We're going to introduce some quite nice new sensors to sense things like the radiation around it was showing, oxygen levels and so forth on the station. So lots of challenges putting this together. I'll just cover some of them briefly. I talked about coping with the sudden loss of power with a Pi. That's always a fun thing. It's a pretty mild radiation environment because crew live there. So we don't really have the same challenges we have going through the radiation belts for some of our small sats and so forth. But we certainly thought about it. We don't want bit flips to ruin everything that we're doing and so forth. So there's some thought about that, but it's not really the problem that we have with most of our satellites because it's a crew habitable environment. Heat management in microgravity, while not as difficult on a CubeSat in vacuum is still a problem. You need fans to move it around. But to be honest, our biggest issue is noise rather than heat, because you could solve that with fans whirring very noisily, but we are already right at our noise limits with our equipment. So it's okay, do that, but don't introduce any new noise. So luckily, we're not doing very much on the Pi. I mean, we're literally running dial is the most we're doing. As I said, it draws about 900 milliamps, right? Pis can draw 2 amps and really go crazy with their processing. So we're not generating too much heat luckily. NASA's really strict on electromagnetic interference, as Randy demonstrated, so we've got to meet all of that. And it'll be in a nice metal case. Safety, Randy talked about that too. And ergonomics, I mean, it sounds crazy, but you have to be able to manipulate it, press the button with microgravity, and it shouldn't be too small. And there's all, NASA's got this sort of endless list of things that you have to meet. So Randy said there would be a case that goes underneath the multi-voltage power supply, which is the box over there with the green LEDs underneath the radio. It'll look something like this. This is from Hunter. There'll be the 2 drawers. Randy kind of covered that, so I won't go into that too much. But it'll go in the left-hand drawer, and it'll have the computer and the student on-orbit sensor system in there together. All right, I'm going to try and do a demo. I'm going to use, I've got a FT817 here as the ground station. And it's running, it's going to run at 9600 bits per second. For half duplex, because I only bought 1 radio. But that'll be fine. It just runs a slightly slower, but it runs fine, half duplex. So give me 1 second while I try and just get this. So. Oh, there's a packet.
Here's something.
Okay, so right now, I mean, luckily we can see the space station over here, which we would probably be able to do. And it's in crossband repeater mode, which is sort of the default mode that it sits in. And I don't add any additional packets into that to interfere with people using the crossband repeater. We could, but I don't. So it just sort of sits there doing that. So what we'll do is we will send a command, take it out of crossband repeater mode. And it's worth noting, by the way, I don't know if anybody else has a Kenwood D710 knows the radio. But Kenwood has a CAD interface, but it's only for flashing the radio. They don't provide any details on CAD commands. As far as they're concerned, there are no CAD commands. Or they must have decided they implemented, but they weren't going to support it or something. So there's no published CAD commands. So people online have worked out what some of the CAD commands are. And there's a GitHub with some of those CAD commands. But the one thing that's not officially supported at all in the CAD commands is how you get it in and out of crossband repeater mode. Okay? And I won't go into the details of how I worked it out, because Kenwood don't necessarily want me to share that. But I did work out how to get it in and out of crossband repeater mode. So we'll see if we can command it into TLM mode, and if it comes out of crossband repeater mode.
Oh, yeah.
And we get a few packets now because we're in this telemetry mode. So we get a status packet that says we're in TLM, that we're on PM0, which is the program mode of the radio. You can have like 5 or 6 complete configurations of the radio. So this is a complete configuration, 0. And we're on channels 201 and 202. The repeater is off. And T0 means this won't run timeout. You didn't give it a timeout value. And it sends us the time, which luckily I set this morning. This radio's battery has died. I'm pretty sure, because last time I set the time on this radio, it hasn't remembered it. And we've got a telemetry frame. So if we go and look at the telemetry, we can see that we've got a telemetry frame. It's 30, whatever it is, 6 degrees or so in the Pi. We get some data from the sensors, temperature, humidity, pressure, accelerometer, gyroscope, phantom, all the normal things you get on those little hobby boards. The last time we shut it down with a command, it's, we've got a number of resets, all the sort of normal things. We can see how often we're collecting whole orbit data, how often we're collecting different types of telemetry, on log level is, like having radio channels are configured, all those different things. So that eventually will include all the student sensors and will feed into the sensor system. So what I'm going to do is I'm going to try and put it into APRS mode. Just frequency just going on my ground station radio. So 85, right? I think it went into, it's in the APRS mode, but I missed the packet because I put it on my frequency.
It changed something. It looked like it changed the way.
Screen 303. Yeah, it's definitely changed, but it doesn't send an APRS packet very often. It does send one right at the start, and it's the one
APRS 1200.
the one right at the start. So because of the way they got their radio set up, it had its own TNC, and the way that the digipeater works, it uses the TNC inside the radio. So I don't change any of that configuration. So I put it into digipeater mode, and it'll send 1200 bits per second status packets occasionally, and it will forward people's 1200 bits per second packets just as it does today. Meanwhile, I can send 9600 bits per second status packets that this system is receiving, and I can send commands at 9600 bits per second. And it supports both. It's got this idea of an internal and an external TNC. So we don't change anything on the radio. It supports all the modes that it supports today. And you can see now we've got a status mode, APRS, we're in PM3 right here, and a time packet. And we can configure it in this mode if we wanted to send telemetry or not as well, how often we wanted to send telemetry, all those different types of things. So, second while I just change command frequency on. Command it out of this and into file system mode. Okay, so we're in file system mode. So that basically starts the AMSAT file server on the Raspberry Pi. So we've got a status message saying we're in file system mode back in PM0 on channels 201 and 202. Hang on a second. I'm on the wrong. I didn't choose all the different channels and frequencies. They would show them one by ARIS. But you have to know on the ground, of course, what frequency the radio is on, which is why it transmits the channel steps on. So we get a whole bunch of files that are sitting in the AMSAT file system. And for those of you who know the AMSAT protocols, you can tell if I just automatically downloaded the file that I have an equation set up to download files that are sent to TXT. And that's the schedule. So I had previously asked it to list the schedule form that it's got currently. So if we look at that, we find that there's a very cron-like schedule that you can do where you can put, you know, the time and the day of the week, whatever you want, cron-like, and then you can give it a command. It can be any of the commands you set up from the ground with its parameters, and it will run that at that scheduled time. And if you want to change that, change this file and re-upload it. And effectively, you're uploading a shadow copy of the file that it will use in preference to the default file, which is on the read-only SD drive. So what else do we have? We have log files. We have whole orbit data files. I won't download them because they're sort of 47K or so. We have whole orbit data files. And we have slow scan television images that I've uploaded previously. We can see that I've uploaded specific configuration for this to override the default configuration for the demo. I did that because I wanted to change actually the cool down period for this, for the SSTV, so it didn't wait 2 minutes between images. It's part of the demo. So we can change the config, re-upload the config, and it changes settings that we've got. So if I want to upload a new message, which is the sort of thing you would normally do in advance, not while the spacecraft is up, but normally in advance, you might send something, you might send it to Aris. I'll type one-handed. Make it a JPEG. Upload picture of Tin Peak. Title. So just it processes that. Click send. That was done uploading. So it logs in, you see EC2CZ logged into NA1 SS. And for those of you who are very observant, if you know the PAXAT protocol, you'll notice it doesn't say open ABCD, it says command ABCD. So I modified the FTL0 protocols for uploading files so that you can have a mode where only command stations can upload files. So the default is when it says open, anybody is then able to log in and upload files. When it says command, one, my ground station won't recognize that unless you're a command station as being open. What's more, after you log in, the way the FTL0 protocol works is you have to send a Go packet to say that you want to upload the file. And you have to send the secret key and the checksum with that packet if it's in this mode. Otherwise, it rejects your connection. And you upload all the packets which don't need the secret key because that would really lengthen the length of time it takes to upload the file. But at the end, we're pretty much there because we're at 90%. The final packet is a data end packet, which in the default protocol doesn't have any length. It's just like a 0 length packet, data end. But I include the checksums from a header and the secret key again, wrapping all of that. So that gives some integrity. If somebody messed with your upload or something, it would reject the whole file. And you know that means only a command station can upload files when it's in that mode. We can command it into the mode where anybody can upload files. But given we're sitting on a NASA space station, there's situations where we probably want to control that. So we have that feature. Now these files then are sitting here, and you might notice this folder column, which again, if you're familiar with the PAXATs, you wouldn't have seen before. And it says that things are in certain folders, like the binary directory, configuration directory. So we can install these files into certain folders on the pod. And again, you wouldn't normally do this during the pass. You would schedule this sort of stuff in advance. What I'm going to do, let's just ask for the directory. You see the tin slide is there, slide 34. So I am going to send a command, put that slide, install that file, and install file 34. And I'm going to install it in SSTVQ1. Okay. So I get an OK response back. And if we want, we could put slides, what we've got, file 12 and 10. Those as well, so slide file 12 into that queue as well. And if I ask for the directory again, it won't let me get the directory because it wants me to wait until PB is available. Which again, if you know the PAXAT programs, you never have that one. That's just to stop people logging this up. Okay, we see both of those files are now in SSTV Q1. So we have, I think, 9 SSTV queues, 9 data directories. So we can organize things into certain folders for, you know, scheduled events for different things that we are doing. And if you put things in the binary directory, we can execute them. Like this thing in the directory here called ls directories is a bash script, so we can run that and that'll list some directories. I was using that just to make sure the demo is configured correctly. I got a script to reset the demo, for example, that just removes all the different files that we didn't want in the demo. So I'm going to stop a file system. And I'm going to run SSTV. Just have to bring it back into mode briefly. We're in TLM mode. So it doesn't transmit in a minute. So in SSTV mode, I can set up the mode. So for each queue, I can decide what mode are the files in there. Normally they will be PD120. That's the default station, for things from the space station. But I'm going to make them Robot 36 because that transmits much faster for my demonstration here. So I've sent that command. The SSTV subsystem uses a Python script that Kieran found that literally turns these files into audio files. It just stores the audio files ready to transmit. So it's a very simple way. And once those files are generated, you just run the event in a loop over and over and so forth. It just plays them out through the sound card interface. So I'm going to do SSTV loop. I'm going to get it to loop for 10 minutes or so. And it's going to be on channel 300. So that is 800, right? This is where the SSTV comes. Still, I'll try and get it right. And let's just make sure that we can see. Chance of being the right sound card.
Default.
Default sound card, yeah. Yeah. I've done this so many times that we have the wrong sound card. So Windows 11 just determines randomly what sound card because I've decided. There's no logic to it. Okay, so we sent that. It's
nice.
So then we're receiving the image that we uploaded of 10. But if we put 10 images in that queue and send them in a loop, we get different queues. We can schedule that however we want to. So that's most of what I wanted to cover. I mean, there's a crew interface, but if people want to see how that works, I can show them up here. We didn't bring a monitor to show the ham TV output, but anything we put in one of these queues, we can also have go to the ham TV. So we got one of these queues and test cards in it. Test card, send that to the ham TV, and so forth. And we have all the sorts of commands that you can expect from resetting things and making things work again. So I'll stop there. I'll take any questions that people have.
So does the crew have a monitor where they can actually see files that have been uploaded on station?
I mean, they don't. They would need a different radio.
What we're going to do is we're going to put it on the tray. There's going to be an OLED.
Okay.
So we haven't planned for it up front, but eventually we'll probably do that. We'll send the pictures across it. So that's the idea. Good question.
I probably missed this at the beginning. So the crossband repeater is running. How do you send the command? You actually send it to the crossband repeater, and your Pi is also listening in?
Yeah, it's just listening to the crossband repeater as well.
Oh, okay. So beginning command gets repeated probably before it's switching.
I don't think it actually repeats. I don't know if it repeats the command because of the way that works, but because it goes in through the TNC sort of input. But it may do. But there's not necessarily any harm in that because you can't replay the command.
Yeah.
So yeah. And it's fair also to ask, but Chris, the repeater is so busy you'll never get those commands in, right? Which is why you have a schedule to change it out of crossband repeater into say telemetry mode or something. And we can also, change the input frequency so that you don't know what the command frequency is. So yeah, so we might, for example, have a policy that we're never going to set the command when it's in crossband at the moment.
So my vision basically is that we use the L band. The radio does receive on L band. Carrier's tested that, and I think did you test it too?
I don't know that my non-modified radio.
Oh, I see.
That's about to do.
Yeah, but the future will be probably using. I want to see using the L band capabilities in the land right away. Right now, we've got 2 antennas up there. One of them we're not using for sure, and the other one's going to be used for the LS is going to be used for the MTV. But we're looking at that to use those antennas basically. So, I solve that problem.
But well, it wouldn't be L band at the same time. You have to tell it to listen on L band because there's only one radio. So
We'll soon have SDRs up there. So.
But yeah, but this solution was very much designed to what can you do with the existing radio?
Sure.
If you plug a Raspberry Pi into it, that was sort of the exact question. So
That's also a technical capability, but there's also the practical capability of what NASA will allow.
any other questions?
So how many images could you upload on a pass if you were uploading pics?
The images
For
take
download later.
Yeah, so the images, these other images are kind of full size PD 120 images, and they're like 54K, 82K, 60K, 46K.
So at 9600,
9600. So they take about 2 minutes to upload, something like that. But
you have the Vantage.
that's in a perfect pass. So if you're missing half the packets, you're going to get one up in pass. Yeah, that sort of thing.
Full duplex and command.
Yeah, full duplex. Yeah.
That
So,
helps.
I mean, if you've got a perfect pass, you could get 3 or 4 of them loaded.
Yeah.
Loaded up in
So we have a
in a-
cooldown
in a
period
box.
too, the radio too. So we got to remember that. So.
Yeah. But it's, but in a patch, you can shoot a new one up, which is,
Absolutely, you
Yeah.
definitely get one up now
Yeah.
in a pass because they're not that big. It's my computer's telling me that it's not that enough. But yeah, so they're not too big. I mean, the trick with these images is PD 120 images only like whatever it is, 640 by 480. It's a relatively small image, and if you make sure you strip out all of the metadata and everything that you don't need in that image, the color table and so forth, then they end up to be about between 40 and 80K in that sort of size. Any other questions?
just a remark, thanks for the work on this. It's deceptively important or something, I want to say. Right, to be able to have Earth control. of
Very important
that.
to us, actually.
Yeah, that's what I mean. Earth control of the radio, really for the first time.
And we actually, so there's probably problems with the radio interface with the astronauts every 3 months at least, right? And then the radio has to get reset. Kenneth has to spend lots of time working with it, get the radio
Talking
back to
them
the
through button presses, right?
So this is gonna hopefully avoid that is our goal.
Yeah.
And so the buttons that was shown before, we're gonna have those on the tray, on the front of the tray. So that's what those are gonna be, along with the OLED. And in the back end, we'll probably have the RF connectors coming out the back and the tray slides in too. And we have SDRs and so forth. So.
That's cool. Good work.
All right, thanks everybody.
All right. Thank you, Chris. Next up, we've got Graham Sherwold getting ready to receive ham TV from the ISS. Take us a minute or two to swap equipment here, and then we'll get started.
Shut down. It takes about 30 seconds.
No, but I'm going on my best. We're gonna take this fourth period. Oh, sorry. Stay. No, that's a great job. No, it does by itself. I have some four areas. Probably history of pastors, fixing into the project side. And it stays charged no matter where you're on. Disconnecting. And what I was thinking about is putting a guy on his corner. The pastor would have got north of the center or so. And it said this going down on the other side of the passage.
So this is.
Yeah, like a boy.
Thank you for the presentation.
Yeah. Big question on this is. Yeah, actually, I think there'll be.
It's different.
Yeah.
Yes,
Yeah, I look pretty good. And that's new training. Yeah. You go out and that's what. Contact. I was,
Watch what come out here.
Okay, good morning, ladies and gentlemen. Yeah.
All right, guys, we're ready to go.
Well, it's been a fascinating morning so far. I've certainly learned a lot. And we've heard a lot about what's going on up there, or what will be going on up there on the ISS. This short session is to give you some guidance as to what you need to do on the ground to receive ham TV when we get it. If, but when. So these notes have actually been prepared by Noel Matthews, GTZ, who is currently, I think, the on-sec of BATC, but is certainly one of the drivers behind the British Amateur Television Club, which has the word British in its title, but I think now a majority of members are actually outside the UK. So it's a fairly international team and an international group. So we know a lot about, in this audience, we know a lot about what goes on the ISS, what's up there. These slides were actually prepared for a more general audience. And Noel was actually presenting about 2 hours ago from the UK at a BATC. What?
Don't do it. Don't do it.
I'm not going to do it.
Cancel.
Right. So, wow. Where that came from. Anyway, so some of the slides don't assume as much knowledge as you've obviously got. But just a reminder about the ham TV or the LS band antenna. That's the one that's shown there. That's on the outside of Columbus. There are 2 of them.
on the outside of the Columbus module. They've been up there now. Columbus was launched in 2006, I think, something like that. So they've been up there a while. Apparently they don't look as pristine as they did when this photograph was taken. They've got a glossy yellow color or golden color due to erosion of atomic oxygen, apparently. So as it says there, the ISS is a complicated structure, and there are lots of things sticking down and sticking out. And modules arrive, and capsules arrive, and get in the way of the RF. Flies slightly nose down, and we find certainly on 2 meters doing ARIS contacts that the signals in the first half are often not quite as good as the signals after TCA, and certainly the polarization changes dramatically. We always have a man manually switching between left-hand, right-hand, vertical and horizontal, and sometimes the signals change polarization in a split second. We believe that's because the signals are being reflected off other parts of the structure. Anyway, it's nothing to do with HAM-TV. So HAM-TV, originally installed in 2013, commissioned in 2014, and we were able very happily to be able to use it for the Tim Peake ARIS contacts in his Principia mission. And I think he had 10 ARIS contacts, and something like 7, I think, had HAM-TV as well. So that was really good. And you know the history and whatever. Anyway, so HAM-TV, the specs as originally supplied. We've got options of frequencies, but they selected 2395 as being the best frequency, and I don't think that's going to change. The nominal TS output power is 10 watts, but we have some considerable cable losses and now a filter loss. And I think the 6 dB there is probably vaguely optimistic, or would you support, Randy, would you support 6 dB cable loss as a number?
Yeah, that's about right.
About right.
Yeah,
okay.
you're right.
So something like 2 watts at the antenna, and nominally an 8 dB antenna gain. So what is certain actually, the signal will not be as strong as it was before, because we've got a filter and a longer piece of coax. But it's still going to be good enough, we believe. So it's a right-hand circular patch antenna. We're fixed on DVB-S, not DVB-S2, 2 mega symbols with FEC, MPEG-2 video, and as we've already heard this morning, it's the kit has to have NTSC video input somehow. So we sent back some time ago, and we've arrived back here in 2023 last year, and then we've heard this conversation stuff about the external bandpass filter, and it was taken back up to the ISS 6 months ago.
April 22nd.
I've got March the 21st, so your mileage may vary. Don't shoot the messenger. Anyway, so again, we've heard that it is it's there, and we've got issues trying to get it commissioned. The current estimate is TBD. Space schedules we've already heard as well. Space schedules only ever move to the right, and we're going to have some fun soon. So receiving HAM-TV on the ground. This is the meat, I suppose. Again, it's fairly obvious. Starting at the right-hand end, there's a dish. We'll talk more about the dish. There's a rotator. The key, as always, in receiving signals, whether it's on this scary microwave frequency dish or any other frequency, a good low noise amplifier as near to the antenna as you could get. Probably, depending on your local environment, probably a filter before the preamp. Maybe if your environment is not too noisy and not too crud, you can get away with a filter after the first preamp. It's certainly the lowest possible noise level. Good quality coax, of course, and we need quite a big signal to reach your mini tuner. A mini tuner or a pico tuner
is it still around?
I'll get it later.
Is a magic box, which takes a signal at 2395 directly. Thank you. LNB input. Well, sorry, input, ALB, not LNB. I'm thinking of QO100 again, I'm sorry. And a USB output to go to your computer and 12 volts, that's all it is. It might have a LED on it to say power's on. Some do, some don't. Mini tuner, this magic box is a bit of kit from BATC. I'm not particularly, well, I am promoting BATC, so that's where you need to go to get one of those. Now, the output from the mini tuner can go to a number of different computers, shall we say. There's also an alternative with using a satellite set-top boxes, some. Originally, it wasn't possible to use set-top boxes because the transport stream coming from the ham TV was not quite in alignment with all the standards. The service indicator stream wasn't, data wasn't correct or something beyond my pay grade. But now that's been corrected, so it may be possible, but that's a big unknown. And also, many of the set-top boxes don't go that slow, 2 megasymbols. So there's a sort of dotted line there, because that is still a thing on so coming back to the beginning, in terms of receiving, what do you need for our antennas? Well, the photograph there is there's a big dish at Goonhilly, we've heard Goonhilly mentioned before. That's the very first dish that they had there, GHY1, which was used for Telstar reception. Not many in the room that would have been around then. And there's me sitting in a sort of deck chair with a G3RUH dish, which was produced years ago, was designed for 2.4, designed, I suppose, for AO40. And I was getting signals on that little dish down at Goonhilly, much to the annoyance of the Goonhilly people who got a 4-meter dish just out of shot. And they couldn't get it aligned properly. So when the ISS was over there, their dish was pointing over there. They got very angry with me. They got it right for the next pass. So as it says, the 1.2 meter dish is probably the optimum. Smaller dishes are easier to track, but you won't be able to receive the signal, decode the signal at a strong enough level until you've got quite a lot of elevation. Reference there to the potty. You heard me talk about the potty yesterday, and potty of the year. That's again a QO100 affectation. But any patch, sorry, the feed for the dish should be either a patch or it can be a helix designed for 2.4 gigs. And of course, it's got to be a left-hand patch or left-hand helix feeding the dish, fed from the dish, which will reverse the polarization for you. The background to that story is the very first Telstar contacts were transmitted from somewhere here in the States. I don't know quite where. I can't remember. And thank you. And were well received by the French with a big horn. And at the Goonhilly, they were scrabbling around with the signal right in the noise and the frame rolling. And the story goes, I don't know how true it is, was that they'd actually got the polarization back to front because someone had forgotten that the polarization got reversed when, etc. I'm not sure how true, but it's a lovely story. Then the engineers rushed up between the passes and put another feed up the other way around. And then the next pass, the signals were as good as the French. So certainly the very first, there's still video or film of the very first reception. So talking in detail of the preamp and the filter again, that sort of shows how close we are to the Wi-Fi and therefore how necessary the filters are. It's only 5 megs below the Wi-Fi band, good filtering necessary. A line amplifier needed in the shack because the mini tuner, or this is called a pico tuner because it's got a slightly different output, needs at least a meg 70 signal. Standard satellite receivers only receive up to around 2.50. So if you're determined to use something like that, then you're going to have it create a down converter to get to 2395. So the receive hardware that I've just been talking about, I think I've said all this. So the mini tuner, Pico tuner is the way to go. There are alternatives within the BATC supply chain options. I won't try and go into detail, but all the other ones are actually based on Raspberry Pis, which we've heard a lot about. A Raspberry Pi, a ports down receiver, the ports down configuration is a Raspberry Pi with a 7-inch touch screen, and so the receive system can be simply a dish, a mini tuner, a Raspberry Pi running ports down. As simple as that. Minitune software is also available. That's the French one. An Open Tuner is some more software if you want to run on PCs. Open Tuner comes from South Africa and it is working well. And I'm sorry, Lou, that there is no Mac option at the moment. But if you'd like to work on one, it would be very helpful. So tracking the ISS, it's not like your 100. Stop making these references to I know I'm upsetting you. I do it. So the maximum pass length is something like 11 minutes. The 1.2 meter dish that I've sort of given as a reference dish is got a beam width of about 6 degrees. So you need to track the ISS quite accurately. Needs to be on something like an XY rotator. Our experience shows that Yaesu rotators are, for this size dish, good enough. And again, the standard, I don't know, PST rotators, SAT PC32 things.
Size of that dish?
Well, that's probably a 1.2 meter dish. SAT PC32 will what we use already. Nothing for us, nothing unusual. So, question has been raised about how do you test your system before Ham TV actually starts. The best way, if you've got a ports down, that's the Raspberry Pi. Part of the ports down suite of programs that it runs, it's not only as a receiver, but it will also check the noise level and a whole load of parameters, system gain, preamp outlet, system noise, etc. And you can simply just point it at the sun and use the noise power measurement in ports down, and you should see something like 2 dB of sun noise at 2.4 gigs. And then the other idea, of course, is to make sure you're tracking the sun through the day. It doesn't quite represent the speed of the ISS, but you set it up first thing in the morning, and it's still pointing in the right direction. In the evening, you know you're doing something right. You can also, of course, test that if you have somebody operating on 13 cents DATV, you can use them as a test source. Or again, if you've got 2 ports down, you can set one up as a transmitter and one as a receiver if you wish to. The ports down. Sounds like I'm talking Raspberry Pis, but they're not a lot of money. For high-tech equipment, which is what we're doing, it's not too difficult. So then, once you're confident, then all we've got to do is sit back and wait for it to be switched on. How will we know? Well, the famous AMSAT status page will no doubt give us the guide there. Or one of the other questions that Lou raised with me yesterday is, what does he do when he's got the signals coming in? What does he do with them? And there will be, and there was previously, a station emerging network transport stream where you upload the pictures you're getting, the sound you're getting, to a central warehouse, which then enables everybody to watch your signals as well. We've actually got it already running with a receiver at Green Hilly,
just sitting there waiting for the signals to arrive. And the dish actually already automatically tracks. No, it's not that one. Sorry. That's GHY6 that Randy was talking about Phil using during the 40th anniversary. That was the dish he used. If you look very carefully, our dish is that teeny weeny little one down there, which is again already tracking the ISS actually. I grabbed this picture a few minutes ago and spotted that it was actually on the move, because normally it just sits horizontally going to the zenith, but I managed to pick a time when it was pointing towards the space station. So we're ready. That's the point. And as I say, that's supposed to be moving, but it's not. I'm sorry. It's ready and live and up and running. You can go to that website. So for more information, the BACC have a wiki page, which really this presentation is just a reduced copy of, but so lots of details and lots of links there for more information where to go for programs, software, code, etc. So wiki BATC Ham TV will get you there. Going the wrong way, sorry. Wrong button. Now, just to finish, there's a link here which may or may not work, but the basis that one picture is worth 1,000 words. Could you just hold that by? Oh, sure. No, no.
Just hit the.
Yeah. No.
Sounds just.
Oh, is the speaker come off here?
Click on your speaker.
Yeah.
Bravo 1 Sierra Sierra. This is GB2 CNS Golf Bravo 2 Charlie November Sierra. Listening and standing by for scheduled contact with the International Space Station.
Hello, Golf Bravo 2 Charlie November Sierra. This is Golf Bravo 1 Sierra Sierra. I read you by.
Doesn't want to go full screen. Don't ask me why.
Hi Tim, this is Tim, M6HDJ.
He was very nervous.
Are you ready for your first question? Over.
Great to be talking to you, Norwich, and yes, I'm ready for my first question. Over.
Hi, this is Maddie. What do you do if you cut yourself really badly in space? Over.
Eyes up there, so we do have to be careful. If we get a really bad cut, then we could actually give ourselves some local anaesthetic and stitch it up with the help of some doctors back in ground control if we need to. Over.
Hi, this is Austin. Are there any protocols or guidance in place if George Clooney comes knocking on the front door as he did in the film Gravity? Over.
Hi, Austin. Well, as far as I'm aware, we're the only 6 human beings in space up here, so if anybody comes knocking on our hatch, I'm not opening it. Over.
Kieran's got a smile.
Tim, it's Kieran M0XTD. We have you on Ham TV. Give us a wave. Here's your next question.
Hi, this is Sophie. What experiment would you like to add to your mission based on the experiences you have had? Over.
Hi, Sophie. I would like to see us doing more of the medical research, investigating some more vaccines and looking into new drug methods as well. I think that's some of the most exciting research we're doing up here. Over.
Hi, this is Max. In what ways does the lack of natural sunlight and fresh air affect you on the ISS? Over.
Hi, Max. I love opening the windows in the cupola when I'm in Node 3 or in the Japanese module. I love the sunshine coming through the windows, and it does make a difference. It does kind of brighten up your day and make you feel better. And you just get used to the fact that we see so many day and night cycles. Over.
Hi, this is Charlotte. How do you get changed in space when your clothes go everywhere? Over.
Hi, Charlotte. They do go everywhere. We have to use bungees. We bungee our clothes down so they don't float off and you don't lose them. Over.
Hi, this is Eden. One of the experiments you are conducting in space is to measure fluid shifts in the body. In what way does this help us back on Earth? Over.
Hi, Eden. That's a great question. Fluid shift really kicks off the whole process of the changes to our body. It's because of the fluid shift we get greater pressure in our head and we start to lose bone density as well. So that triggers all the changes, and it's by changing things in our body that we can learn about our body and we can investigate these things. Over.
This is Thomas. With the basic design of current spacecraft dating back decades, where do you think the next leap forward in spacecraft technology will occur? Over.
Hi, Thomas. Yes, I mean, we're playing with the basic rules of physics and gravity here and laws of motion. So I think that we're going to see big changes to our spacecraft in terms of our transit to Mars and transit to Moon. But in terms of getting to low Earth orbit, I don't think we're going to see many big changes that we have in current spacecraft design. Over.
Hi, this is Emily. How different was the training compared to the experience of actually launching into space? Over.
I believe the training was so good that it really prepared us for launching into space, and there are very few differences between what we were training for on ground and how we live and work up here in space. Over.
Hi, this is Millie. With improving technology on Earth, are there experiments that you are currently carrying out in space that could one day be repeated on Earth? Over.
Yes, there are loads of experiments up here that we're doing that could be repeated on Earth. I think that it's going to be a long time before we manage to sort of counter gravity for a long period of time on Earth. So we use parabolic flights and drop towers. But the benefit of being up here in low Earth orbit is, of course, we have microgravity continuously. So we can do those experiments for a very long time. But we do repeat the experiments back on Earth, of course, to see the changes, to see what's difference between space and Earth. Over.
Hi, this is Erin. Which materials being developed with the electromagnetic levitator will have the largest impact on the development of greener living? Over.
Hi, Erin. Well, I think the metal alloys are the one area of research that are going to have the big impact on greener living, because that will affect how our engines are designed, and in particular our commercial aircraft turbine blades and turbine engines, for example, which will cut down fuel production and cut down fuel usage and have a good impact in aviation. Over.
Hi, this is Maddie asking Lola's question. Since being in space, what has been your most amusing dream? Over.
Hi, Maddie. Do you know, I haven't dreamt much up here in space. And when I do, I dream of Earth. I haven't yet dreamt of being in space. And I think it's because we sleep quite heavily up here, actually. I sleep quite well here in space. Over.
Hi, this is Austin asking Livy's question. If everyone in Britain turned their lights on and off at the same time, would you see it from space? Over.
Hi, Austin. Yes, you definitely would see it. You know, we would see a small village if you turned your lights on and off. It's amazing that the lights really stand out very well from space. And certainly a major city turning their lights on and off would stand out very clearly. Over.
Hi, this is Sophie asking Ella's question. Which part of the Earth do you like orbiting over the most and why? Over.
Hi, Sophie. I love orbiting over Africa. It just looks beautiful from space. It's like flying over a canvas of art. And also northern Canada is beautiful, especially right now with all the ice and even the sea is frozen up there. Over.
Hi, this is Max asking Amy's question. With sunrise and sunset occurring 16 times a day on board the ISS, does it have any noticeable effect on your body clock? Over.
Hi, Max, that's a great question. Yes, it does. You know, if I'm looking in the cupola late at night when it's bright sunshine, it does take me a while to get to sleep. So I try not to do that. You have to try and trick your body that it's nighttime when it's time to go to sleep. Over.
Hi, this is Charlotte asking Mimi's question. How does being in space make you relate to your place in the universe? Over.
Hi, Charlotte. That's a great question. You know, I mean, being up in space gives a different perspective, and it makes you realize how vast the solar system is, how vast the universe is, and also it makes you realize that our planet, you know, it has no borders. It's got massive weather systems that affect all continents, and so it does give you that perspective of the planet as a whole. Over.
Hi, this is Eden asking Bruno's question. Is there a song or a piece of art that you think reproduces the feeling of being in zero gravity? If so, which one? Over.
Hi, Eden. Well, there's nothing particular comes to mind, but you know some of those pictures where things look different upside down. For example, it might be a beautiful woman one way up and an old haggard woman the other way up. I think that's great because it makes you realize in space, of course, we have a different perspective depending on which way up we are. Over.
GB2CNS returning. That was fantastic, thank you. Everyone here would like to say a big thank you. This is GB2CNS handing back to GB1SS for the final. GB2CNS, off and clear.
It's been wonderful talking to everybody in Norwich this afternoon. Have a great day and thank you for those brilliant questions. Goodbye from the International Space Station. Out.
Nice. Yeah, there you go. I played that because I just wanted to remind us all how much difference it makes to the contacts. But Tim was very good at it, so we're very grateful to him for doing all his QSOs. The one jokey bit is that I'm not sure whether it was the Goulet receiver or a receiver in Ireland, but a receiver to the west of Europe was receiving some signals from the ISS on hand TV randomly. It was during the commissioning, and I actually can't now remember which astronaut it was, but the camera was sort of more down here, and he was busy adjusting his dress. It was very good. So a note to those who communicate with the astronauts, a reminder that ham TV is TV, and if they switch it on, do their whatever they want to do and sort themselves out and do all that before they walk in front of the camera, please. There is a recording of it, but I'm not authorized to show it. So that's just a quick infill before lunch, and I'm now 5 minutes late, so I won't carry on, but thank you very much all.
Thank you very much, Graham. As he said, we're breaking for lunch now, and we will see you back at 1 o'clock.
Yay.
Yep. That's fine.
That was great.
Oh,
That's a classic.
Nice. Great job, Cross.
I have a D7.
It quit. I've had to do my cloud development.
Yeah. And there isn't much terrestrial DATV over here in the States.
Well, not about that.
Yeah.
About in LA.
Which port that the cat's command goes to the controller or to the radio base? Okay. So you're okay. So the serial port coming out of that.
Trying to set up that's gonna work for 2.4 gigs.
And by the way, you need replacement batteries.
What's the things that they do? We know that.
The problem is change mine out.
What they call it, find a space station.
Oh, okay. I thought you were saying your one was.
Well, this is
Okay.
yeah, this one is so they can change that one. It's all space station.
Well, I'm sure there's so many years. Yeah.
I'm worried that it's gonna start interfering, so. Yeah.
This is the US.
Yeah.
Initially.
It's a, well, there's
That would be.
I have to, well, I don't know. They have maps, I think, from all over the world.
There is another one.
What was the first thing?
Yeah. I've got the A.
Yeah, it could be a problem, but most of the time, the road's gonna be looking up in the sky. It's built.
So you think the sides?
Well, in fact, yeah, I'm not to be really, I plan on building a kid. Maybe 12 years.
Okay.
So we have VHF contacts. We have,
To be able to-
meters that
so he has basically a
level
list of
our
commands.
commands below 1.5.
Okay,
We
and then
get
what
those switched
software
on.
do you have to use for that?
What's going
Well,
on.
all
That's easy to do.
toggles
So
are
you can
protected, make sure that.
You can buy the kits.
Like you hit the
Yeah.
max.
Yes.
Okay.
I'm actually doing it.
Oh.
It's a VAT
No.
thing.
You kind of have to wonder why.
I think you do have to be on a member.
Because they always.
You gotta be careful, you build a heavy duty, just like a club. Let's say a white outside, 3 or 4 members, they have to pay tax and switch.
Of course,
You gotta put so much force on it. You move it.
Right.
On the software.
Your email on
Yeah,
your,
it's took much power, you almost have
It's a
to
good
have something
international
that
event.
just
Yeah.
moves.
Wish we could get back up and running on this stuff.
That's the
That's got power, feeds power. Buy a switch.
Yeah,
Power.
does all that.
Speed, and then probably silver plated basically, because it's on
Right.
12 this one, yeah. All those cheap switches, yeah, first of all, moisture can get in.
Right.
USB, second's a USB, but we're time.
We're
not using switches. I have stuck.
I did Google Translate on it.
Yeah.
You show what the picture gets.
When we built
Class.
Of course, I should have known.
Social media.
But I just kept those switches.
I think that's really cool.
Right.
Either that or they knew who their audience was.
I'm done.
Yeah.
I like.
Very good.
These-
Yes.
Yeah, it's a particularly good one.
Plus.
Yes.
The questions
We
are
have
very
like,
clear. Yeah. The questions were great. It was, I think it was the only one. But that was giving a mission that I didn't get to. Well, as much as the lecture, always going.
No, the thing, that's the thing
It's
is.
not scary.
People are saying, we ought to replace them.
Oh, well, there you go.
Something else. But things, these are all.
We just get something up there that I can.
Well, yeah, they're.
I'll just buy.
Yeah, they're made of a very special
Yeah.
plastic.
Yeah. Yeah, and yes, and they're so darn small. The worst part about it is trying to get them on the board, you know, like you can't move stuff hardly.
Why I never used them.
Contacts are underneath.
We had those have been around in military stuff for years.
Texas, and I can't get.
They have a limited supply of money
Right.
and time.
Because
If you know of another connector that's
have
like
that issue.
9-pin like that,
But,
that, well, it's good, I'd be very interested.
It's done. He's gone for the moment. PC comes on, everything goes down, he comes on, it's on the floor, and the cat's sleeping.
I don't have that problem.
Yeah, Peggy's coming back down.
You're in the Navy, Barry.
She was.
I was a surface warfare officer. This was ancient times.
A SWO, right?
Yeah, I was a SWO. I was
Another retired Navy.
I got a missile destroyer, USS Dahlgren. I was on board I got my commission in October '75 and got out in November of '81.
Okay.
But, was at sea with the Dahlgren, and then my last gig was, an ROTC instructor, University of Florida in Gainesville.
Okay.
And I started my MBA Of course, when you're on a gig like that, they want you to get a graduate degree because you're there on the university. And I started my MBA, and then I got a call from my detailer saying, "Hey, we want you to go to destroyer school." I said, "Wait a minute, I'm supposed to be here for 3 years so I can get my degree." "Well, we want you to go next year." And I said, I think not. I actually got out and finished my MBA. Okay. So,
Yeah, I was a cryptologist.
okay, cool. CT.
Got my master's in cybersecurity and worked cybersecurity for Department of Defense for 14 years.
Cool beans. In DC or where?
Fort Meade.
Fort Meade.
I took the Langston course.
So.
Yeah, well, did
Paid
you?
the grounds.
Very
Oh, really?
One of them three-letter agencies.
What's finance?
Yeah, talk about it. I hear you.
We didn't run.
I hear you.
And you know, everybody's got three letters, but the
Community radio flow.
FBI is the only one that's got a good acronym for it. FBI, freaking bunch of.
Basically.
Yeah.
Were you at the Space Symposium in Baltimore, like in 2014? So we had our 40th anniversary.
Was a Pluto at that, and then this was also running.
2009. We also were there in 2014, and we were right by TWY. And of course, these guys bring their aero antennas and HPs and all that stuff. Huge satellite contacts in the parking lot.
Yeah.
People in black Suburbans were showing up to check us out.
No,
Because we were too close to
very
whatever
steep learning curve.
Yeah,
It's like
building was
It's great to be able to
nearby.
start from the part
there.
banks of the whole people. It sounds really crazy. I've done quite a bit for before.
Okay.
But when you have another program there, tell us new radio to kind of change mode.
Right.
Do
We don't
things.
talk about. And
So we also had
Those buildings aren't really there.
We also had software nationals there that was with, we took a picture, we called them the three amigos, right? They used their HDs and their aero antennas, and one was a foreign national. So, yep, I hear you.
Just those little tracks that take a long time to step through, it's really clear, and that's why that's all so that's shared. It's so great.
So it was a great conversation on what
Yeah,
the
I agree.
Americans were doing and sending them. Oh, yeah, we've done.
It's running.
Blah, 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 blah. What?
One of the guys who was there was Cuba. He ended up quote unquote emigrating up in Texas.
Call me back.
Antennas in all directions they come off. Did you make it over to the electronics museum there?
No, I did not.
So, for example, one unit could be radio, sensing system, TV, picture. Let's give it a try. Just to use the exit system. Yes. Of course, it's Newton. No, that one. I think what I want to do is this. It's happened. I will have ideas in my head. I can leverage this. I think there is experimentation. Yes, I can do them at all. Exactly. I have an idea. We may get more of what. Yes. For example, for radiation or like over there are some scintillating materials used in nuclear activities. So this is the sensor is excited not only one which hit, but if I impose such a big cluster that will cover all entities here, I'll get a more sensitive area. We are working on this one,
very SD camera to mount it. And also the sports, final sports kids. But this is never used. It's hard to find good people. I think it's much more easy. I'm not surprised how many people, students, for some teachers, need out. Many after.
Throw it up in the air. For everybody in the room and on the stream, a lot of people are still trying to finish up lunch, so we're gonna wait another 4 minutes or so. We'll start at about 1:15.
It's a good, amazing.
Most people are.
Doubt it. Huh? I doubt it. No, I said, who? Oh, I'm sorry. I thought you said, are we? Yeah, probably ISS. Crew, right? I mean, the guys doing all the shallow bridges and all that. There's, although, let's see how they do on 96 out of 5. Yeah. Let's see how they do with kilowatt. Yeah, yeah. Yeah, yeah. You know, if you're encouraging people when AMSAT was gas is efficient, and you have the support. Of course, you have the supply of antenna. Now sheer electric. Yeah. You don't have the capacity generation. Because you know, everything's electric. Even electric lawnmowers. I mean,
They don't know what it, you know.
well, yeah.
Show it, I can get into it.
Yeah, yeah. I mean, it's all kind of now. They're not something at night. It never bothered us. Well, it was a while ago.
Actually. Yeah. Way more than I remember watching him before that thing on national TV. Oh, God, no, geez,
Let's tie it off to the hatch.
Yeah.
What do you do? I
don't know, you ever see a picture of it that shows that the antenna was actually off before they went outside?
They sheared off going through his hatch.
Yeah, because.
It went out and went together. It's like this. We'll sit back, let's get with it. But the way Lou built that, it was an end connector. You had a piece of Delaware and close it around it. It's about that high.
Yeah.
So if it was, there was no way it was sheared off under the Dell.
Right.
If it got sheared off, that was less than 3/4 of a minute or so like that.
Yeah.
It's like Park Wolf. Coyote there.
That was it.
Really?
Some of the ones in the weeks ago, because Tesla's network is the best. Yeah. And these other ones are really for kind of the carbon like Tesla's that they buy now. But
It had a big silver zinc battery in it, about that big.
technological success too, right?
Yes.
Well, it worked. I went over there and I told everybody I was gonna help you out a little bit, field test. I unplugged and plugged in your Raspberry Pi about 20 times, just to make sure.
Good nose.
Yeah, yeah.
What did it cruise on? It was.
Yeah.
They were talking about. Getting out of Colorado.
Oh, cool. That's good, man.
You
wanna go?
1:15.
Okay. Storage goes down. Even if the situation was a thing that happened around here, it's like, my son's I think it's cool. I'm very cool.
Here.
All right, we're gonna go ahead and get started. We're running a little late, but engineering's got 3 hour or 2 hour and 45-minute blocks, so we'll make it up in there.
Or not.
Oh, you don't want me to show all my slides out for?
We want to welcome Burns Fisher, WB1FJ. He's going to talk about Golf Tee flight software and bus overview.
Thanks very much. Yeah, I'm Burns Fisher, WB1FJ. I'm a life member of AMSAT. I'm right now the volunteer lead flight software developer for the Golf satellites. And I just want to say that the Golf Tee project, as you know, has been going on for a long time. And I've talked about some pieces of the software before. In particular, in the 2000 virtual symposium, I had a whole video showing you what the software was doing now, but it seemed like a good time to go back over it. We have a lot of new people, new volunteers, and there's probably new people in the symposium here. And I'm going to actually go into some level of detail. There's only a little secret. But in any case, the point here, I'm going to go through some of the stuff about how the software in Golf works, and hopefully it will lead into Joseph's talk, which will be following on.
That's it. Jerry doesn't want that.
Okay then. So yeah, here's what I kind of talked about. I want to show you the Golf Tee flat sat, we call it, which is essentially the way the hardware is sitting right now. I want to talk about the flight software in general. And I say overview, it may be a little bit more in-depth than an overview. It depends on what you feel, how you feel about software, I guess. I want to talk about how the telemetry works. And I want to talk about the electrical buses, which sounds really boring. But hey, I mean, I think David talked about the CAN bus yesterday. So I'm going to talk about the CAN bus too, because that's fun. And some of their quirks. And eventually, as I say, that will lead into Joseph's talk, I think. First, I wanted to just bring up, there's a few anniversaries coming right around this time of year. FunCube 1, AO73, 11 years coming up next month. 11 years in space, really, that's really cool. Fox 1A, AO85 launched 9 years and 2 weeks ago. Unfortunately, the battery shorted out, as seems to happen in a lot of satellites. So it's no power. Will they open up? Well, that would be nice. But I mention it particularly because this is special to me. That was the first satellite that I worked on. And when I heard that come around the first time, I knew my software. What a feeling. Anyway, AO7 coming up on 50 years, still operating in the sun. Now, I say these anniversaries, and that's kind of, if you do the math, there's 122 Oscars now. If you do the math, the probability of an anniversary today is around 28%. So, you know, I just bring it up because it's fun. So this is the 3D printed model of Golf Tee, a 3D printed model of Golf Tee, I should say. And if you were at Hamvention, this is the very one that you saw. And if you were at Hamvention, you saw it was a little shaky and so on. And the reason is because the sides were actually 3D printed as well. Here is a new, do not drop this, Burns. A new 3D printed model of Golf Tee that actually has aluminum rails, and it actually has solar panel, sort of solar panels that fold out. So when it launches, they're going to be, I'm not going to try to fold it because I don't want to break the 3D printed solar panel, but they're folded flat and they unfold twice like so. So you get essentially 5 panels across. And that gives you something in the area if you're right out in pointing at the sun, something like, what was it? Is it 30 some odd watts?
Yeah, about 36.
Yeah, 36 watts. Now, you're not going to be pointing at the sun all the time, of course. And sometimes you're in eclipse behind the Earth. Sometimes we need to point at something else and so on. But that's a general idea. We have a surprising amount of power as compared to the Fox 1 satellites. So thanks to Tom Karnauskas for doing that 3D printed model. This is great stuff to be able to actually visualize what these things look like. But this is what golf looks like right now. This is my shack. We call it a flat sat, and you can see kind of why. I'll show you the pieces of it so you'll have a better physical idea of the pieces that are logically connected to software that I'll be talking about in a few minutes. So let's see, this is the microwave receiver transmitter. It's an EDIS 310, which you can see right here. Now, when it's in the satellite, it's not going to be in that metal case, but it'll be the EDIS boards. It's the microwave uplink it'll receive, and that 10 gigahertz downlink. This thing won't output 10 gigahertz, but it goes through an upshifter and a power amplifier and so on. The yellow wire that's coming out of it, going to a solderless breadboard right there, is the CAN bus through which we're going to talk to it. Obviously, we're not going to fly the solderless breadboard, but plug everything together in my shop just because I'm a software developer, not a hardware guy.
That's pretty good for a software guy.
Thanks.
Yeah, pretty good.
Yeah, you should have seen it was even worse.
You tidied up.
I tidied it up. Yeah, that's right. That's right. So this is actually a stack. This isn't totally flat. This is what we call the it's going to be the transverse stack on Golf Tee, and transverse, of course, means across the length. So let's see, well, it would be down here somewhere.
I think you can see it from the back.
Oh, okay. We'll see. Nope, not in this one.
Oh, side. Yeah.
Right.
I might have to put it on
You
the
can see
floppy.
let me bring it up. Yeah. Thank you. Yeah. So you can see there's a stack of boards that go across instead of up and down. And the reason we're doing that in golf is because of that EDIS. The EDIS boards aren't cut to the same size as everything else in the spacecraft. So we just had to tweak things around and turn them around and twist and turn. So we ended up with some boards being transverse. And this is how they are in my shack right now. It consists of a command receiver, a 30 kilohertz linear transponder, and a UHF telemetry transmitter. So and it also contains 2 command receivers and 2 onboard computer boards. So this is similar to the LTM board set that I talked about a couple of years ago in Minnesota, and it's been discussed around here quite a lot today, yesterday. In the center of the picture with the gray ribbon here, this was the center of the original picture, but I cropped it down. This board is called the CIU, the Central Interface Unit. And you can kind of see there's a lot of wires coming off it, and that's because This is where everything connects together in the satellite, the central interface unit. The next version is going to be a lot different from this one because you have a lot of changes. This is a couple of years old. The big white thing, by the way, is just the programming module for all of these packages. Terribly interesting at this point. This is the GNSS unit in red here. GNSS is Global Navigation System, Satellite System, which is kind of a generic name for GPS because it will also receive Galileo, GLONASS, and a couple of other countries have global navigation systems. But this little board is the only thing that flies. The rest of this stuff is the development kit that the GNSS provider sent to us to, quote, help us. And I mean, it does help us because this is just one tiny plug right here. And this does a lot of the CAN conversion and serial line conversion and so on. So it is something. And on the far, I think it was on the far left of the original picture, this is the attitude control system. We call it the ADCS, attitude determination, thank you, and control system. And this is the unit that will fly. This is the board that they gave us to help with development. And you can see it's connected by a bunch of wires, whereas in the satellite, well, it won't be these wires, but that many connections somehow need to be made within the satellite. So I want to mention also, by the way, that there's a bunch of wires you see floating around here in various places and various times. A lot of those are the CAN bus that we'll be talking about because that's running all over the shack. What else do we have in that shack? This is the RTIHU. It's the radiation tolerant IHU or onboard processor. The reason we hope it will be radiation tolerant is because it's an automotive grade. It's not radiation hardened per se, but automotive companies really don't want a little stray cosmic ray going through your brake system computer to suddenly stop your car's brakes from working. So they are not radiation hardened, but they have a lot of stuff in them to help out. They have EDAC memory, which is what does EDAC stand for? Error detection and correction. Thank you. Yes. They have lots of parity on the buses. There's actually 2 cores within each of these that are executing the same program. And if they don't match, then they raise a failure line. And you say, well, what happens if they raise a failure line? That doesn't help anything. Well, it does on our system because the RTISU actually has 2 separate processors. Right down the middle here, you see these 2 guys and some more are bus switches. So only one of these processors is connected to the satellite bus at one time. And these are not exactly mirror images, but essentially the 2 halves of the board are the same. And only one is the major controller at any given time. The Golf T will actually have 3 different processors. It has these 2, and it has the traditional processor that we've used on all the Foxes that we use in AMSAT 1. So we have one that has a lot of space heritage. And we have to coordinate those, of course. And I talked a lot about that at the 2020 Symposium, so I'm not going to go into all that now. So let's talk about the software now, my favorite thing. The software is actually running a real-time operating system. A lot of earlier satellites would just have a loop, basic loop that would just call things and come back and call things and come back. But we're really using an operating system in here. Now, a real-time operating system, and FreeRTOS in particular, is pretty simple operating system. It only does a few things. It does task switching. It has timers, it has queues, and semaphores and mutexes, which are pretty similar things. So think of a task as being like one of the windows in your Windows system or your Linux system or whatever. It means programs that can run individually, not connected to one another. So any task in the real-time operating system can wait for for a timer. It can wait for something to be put into a queue. It can wait for a semaphore. And when it's waiting, the other tasks can run. And when you wait, you can just stop where you are. So you don't have to loop back to the beginning and figure out where you were when you stopped. So that's the real advantage of a real-time operating system. I do want to say, by the way, most of the things that I say here apply to Fox, the Fox 1, AMSAT 1, Fox Plus, the LTM, and so on, because this software was pretty much written from scratch, but it was written from scratch for Fox 1A, the first Fox. And from all the satellites since then that I've been involved with, we've just taken the same software essentially and tweaked it, modified it, added more stuff to it. In golf in particular, we added a lot of stuff because the multiple processor stuff is completely unique to golf. So let's talk about the tasks that are actually there. Remember, task is an individual program that can run, that's more or less individual. There are interrelations between the tasks, but think of them as separate applications. So here are the golf software tasks. There's 8 separate tasks in the golf software system. Fox, I believe, had only 5 or 6. LTM doesn't have as many as 8, but golf has 8. And I'm not going to talk too much about any of them beyond what I say right in this one. But just to give you an idea, and of course I don't have them in order, the diagnostic one is also called the console task. That's what we can type commands to when we're testing it on the ground and say, okay, show me the telemetry for such and such, or switch to science mode, or whatever. So this is essentially the console. The downlink control, I'm going to wait till the end for that one. Telemetry collection is just what it says. It runs around and collects all the telemetry that we have available. It reads the temperatures. It looks at voltages and so on and so forth and collects them all together. And it will also, one of the things that we downlink is a min-max. And the minimum and maximum can be cleared, but typically the min-max will be able to tell us since the last time it was cleared what was the minimum value and maximum value, which of course only makes sense for certain kinds of values. You know, true, false doesn't make much sense. But that's what telemetry collection does, is it goes around and runs through the min-max algorithm or the telemetry values that make sense. RxTX control is the task that actually runs the radio. So it is the one that in some case that will send the telemetry data to the modulator. And in some cases actually does some of the modulation, depending on which processor we're talking about. It also does the receiving and can recognize when there's an uplink command and does the appropriate thing with the uplink command. And the appropriate thing with an uplink command is to collect the data together and send it to the commanding task. So the commanding task's job is to decode what the heck does all this stuff mean that you just sent me. And oh, by the way, I have to de-encrypt the authentication codes that are along with it and make sure that this is legitimate. And also check time and make sure that it isn't a repeat command and all that kind of stuff. Experiment control runs the experiments that we're flying, and in Golf's case, we'll be flying a Vanderbilt radiation chip test. I guess I'll leave the CAN bus control for a minute too. But processor coordination is quite new to Golf. Processor coordination is a task that keeps looking at the processors and making sure that there's an active processor. If one fails, it switches to a different processor. And when it switches to a different processor, it either makes sure the bus switch is thrown on the RTIHU, or if we're using the old IHU, it goes through all of the connections to the bus and tri-states them so that there's no drag on the bus flow. CAN bus control. Now, the CAN bus is interesting, and I'll talk a bit more about it later. But the CAN bus is totally asynchronous from everything else. In other words, if I'm using an I2C bus or something, I have to say, tell me the temperature. And the temperature sensor says, okay, here's the temperature. And it doesn't do anything until I ask it. CAN, on the other hand, might bring in some data anytime. Another task might send CAN, another device might send CAN. And in that case, I need another task, which will collect that CAN data and put it somewhere. So those are the tasks on Golf T. Device drivers. You may or may not be familiar with the term, but if you use Windows, if you use Linux, if you use Mac OS, these all have, if you use VMS, which I worked on, these all have device drivers. And what you'll find is sometimes you'll get a device and it doesn't work on your Windows machine. Always works on Linux, but it won't work on your Windows machine. So you have to download something they call a driver. And the driver is the thing that knows how this hardware works and is able to connect it to the operating system. Well, you don't get any of those supplied by free hardware. You have to write. We had to write every one of them. But the really critical thing for use in RTOS is that devices must be interrupt driven. It's pretty common for software that's just written not for an operating system to tweak a device and then just kind of loop around and wait for it to be done. You can't do that if you've got an operating system of any sort, because that means another task can't run if you're just sitting there looping. So the general path for any of our device drivers, the way we worked it, was that the task calls the device driver to ask for some data. Say, like I said before, the temperature from the I2C bus sensor. The device driver sends the commands over the bus to the sensor, and then the device driver sets the semaphore and waits on the semaphore for the data to come back from the device. Now, when it waits on a semaphore, the operating system knows about this, so another task can run while it's waiting. In the meantime, the data returns over the bus. The device forces some sort of interrupt to run, and that releases the semaphore, and therefore makes that task able to run again when its turn comes around. So what do these tasks actually do, or how do they work in general? So this is kind of a generic task. Wait for something. Something triggers it. Otherwise, it's just sitting there waiting and not doing anything. So the trigger happens, and typically the trigger has some value. It either says, hey, I received something from a sensor, or I received a CAN message, or whatever. And then the task uses whatever that value was to do whatever it has to do for its job. And it might do I/O in the middle of it, so it can stop in other places other than that beginning wait. But this is the general path of a task, and it goes over and over and over and over again. So what might a task wait for? What is in the beginning there? It might wait for a timer. The telemetry collection task at the top of its loop waits for a timer. And every 4 seconds, it goes to all the devices, collects the telemetry, does the min-max calculations, then goes back and waits for the next 4-second timer to go off. It might wait for a message from another task. An example I mentioned before is the command task. We'll get a message from the receive transmit task, giving it command bits to decode. It might wait for a device interrupt. RxTX and CAN are both the top of that loop is waiting for an interrupt for a device, either to tell it the transmitter saying, okay, I need more data, or the receiver telling, okay, I've got a command, do something. And in CAN's case, hey, somebody sent a message to you, here it is. So I'll just talk a little bit about this particular task a little bit more, because this is the task that's kind of the most complicated one, I would say, and it's responsible for implementing modes. You might have heard the LTM, or I think Mark was talking about the modes for AMSAT 1, safe mode, science mode, health mode. This task, the downlink control task, is the one that implements those modes. And how does it implement them? It implements them because this is the task that's responsible for deciding what telemetry to send. We've collected all the telemetry, but we're not necessarily going to send it all in one big lump. This guy decides what telemetry to send, and what telemetry it sends is based on the mode. So if you're in safe mode, you want to send stuff that's important for people like us on the ground who are trying to understand how the satellite is working. That's the stuff you want to know. In health mode, you're interested just in all the general health information. And in science mode, you are particularly wanting to spend most of your bandwidth downlink sending science data. So that's the job of the downlink control task. Let's see. How's telemetry sent? There's two sub what do you want to call them? Pieces of telemetry. One is a frame, and the frame is always a fixed size. The frame has the forward error correction applied to its entire thing. It's got a CRC, cyclic redundancy check, error checking applied to the whole thing. And if you have collected telemetry using FoxTelem, that's what gets counted. You'll see it running for 5 or 6 seconds, and then the counter for the frame counter increments. But what is within a frame? And within a frame are smaller pieces called payloads. Why do we have all of this separate thing for payloads and frames? And the reason is that there's some data that you want to send more frequently. For example, whole orbit data. We need to send that fairly frequently because we need to get the whole orbit data down before it gets overwritten by the next orbit's worth of data. So we send that fairly frequently. So we have one whole orbit data payload, but it appears multiple times in multiple different frames. In addition, as I mentioned before, some data has min-max values, and the data that has min-max values are separate payload, because you can use that same payload to display the minimum and maximum values. And a lot of credit for this goes to Chris. Yeah.
I'm just wondering, under header frame type 2,
yeah,
payload type 2 is repeated. Is that accurate?
Yes. Yes, suppose payload type 2 might be the whole orbit data. And so what you want to do is send if whole orbit data is collected once a minute for the course of the, over the course of the orbit, you need to send it more than once a minute in order to be sure it's all down. So they wouldn't be identical, but one would be for 1 minute, one would be for the next minute, and so on.
Great, thank you.
Yeah, sure. I don't know if you heard the question. The question was why there are two payload type 2s there in the same. So sizes. The other thing about the payloads are that they are not all the same size. I did say that the frames are the same size, and they have to be because of the way FOX2LM and the forward error correction works. But within the payload, within the frame, the payloads don't have to be the same. Oh, let me just mention, yeah, this, let's see, filler at the bottom, because the frame sizes don't necessarily all add up to, the payload sizes don't necessarily add up to the same size as a frame, so we sometimes have to fill in stuff. But the reason that the frames have to be the same size is because of the forward error correction that we're using, which is a Reed-Solomon type of 223, 255, if that means anything to you. I'm not sure it does to me. So notice that the size of the payloads are fairly small. Let's see. So these are frames here, and this is the size of the frame, the size of all the payloads that are in that particular frame. So this is the number of wasted lights in the frame. And just for an example, here are the payload sizes. The header is only 12. The health is 100, and that's subdivided. Minimum, maximum, full orbit data, health guy, and so on. You can see there's a whole bunch of different payload types, and we put them into different frames in order to, in a way that makes sense for when we want to send a particular payload type down. So you can probably guess that FOX2LM, the ground software, and the flight software have to understand the same formats. Well, how do we do that? We started out doing it, and it was really complicated. You know, we had each of us had our own little paper description of what the data looked like, and I would change something, and Chris would say, "Oh, you changed something. Now we got to change something," and so on. And so what I finally started to do for myself was to we got to keep it in sync across country borders now that Chris is in Canada. So what I started out doing was making an Excel spreadsheet. You know, everybody makes an Excel spreadsheet when you want to figure something out. And the Excel spreadsheet would have all the data items and how many bits or bytes they were, and how they added up, and blah blah blah. And then my little revelation was, oh, I can write a Python program and turn that into C data structures. So now when I make a change, I tweak the spreadsheet and run the little Python program, and I get all the data structures that I need in the flight software, which was kind of fun. And I should say the payload definitions are totally open source. They are on GitHub, and they are on GitHub, in fact, under FOX2LM. So they're under Chris's GitHub account under FOX2LM, and just kind of to prove that we both use the same thing. So the next thing that happened was Chris looked at this and said, "Oh, well, I can make FOX2LM so that it will work with CSV files." And if I just write a Python program, I can turn your spreadsheet burns into CSV files that will tell me how to decode them and display them in Foxtel. So that's been working pretty well now for several years and several different satellites. We've been pretty happy with it. And don't even try to read it. All I want to do is point out a few things. There's a name of a field. This one says reflected power. The code name that goes into the seed. Here is the number of bits, the data type, and this word is conversions. So this is the name of a conversion that's in Foxtel. So a conversion means if I send a number like 0 to 255, that might represent 0 to 5 volts. So the conversion is just telling Foxtel how to take this number and actually display it in, I was going to say human readable terms. Maybe 3.7 volts isn't readable to some humans, but to engineering folks anyway. So that's the way we do telemetry. And now going on, I wanted to talk a little bit about the electrical lessons. Now this also sounds boring, but well, sorry. So switching from software to hardware, these are the buses that are used in golf, but they were also mostly used in the other satellites as well. A bus in electrical terms generally means a set of wiring that can carry data to and from multiple devices. In other words, it's this whole thing, or this whole vehicle with multiple people, or multiple devices, if you want to think of it that way. The one that to talk about first is the SPI bus, not SPY, SPI, standing for Small Peripheral Interface. It was actually invented back in the 80s by Motorola. It carries 3 wires that go to everybody that's using it, and then a separate wire to each of the devices that uses it. That separate wire says, okay, I'm talking to you, guy, if I raise the voltage on that select line. It's full duplex. You can actually send data in both directions simultaneously, although not too many people do that. Too many devices, I shouldn't say. It's pretty robust and it's pretty simple. It is a master-slave protocol, and we just need to step aside and say there's a lot of controversy about the term master-slave. Right. Okay.
Why the superscripted one?
Hmm?
Is that why the superscripted numeral 1 is
Yes,
there?
it is. Yes, it's just to remind me.
Good for you.
Yeah, yeah. And you know, I get that. But as far as I know, at this point, there isn't a real good terminology that describes it.
Yeah.
Because what master slave in this case means is that there's one device, usually the computer itself, called the master, and that's the only one that can initiate data transfers. The slaves are all of the devices. And you know, like I say, I get the terminology has issues, but so there's a lot of devices, including pretty simple chips that use it. What we use it for is MRAM, which is non-volatile memory storage. We use it for the telemetry modulator on the RxTX card. We use it for the command receiver transmitter on the RTIHU. And believe it or not, we use it as the CAN interface on the LIHU. The LIHU never had, and that processor does not support CAN, but we have a chip that can interface between SPI and CAN. So that's why it gets used there. Another device that you hear quite a lot about is I2C. Sometimes it's called I2C, I2C, IIC. It stands for Integrated Circuit. And that was also invented in the 80s by Philips in this case. Now, the nice thing about I2C is that it uses 2 wires. And each device that might be on that bus has an address, so you don't have to have a separate select line. You just send an address on the bus, and only the device with that address will respond. It's unidirectional. It only goes in one direction at a time. It is a somewhat complex protocol. It is a master-slave protocol, so it can only be started by one device, although you can sometimes have 2 masters on the device. I've never done that. It's a little more complicated. I have found that it's easy for EMI, electromagnetic interference, to hang the bus. I don't like I2C for that reason. If I walk up to something, shuffle along the floor and touch some metal, boom, there goes my I2C. Maybe I don't have to worry about that kind of thing on the satellite too much, but I still don't like it. Yeah. So anytime we use it, we also have a reset line so that if I2C is not responding, we can power down all the I2C devices and reset them and restart. So what we use it for, there are temperature sensing chips that run I2C. There's analog to digital converter chips on I2C. The Vanderbilt experiment that I mentioned talks to us over I2C. We use it as a backup for antenna deploy, and we use it as a backup for communication with the ADCS, the attitude control system. And finally, CAN, my favorite of all. It was designed for automotive use by Bosch and others. Everybody jumped on the bandwagon after Bosch came out with the very first version. And I say in the late 80s and 90s, because there were multiple versions and it didn't really start getting used in cars, in a lot of cars, till a little bit later. It is also only 2 wires plus relay, and it's differential, which means that all you care about is the voltage difference between the 2 wires. So if you get some electromagnetic interference or something, it's probably going to affect both wires the same, and it won't change the data that you see because the difference between the 2 signals is not so likely to change. It is not master-slave. Any device can initiate communication. And it's fairly robust, although it is complex. It's robust because it has its own CRC, it has its own retry capabilities all built in. And most devices that use it have some sort of built-in processor. It's harder to, you see CAN less on simple little cheap devices, which is the big disadvantage. So what do we use CAN for? A lot of stuff on golf. So the power system is going to connect to the CAN bus, the legacy, the original onboard computer, connected to the active radiation tolerant computer, to the CubeSpace attitude control system, to the GPS system, to EDIS, to the CIU, which has a processor running. And the thing you might notice is this little red arrow here. There are actually 2 CAN buses on golf. This one connects the active and the standby RTIHU processor. And that means if one of the processors screws up, it's not going to bring down the entire CAN bus because these 2 are connected and they've got an isolator between them. CAN messages, and I think Dave yesterday was talking about CAN, and yeah, CAN sounds simple, but everybody has their own idea of what the CAN message looks like. Yes, very true. Very true. There is no device address. Any device can send a message, and it's quite possible for multiple devices to read the message. Remember, these were originally on automobiles, right? So let's say that you have the engine control unit sending out messages that say, okay, my RPM is 1728. Well, who wants to know about the RPM? Well, probably the fuel injection system, certainly the tachometer on your dash, probably something to do with a emission control system. You know, lots of things want to know it. So the engine control system sends out the message, and lots of people can read that. And that was the intent. That's why it was designed that way. Each message we don't say it has an address, we say it has an ID. And the current version that we're using has a 29-bit ID. It also has a data count, 0 to 8 bytes, and 0 to 8 bytes in data. Typically, devices that have CAN controllers can filter out CAN messages, so they can say, I only want to see the messages, and this is in hardware. I only want to see the messages that have this bit set in this ID, this bit clear in this ID, and I don't care about the rest. You can send me anything else. So they can very clearly, if you were willing to divide that ID into fields like this that include the source and destination, you can filter CAN messages for only messages that are intended to be that are destined for you, have your destination ID. So the CAN ID, well, I designed a CAN ID scheme for Golf a few years ago, and then we started getting the ADCS unit. We started getting the GNSS unit, and guess what? They both have their own ID definitions.
And it made you scream.
It made me scream, yes. Yeah. These pictures, by the way, are open source pictures. Luckily, I was able to move the destination and source messages or fields in the Golf ID around so that they would work. I can figure it out. I'll show you. Yeah, so here's the only C code that we have. Don't worry about it. The only interesting thing is that, see, this says CAN ID bits. This says J1939 GPS CAN ID bits, and this says CS, which is CubeSpace CAN ID bits. So these are the definitions of the IDs for the 3 different types of devices. And it's a lot easier to look at something like this. And what you can see is that the big difference is, and this is just the ADCS design, but the GPS was pretty similar. You can see the big difference is the source and destination fields are bigger. These are 8 bits. Yes, 8 bits. And I was only designing 4 because we didn't have that many devices. But guess what? If the source and destination are less than 16, that is, they're only 4 bits, then I can look at it with using this field and say, oh, I'm only looking at these 4 bits, but I can still tell that this is intended for the ADCS or for the GPS, and then switch over to the other definition. So I just was totally lucky that it worked out to be similar, or similar enough that I could do that in the lesson. And as I say, the GPS is pretty similar. Took a certain amount of different hassling, but the big point is that I can look at that a GPS ID and tell that it's intended for the GPS that it's from the GPS and going to the GPS. I want to mention CAN commanding briefly. We're kind of getting closer to Joseph's talk, so I want to set it up a bit here. I just and before anybody freaks out, oh, you're talking about commanding in a public forum. No, I described a plan for secure commanding 9 years ago in 2015, and this is pretty much what we're doing. If anybody wants to see how our commanding works, I'm happy to show you. I only won't tell you the secret key that is used for encryption. But for this talk, I only want to point out a few things. A command can be sent that contains a CAN message. Okay, so and this is particularly good for LTM when we have universities, and we have no idea what they're going to do. But we say, well, if you want to send a command to your stuff, just format a CAN command and send it up on the uplink, and we'll give it to you, and you do whatever you want to do with it. There's a restricted set. You can't mess around with the importance of the commands. Another thing about commanding our satellites, and maybe satellites in general, Mark is very well aware of this, is that commands are reasonably slow and they don't always work every time. You have to repeat them. And so it's a good idea to be able to repeat the same command multiple times and not have that hurt anything if the satellite sees multiple of them. Mark knows about my.
We test that often.
Yeah. Mark knows about my AMSAT 1 book where bad things happen when you get the 2 science mode commands at one time. So any command that you can send up has at most 8 bytes of data. So you might think that this is not related, but it is. How does the ADCS work, by the way? I don't know, but I know that the ADCS needs to know where it is in an orbit, which means that, or the way that it knows is by knowing the Keplerian elements of the orbit that it's in and the time. And with those 2 things, it can figure out where it is in Earth orbits, just as we can figure out where to point our satellite antenna with that same information if we want to point them a satellite. So the time and the orbital elements can be uploaded by commands. See, I told you these 2 slides were related. How long does it take? Well, let's take a look. What does the ADCS time look like? And this is actually from the console task. This was me typing to the FlatSat and saying, well, tell me what the ADCS thinks its time is. And it tells me in somewhat the same format as you need to tell it. So I decoded it at first here, 2024, day 308, and so on and so forth. But this is the number that we have to use to tell at the time. If you're Unix geeks, you'll know that that's the number of seconds past January 1st, 1970. And it fits in 32 bits. So that's 4 bytes, easy to send in a single command. What else do we have to send? We have to send it the orbital elements. So I, again, asked the ADCS to give me what it thought its current orbital elements are. And I'm sure you have these memorized because this is actually AMSAT 1. That's what I told you. There are 8 numbers here. If you normally look at your TLEs that you get from Space Track or whatever, there's 2 more that are a little bit more second degree changes. But if you don't need those, if you send these off in enough. So epoch, inclination, eccentricity, perigee, anomaly, etc. But the point is that there are 8 of these, and each one of them is a double precision floating number. So it takes 8 bytes. So that means you need 64 bytes to send this command. So you would need to send at least 8 commands, and 8 commands would have to get through successfully. So if you have to actually update these every week, every 2-3 days, you don't know yet, that's going to be a lot of work for the ground stations. And on top of everything, if you can't get all these commands in a single pass, then we have to have some way of saying, well, I don't want to send all the commands, I only want to send one. And we have to have a way for the ground stations to know which ones what order to receive. So there's a certain amount of complexity. to make this work. So we have another way to do it. You like that? So Joseph will talk about that in the next talk. So before I turn it over, thank you for your attention to a rather detailed presentation. If you have any questions, please go ahead. See if I can answer them. Barry?
How much capacity of the system is now going to be utilized? How much ability to increase software storage or data in the FPGA with the current design?
Yeah, so the question was how much of the processor is used up essentially, and the question can actually be looked at in two ways: how much of the time is available for the processor, that is, how much idle time is left, and the other question is how much memory is left. And the RTIHU is currently using quite a lot less than half of its memory, of its flash memory, where the program is stored. And I haven't looked recently at how much of RAM it's using, but that's not a problem.
So how does that compare to five?
Certainly more by a good lot. But we had on the LIHU, the older processor, on Fox, we probably could have had 2 copies of the software. I don't think we can now. On the RTIHU, which is bigger, we might be able to do that. Any more? Okay. Oh, I heard people talk. So you're going to use that?
I think it just died. Yeah, this one's. I'm not.
I think we're at that.
One Burns was using was working.
Stop.
Just good.
Oh, right at the last second?
Yeah.
I thought I could hear myself most of the time.
Yeah, just quit. Just quit.
Buddy. Just be quiet. I know. I looked at it.
Luckily, this small room.
Yeah.
When these two used it, microphone for the remote? No, it's picking up off the webcam.
All right.
Just talk about it and I'll try to find a.
I will project. Good afternoon. Thanks for having me. I'd like to thank everyone who's sticking around for these shenanigans. Rachel asked me before, she said, "You're a chemist and you're doing this." Yeah, the answer is yes. This is a crime of passion. And that's my involvement with AMSAT is to do that. I got on board last spring and was scouting about for things to do, and I started complaining that we didn't have a GNSS receiver on AMSAT on Gulf, and it was kicked off. But then all of a sudden we found out we needed to have one for the ADCS, and so I'm back in business. So I'm going to talk to you today about helping Burns do his software work, how I'm going to get information from the GNSS receiver, which ought to be buried somewhere around here. Batteries over there, either up there or down there. I think some kid was probably trying to decide where he needs this. But we have a receiver in there, and we'll talk about how we're going to get the orbital elements. So this is going to be a bit of astrodynamics, as they used to say in Monty Python. Now for something completely different, right? So to set this up, those younger than a certain age might find it hard to believe that there was a day when devices, and especially munitions, didn't know where they were going. They were basically shot and they just went. It's true. It's true. I wasn't around for either of those, but I'm told they are. And the way they could do it was because the people who built these things understood physics. They understood there was a model for how these things went. So a cannoneer could basically know the amount of energy that was in the propellant that was being used, the mass of the object, and could then, by adjusting the angle theta here, could get a distance out of that. But it was not easy to do that in the field, especially back in the day. So there were folks around, they were called computers. Those were people. Computers were people back then in the 40s, and they would make these things called firing tables. They basically understood enough physics, they had sharp enough pencils, and they could figure out where something was going to go based on that, and other folks could use it. Well, I'm going to talk today about a somewhat similar circumstance in microsatellites. Microsatellites, with spacecraft now, GNSS is becoming increasingly prevalent, although the micros are a little bit behind the curve on that, and we're all catching up. So we're going to talk about the models that we use to convert this information that we get out of the GPS or GNSS receiver. You can use those pretty much interchangeably for the purpose. The physics that is associated with this is what's called the so-called two-body problem, not the three-body problem, which is unique. Yeah, but there are actually two-body problems. The classical mechanics is two objects orbiting each other, gravitationally bound, square law rule. But many of us are familiar with the two-body problem in life, and that is trying to find jobs for both us and our spouse in the same city. So the two-body problem often reduces to a one-body problem. Kepler figured this out hundreds of years ago. Clever guy. If one of the bodies is much, much heavier than the other, it reduces to a single body problem. Right? We can have that handle in there. Jump forward 400 years in one slide. And here we are with GPS. We have now satellites, devices, and they've already been demonstrated. One of the questions a couple of years back was, could it work if your satellite was above the GPS constellation? And the answer is yes. But the point is, what you get from a GPS reading is two things, three numbers each. You have the instantaneous position. We're all used to seeing that. We know that means the GPS receivers and our phones and everything, but we also get the velocity. Three-dimensional. You could get it in any number of formats, they're all equivalent, very convenient for a lot of things. It's to do Cartesian coordinates, X, Y, Z. And there's a picture of one of those receivers. Now, Burns overstated his position. His receiver is not going to fly. I'll explain why. Mine will. When you start talking about GPS, any kind of a measurement you make, I'm a physical scientist. I spend a lot of time with 20-year-olds, and we talk about significant figures and how they always overestimate. But in GPS, it's important. If you're doing something very, very simple, and I thought this was very funny that this is the comic XKCD, Randall Munro, a great author. He says if your latitude longitude precision is 28 degrees north and 80 west, you're probably doing something space related. We're doing a lot more, lot tighter than that. But here's the model that we will use. I said there's the basic physics, and we're going to use a Keplerian model. Right? It's well known the solution for the one-body problem is, generally speaking, an ellipse. Right? If something is gravitationally contained, the orbit is in the shape of an ellipse. To define ellipse, not remarkably, it takes 6 parameters. And what we have is an ellipse. 3 parameters give us the shape of that ellipse, and 3 parameters give us the orientation of that ellipse in an important frame of reference. The answer to most mechanical questions in physics is your frame of reference. It's always the case. You get it in there. So we have a whole bunch of different ones. Very annoying names. The names for these different parameters, we saw that before, can be quite annoying. I don't like the idea that the position of a satellite in its orbit is called an anomaly.
Yeah.
It's a couple of 100 years old. Don't blame me. I didn't do it. I didn't do it. I didn't do it. But here we have 6 parameters that serve to describe this idealized model of an orbit, right? Motion, and how these are mean parameters. I'm not gonna enumerate them. One reason I'm not gonna enumerate them is because no one can agree on them. No matter who you talk to, there'll be slightly different variations. They're all they all are ultimately equivalent. They can be interconverted into each other. We all have to deal with the same number systems. Let's get real, folks. But nothing is so trivial as not to have holy war, right? So different individuals use different ones. They're all the same. We have to generally work on that. But we have a problem. And the problem is stated in the first paragraph. A state vector is defined as the instantaneous position and velocity of an object that's in orbit. 6 parameters, X, Y, Z, do spherical coordinates. It is interesting, and it's a lovely thing that you can take a state vector and you can convert that into those orbital elements with only trigonometry. This is easy for me. Remember, I'm a chemist. Right? This is variational calculus comes involved in this, but I have to say, to my great relief, I have studied quantum mechanics, and that makes no sense whatsoever. At least this stuff makes sense. At least this stuff makes good sense. But that's the problem. The initial value problem connected with Laplace, right? Actually, it was actually Italian but turned French. And then Gauss, who was German but never changed from that. Initial value problem, take the position and velocity vectors, RV, at a given epoch. That's another one of these terms. An epoch is basically a moment in time. Put everything else out of your mind. Just when you see epoch, it's a moment in time, and you'll be happier. You won't even feel look at this stuff. We can convert those into those 6 coordinates, right? You can also go backwards. You can go forwards and backwards, and we're going to do that both ways. Now, as was mentioned, as Burns mentioned before, this information needs to be determined. In fact, there's a couple, I'm from Northern Colorado, and a few 100 or so miles south of me, there's a couple of folks down in a place called Cheyenne Mountain who are keeping track of a lot of different objects, right? They've got enough room in their fields there. They can do 100,000 objects. We're running out of objects. So down there, they keep track. They take data around from around the world, optical data, radio data, and convert that into position data and velocity data, and convert it into Keplerian elements. Oops. Those elements are commonly referred to as 2-line elements, which is kind of ironic because there are 3 lines in it.
Same letter.
Same letter, TTLE. This is a standard encoded terse message, which comprises the information that Burns mentioned before. This is the one for ISS, which embedded in here is the epoch when it's valid, right? It's valid for a moment in time, but it's a model. So just like those cannoneers, once they fire off that projectile, they know its velocity, they know its orientation, they know its mass, they can predict where it's going to land. It's the same thing with this. Given this and a good sharp calculator, maybe a sharp pencil and a good HP calculator, you can figure out where that is going to be at any moment in time. It's really terse. It's extremely terse. There's 79 characters across the bottom. Each of those lines, you say, why 79 characters? This was written in a time when I was in college, I had a work-study job in the computer center. Computer center was as big as this room. It had one IBM 360 in it. And I had a disk drive. We got a disk drive one day. Came in, we brought it in. It was the size of this. It had 30 megabytes. And it cost $30,000.
You'll never fill that drive.
Unbelievable. So we were throwing around colorless cards, punch cards, and it turns out there's 80 characters across that card. And so that was what we used for. how many years, how many decades old is this? And we're still using the same format. Fortunately, some clever young kids have been working on some other projects. I think the youth are going to save us. I'm convinced. We're going to, that's all I'll say. They're going to save us. The orbital means elements message, OMMs. That's another format that's being used and it's available. And this is a small piece of code. This is my homage to a little bit of code there. This here, there are a number of different ways. XML, you can put these things in XML. There are all kinds of ways. Same information, a little bit more verbose, taking advantage of things that we have available. Here's my flat sat. All right. I'm a hardware guy. You see how much tidier. There's a lot of solvent weld acrylic on there. There's a lot of hot glue holding wires down. Plus, I said, Burns's receiver is not going to fly. Mine is. I just took delivery just before the week before we came here. We thank you, board of directors. We bought a second receiver. There's an interesting problem with these receivers. It's not the problem with the receivers. It's what people do with them. The receiver can give you instantaneous position and velocity. You could use that if you're driving a car, if you're flying a satellite, or if you're sending out an ICBM. It's a dual use problem. And if you're going fast enough, that's probably because you're in a rocket. And if you haven't filled out the right paperwork, you might not be a friend of ours doing that. So there are various organizations around the federal government that say, no, you can't have a receiver that gives a result that's greater than 600 or so meters per second. If the receiver they're hard coded so that if it exceeds a certain speed, it stops reporting. Now you can fix that. Fill out you get Jerry to fill out get Jerry to fill out a bunch of forms for us, our VP of engineering, pay a ridiculous amount of excess money, and they turn that switch off. So there's one here. Now, why do I have one of these receivers? I'm not going to take this thing and go fast. All I'm going to do is I found a colleague down at CU Boulder where they have a strong aerospace department there. They've got a simulator that generates RF, and I've already convinced her to let me come down there, drive this is why it's all glued down, because I can't just leave it in my shop. I have to bring this down to Boulder, and we're going to fire it up with her simulator and throw different kinds of scenarios at it so we can validate it, right? The goal here is to increase the reliability of our of the success of the flight. So we want to do as many tests as possible on the ground. This is a flat sat. Receivers there. We've got some DC power. These things are really persnickety in terms of the voltage. It wants 3.3 volts, and it really wants it down to like 0.5%. It's really, so I have to do a little fooling around there. Why not use a Raspberry 4 Pi? I'm actually monitoring information. I'm talking to the receiver, and I'm also collecting data on it. One of the things we want to know about it is how much power does it draw, right? Power is the king or queen in the satellite. So over here, there's a current monitoring device. Goes out as I2C, back to the Raspberry Pi. I can talk to the Raspberry remotely. I do that. It's actually connected to my home network Wi-Fi. So I don't even have a keyboard or a monitor hooked up to this. I just talk to the Pi remotely. Got a USB hub because I got a whole bunch of USB peripherals here. We have a serial to USB converter. That's how we talk. I'm talking to the serial port here. I've got a CAN receiver because Burns says I have to make sure that it talks CAN in there. So we're doing the same sort of stuff. That's what we're doing, and everything is glued down. I forgot to say this at the beginning. I invite you, if you have a question, don't wait till the end to ask. I'm used to being interrupted. Remember, I deal with 20-year-olds all the time. Yes.
You say you have an RF environment, which is a folder. It simulates the GNSS.
Yes, yeah. So it comes in. There's the antenna port there. So it
tends to be 3 of the satellite.
Yeah, and it's programmable. Yeah. It's a remarkable system and very expensive, apparently. Apparently, as is often the case, She got a demo from the company and refuses to return it to them. Academics, this is the way we roll. But the problem is, she said the license expired, so she's trying to talk them into extending the license now. So that's why. So I've got the receiver, so it came in last week and it's hooked up, and it looks exactly this. It looks exactly the same. It just has a little H in the serial number. So yes, please do interrupt anytime to ask questions. So we started out this project a while back, and Burns said, would you do me a favor? Would you figure out how to get the information that comes out of the GNSS receiver and get it turned into orbital elements? So took that on, and this is a sort of a flow chart of how I've been approaching this problem here. A bunch of software. I'm a hardware guy. Yeah, why I'm doing this here, but it's a fun project.
I'll clean it up for you.
Thank you. I know you will. So the dark orange are the two devices, the start point and the end point. The OEM, it's an OEM 719. That's the model number. ADCS. It has a serial port, and so I talk to it, send it commands. It gives me messages. It can give me messages in two formats. It's very, very nice. Either as an ASCII response or a binary response. My goal here is to give as much information to Burns as possible to make his job easier. I feel like I'm in service here in this. So I'm looking to get every single way I can talk to this on the table so he can pick and choose. He complains a lot about how much work he has. ASCII response, binary response. So these green boxes here are small applications that I've written. All right, some C stuff, some Python, some JavaScript. I'll write it in anything.
Fortran.
Oh, sorry.
That's harsh.
I saw it earlier.
Yeah, good point.
I used to teach back in the day.
Yeah, I bet.
I'll bet, yeah. Got it. So we can issue a command to the OEM, it sends a response, and there are different ways that we can read the response. And all these here, parse the ASCII, parse the binary. Ultimately, what we get is a state vector. 6 elements plus the epoch, the time. All right, so we get those there. And then version of orbital, the state vector into orbital elements. Is this little piece on the bottom here, the TLE, the 2-line elements. That's a print statement. There's nothing smart in there. That's just a conversion of that. That's not, but we have a lot of talking to do, and do. I'm not sure exactly what the format is needed. I'm hoping, as Burns has alluded, that we could just send those double floats over there.
Just those numbers.
And that goes over, that's fine. But in order to test this, I've had to do a bunch of different things. You got to throw everything you can at it to see if it sticks to the wall or not. And so we have other programs here. This is a ground application. This yellow here, it's called State Vector. And it's some programs, a couple of programs I wrote. And it turns out I found a library, which is the SGP4 library, that was written and promoted by David Valadu, who just happens to be another couple of 100 miles down the road from me. And he turns out to be a nice guy. I talk to him all the time. Wrote the SGP4 orbit determination libraries. And this is what's been used for the several decades by NORAD. This code is so old, it's dusty. All right. But it works. And there's some I'm not going to go into such painful detail today. I'm going to try to keep it a little simple. There's some detailed stuff that is a surprise when you start playing around with this. So I've written programs, various kinds of programs, to take a TLE, that little bit of snippet data, and turn it into an ephemeris. I'm learning a lot of Greek words here. Ephemeris is a list of positions and velocities as a function of time. And so here we have 3 lines. This is basically sine waves, pretty much, in the 0th order. The orbit consists of 3 sine waves. You can make an ellipse out of it. And we take the TLE, turn it into an ellipse, and then bring it down here and try to figure out can they get the same ellipse? Can I get the same TLE back at the end? This case, I've written a program and thrown a little noise in there because I'm an experimentalist and I know I've never made a measurement in my life that didn't have some noise on it. So I want to know how bad it gets and how quickly it gets bad. I want to do those kinds of things. This is some of the stuff that we're throwing at it. These are the kinds of details that we get here. We get fits, amplitudes, phases. We can figure out what the period of that object is. And so I throw all kinds of things at it. This one here was from NOAA 19, right? You can get these off the web, right? So I had some other stuff too. I found a library that had the SGP4 in JavaScript. Go figure. I don't know, but I know JavaScript. I know more computer languages than I know human languages. So that's I can do that. So I wrote a couple of web applications. Can't really read this well enough here, so I apologize for that. Down at the bottom it says go to Celeste Track and go get your TLE. Right? So go get one, and you can enter it right in here, and then I'll give you the in this case an ephemeris. We'll come up with a table of positions as a function of time. A different one we've got for state vector generators. So here's a state vector, the green panel here. And these are, again, apologize, can't see this. I took, when I wrote this program was about a month and a half ago, and I grabbed the AMSAT 1 TLE and put it in there. And I just did it the other day and got it again and wanted to see how bad does it get, right? So I think that what's important, one of the take-home messages here is to stop thinking about TLEs. If you've got a GPS receiver in your satellite, it doesn't matter because you want to know where you are, just ask the receiver. The only reason you need to have a TLE is because you don't have a GPS receiver. If you were driving a car and blacked out all the windows, you can appreciate the difficulty it would be in general operation. If you had the appropriate kinds of instrumentation, you could keep from running into trees and bushes and cats. You need to have that information. That's what the receiver is going to give to you. Now, in order to understand this, I gotta tell you, this was what I don't know what your summer was like, but this was my summer. I was reading all these papers on this kind of stuff here. Orbit determination by Bizentif, orbit determination by Vetter, thesis by Carr, thesis Rousseau. Rousseau is one of the founders of CubeSpace. So I understand some of the heritage of the stuff that we've been doing. So this is just reading about all this kind of stuff, fun kind of stuff there. Now, I mentioned before that I want to measure the current draw by this receiver. All these damn devices, they keep drawing power, all right? And we don't have an infinite supply of it. So it turns out this receiver requires about 1.1 watts. And that's not trivial in a 3U spacecraft like that. So we'd like to figure out, do we need to leave it on all the time? What can we do to do that? Well, there's another complication, a little detail about that. It says you turn it on and you don't get the information instantaneously. What happens is the receiver turns on and it goes and listens out for a couple of different, at least L-band microwave signals. It gets 4 of them. It gets at least 4 of them, and it measures a variety of properties of those signals and can generate the result. It has its own internal processor to generate that state vector.
Can I add something?
Yes, please.
You need to download the ephemeris. That's what takes so long, right?
Nope, we don't need an ephemeris.
The GPS receiver is going to need the ephemeris for the GNSS birds, right?
Nope.
You have to download that.
No. It wakes up and it wakes up. It listens for those. It listens for the signals and encode. All right. So in a pseudo-random sequence is encoded in there, and each of those signals is a time marker, and it looks at the time marker that it was transmitted, received, and it actually. What it can do with each of these satellites that the receiver talks to, and it determines, it says, how far am I from you? That's what it can do.
Yeah, but I think his point is to know how far, you need to know what the time was in percent, but also.
It's
where
encoded in the same message.
Yes, yes, but that encoding, you have to wait up to 15 minutes. It's on.
Okay, the slow modulation because of that, yes, but we're not doing it from the ground. It's encoded in that message, and it does take some time to get that there.
It's not finding the birds usually, especially if you're out in the clear. It's needing all that data.
Sure, and it comes in relatively slowly. There are some model, or at least some internal features of them that the difference between a cold start and a warm start. In the cold start, you have none in there at all. And I've seen some in the literature of some folks who have flown these things, and they have some advice on how to set some parameters. The other thing, in order to get the speed, you need the Doppler. There's a Doppler data too that's got to come in that. Yes.
I'm sorry, I'm not familiar with pseudo-random. Is there a simple explanation for that term?
Pseudo-random is random noise or a signal that has equal probability of occurring at all values, but it repeats.
Okay.
That's the pseudo part. Random is there's a statistical variation to it.
Right.
The pseudo means it repeats, but it repeats long enough that it doesn't really matter.
Okay.
In the case, it's a situation.
Thank you.
Thanks for the point. That's an important point in there. It takes the spec from the manufacturers. It's a 60-second cold start to a fix, right? Guaranteed. They say guaranteed if you got enough signal to noise there. That means we're drawing 1.1 watt, and we want to figure out one of the things we want to do for good stewardship of the spacecraft. How often do I need to know the fix? It's a 6,000 second orbit. Does it change that much from 100 seconds to another 100? These are questions. I don't have the answers to these here. These are questions we're looking to work out in simulation and also studying of the literature. That's what we do. But if we say that I can just do 10 fixes in orbit, I can take that average power over an orbit down from 1.1 watts down to 100 milliwatts. So I'm getting more comfortable with that. And the question is going to be, how much do we need? Well, we got to fly this thing and see. I'm going to figure that all out for it. Now, I've got some others. I have a whole bunch of, I can go on like this for hours. I won't do that to you. I have a whole bunch of other details about some of the astrodynamics. And depending upon what the questions were like, I was ready to go through them or not. Since there aren't that many, we might get out of here faster. Yes.
One of the things that amazes me is that all these GPSs you've been looking at flying seem to be very power hungry. And on a 1-year CubeSat, we must be impossible to have enough power to do it.
Right.
Whereas I haven't, many people have got GPSs on their watches or their mobile phone. Because why aren't those GPSs screwing that?
My standard answer to that is FIIK. I really don't know. I've asked the same question. Why is it that we can handle these in there? I don't know why that is.
Because in my CBM, you only need the power for 3 minutes.
What do you think, Chris? What's the answer to that?
Okay, sorry.
You just said, is it some sort of meter or stabilization that makes it very accurate?
I mean, it's possible, right? There has to be some good stuff. I don't know. It could be that the stuff that we have for consumer grade is quite.
So
I'm sorry, what?
I've worked in GNSS for 20 years.
Come on up. Come on.
Assistance makes a lot of difference in self-boost, right? So assistance is really key. And
assistance?
Meaning that you send to the device information like the ephemerals.
So are you saying that his watch has an ephemeris?
Doesn't have to receive it for infants, right? Yeah. It's being told lots of stuff. It's being told time assistance, things like that. Really helps with power usage.
Yeah, it already knows the time.
We should talk after this, please.
Also, you have, if you're locked onto an LTE signal, you're gonna have a really good sense of time right there.
Right.
That just hugely affects the correlation calculations.
Okay. That works for me. All right, good. Like I say, I have there's a whole bunch of stuff about the astrodynamics, which I'm not going to spend a lot of time with. We talk about mean values. I think this is an interesting topic right on this slide here, and that is like many physics problems, it's a successive approximation problem. One of our systems engineer, Eric, he loves the statement that I brought in there. He says most to a physicist, you always reduce, and I'm not a physicist, I'm a chemist, but to physicists, you reduce the problem to a simple case. And so the example is assume a spherical cow in a vacuum. That's what you have to do. Just take it and take it. Just totally simple. Well, it's important to understand the strengths of the different kinds of things that are important, that are having an effect here. Near Earth accelerations means what is the size of the gravitational effect here? Most of the gravitational effect is the Earth's central force, and it's 6 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ of the Earth. And that's 4 orders of magnitude smaller. So you're pretty good. You got pretty good shape there, spherical. But if you want to get better, you can call it an oblate sphere. The moon is an order of magnitude smaller. So there are effects in terms of this simple model, this Keplerian ellipse. We can assume to a certain degree of approximation what's governing it. If we want to get better, we have to take a look at some of these smaller effects. Now, the moon is a tenth of as big as the gravitational force, but the moon is moving. So that becomes a periodic variation, but it's a repeating periodic variation. The sun's central force is further away, other gravitation, radiation. Earth tidal, that's mostly governed by the moon. Atmospheric drag is totally unpredictable. Not totally unpredictable, but it is not periodic and it has to be handled. So it's worth mentioning these. If you want to get fancier and fancier about predicting the position of a spacecraft sometime in the future, you care about these. If you just want to know where you are now and in a short time in the future, you don't care quite so much, or if you don't need to know quite so detailed. Depends upon what your mission operation is. Our mission is going to be attitude control. How much position information do we really need to do attitude control? We need to know if we're in eclipse or not. That's one thing. We can do that by looking out the window. Depends upon your mission objectives. We'll do that. Frames of reference, I'm going to keep it there. Let me close by thanking all the folks that made this possible here. The AMSAT board of directors ponying up the cash for those devices. I love the engineering team leadership. Burns, Jerry, Eric, those folks are doing all the volunteers. Some of them are here. Be nice to them. They're okay folks. Dave Villardo has been a gracious communicator, talking about astrodynamics, and thank you for your attention. I'm going to answer any questions, especially. Yeah.
So, do you imagine or envision having the ability to vary how often things are seeable? Because if you're
he can do that. He can say when he wants it.
Yeah. Okay.
Can do it. It's just software.
Yeah.
That's what we always
one or two lines.
I mean,
right? Yeah.
So we can envision different situations where we might want to know more frequently than others.
Yeah, because if it's just circling, just orbiting, it hasn't changed a whole lot, but now you fire something or point it or twist it.
But we're back to that hot start, cold start problem.
Yeah.
If you don't know, then it takes longer to wake it up.
Or you wake it up and then you move, right? And then you turn it off or something.
Yes.
I'm just going to mention that AO40 was one of the first, if not the first satellite to have a GPS system aboard for the specific purpose of testing whether or not GPS would work above the GPS constellation.
Absolutely. That was one. It wasn't a paper that was up on the screen, but I was reading that this summer and learned about that. That was a legitimate question.
Tested it further than it was expected.
Exactly.
Right.
Went out to 60,000 kilometers.
Right.
Right.
Yeah, I was just going to ask whether, the numbers that I showed that the ADCS wants are missing 2 compared to the TLE. There's 2 second derivative. Can you get those?
No. Well, yeah. I mean, yes. It's just software. It's just software. So the 2 terms, besides the 6 terms that I mentioned and the epoch, there's another term called B star, which is basically an aggregate measure of the atmospheric drag. That's in there. And that can be obtained only by taking repeated measurements and fitting the data coming up with to that information. There's also a couple of derivatives. Turns out the SGP4 model ignores them completely.
Really?
Yeah,
Oh.
yeah, and it barely look. It seems to barely look at B star.
Good.
Isn't there an SPG8?
There is. Okay, so this is one of the subtleties about that.
Yeah.
When the elements are created, they are created with a model which includes models of the shape of the Earth. W80. There's a whole bunch of different ones. You can't use a better one than it was created with and get a better result. You get a worse result.
Oh.
It's an asymmetric problem, and you have to use the same one together.
Makes sense.
I think the more that we do this with the GNSS, the better we're happier we're going to be.
Cool.
Thank you again.
Okay, guys, Jerry's gonna be up next, I think. But we need to figure out how we can get this mic powered. It went dead. Wilson or Carson,
No, I've seen it.
Appreciate it. Thank you. Thank you for the camera.
I'll probably have to Jets game. Yeah.
Thank you. Expertise in teaching the academy comes out.
Paul, can you go back and jack the game up on this so Jerry doesn't have to get right now? Is it coming out over there too?
A little bit. Not much.
Okay. How's it sound? Is there any amplification?
Yeah. Got to raise the mic up a little bit better.
Because it doesn't stay.
Duct tape.
Test. A little better? Rich? Okay. All right. And, to some of the folks on the stream have talked about the focus. I've tried the best I can. I'm sorry. It's as in focus as it gets.
Well, it's not every you also see this.
But, you know, like with,
Maybe I'll get some part.
I think it'll be great.
So,
they're close. 3:45. Or thereabout. AGMs normally go short, so.
yeah.
Yeah, do that.
Measurements in you plugged it in. Something with some checks on it, so I do. Then they also have some text.
Maybe have to make a motion.
You've got it.
Well, I know.
So it's days on 20 months. I don't know if it was. Yeah, that's all. It's great. And just looks for a door crossing. I mean, gotta be. We'll do that. All right, thanks.
Good afternoon, everyone. Is this microphone working okay for you? I'm close to the.
Very faint.
Can't hear you.
Okay,
That's good.
I've got quite a bit to talk about in engineering because there is a whole lot going on there. So I'm gonna run through some stuff about Golf T, a little bit about Fox Plus, and then let some people, Bill Reed, talk about PaxSat. He has something to say about it, but he was not scheduled to present. And also some more details to some of our engineers that are here with us regarding the finer points of the Golf T satellite. There it is. Sorry. All right, so before we do start that, I don't know how many of you have been here. I know it's only a few, but long enough to be at the BOD meeting, Board of Directors meeting. This is something that it's really, if you ever get a chance to do it, coming to Symposium, there's a lot to learn from what goes on in there. And sometimes they're pretty lively, I guess you can say. And so
We've heard.
we had one just recently, yeah. But look, I will be, how would you say, passionate about defending my engineers, the team. I ain't no Rocky though. But I do make a good bowling. So, what else are you gonna do with an eye like this? Somebody's gonna ask, right? So.
Yeah.
Getting down to programs and projects, here you see we have Golf, Fox Plus, and Ascent projects going on, and lots of activity in those. I'd like to start though with a message about what drives all the schedules for everything that we work on, and that is the humans and human resources, the engineering team. So of the engineers that are here right now with me, this is gonna go call up what's going on state by state. So rather than try to name every picture that comes up, if you just stand up one at your state, just so everybody can see that you're here, that would be cool. So we have a lot, geographically diverse, from Arizona, Colorado, pretty well represented. Not necessarily here, but these are the engineers that provided me with the pictures. And Massachusetts, and we've got Maryland, Michigan. The geographically diverse, as you can see, is everybody spread out working from home is what it amounts to. It has different effects on what we do. Minnesota and New Hampshire. When we had Fox One was small enough to fit in a small Pelican case. Then we've got New Jersey and then also New York. So we could take that satellite in whatever form it might have been, engineering model, flight model, and safely put it into this Pelican case and send it off between one another essentially for the work that was done. Tennessee and Oregon was there. We got Texas, and there's 4 of us, but 1 of us don't count because I don't do the actual engineering work. And then we finish up with Virginia with Mike out there. There you go. So now this isn't everybody on the engineering team. I requested photos. I may have missed some. Some people may have chosen not to send it, but 14 states were spread out over in this instance. And with Fox, like I said, with Fox One, we were able to ship it around fairly easily. Golf T starts to get a little bit more difficult with that because of its size, its mass, and well, think about shipping something like that. With the challenges that we face with our all-volunteer workforce, our
kind of the same challenges that everybody faces each day. When somebody signs up, we typically ask if they can, or would say that they will donate 4 to 5 hours a week to whatever they're working on, because we need to have some consistency with what's going on. Now, the design and construction and all that is very complex. And so we need people to be all in to the extent they can on whatever they're working on. But real life, of course, comes along. I've been suffering a lot of that lately, and it wins. It wins over your AMSAT volunteer free time, essentially. And so that has a big effect. Day jobs, some people still work, and working during the day and then working for AMSAT at night can be a bit much. Overall, though, if you can't do 4 to 5 hours a week, generally it averages out. So, you know, you're going to miss some things or such, but people are very good at keeping things going. There are some challenges even in that. Right now, it's a good situation that we have so many projects and opportunities, but the bad situation there is that we don't have enough people to do them all, or at least a rapid pace, so to speak. There are some people that are working on 2 or 3 different things, and we have not just the projects that we're working on, but we have launch and partner opportunities that come up, and at some randomly, where it'll be like, do we have something to fly on this rocket, or somebody wants to fly an LTM on their CubeSat, and a lot of times that though comes in when they figure out that they don't really have a radio and they have a launch getting real close when they call us. So most of the time that we're unable to help them with that because we don't have the hardware ready for it, or because it's just too short a time to try to integrate. We also have, sorry, dropout rate. Dropout rate is a factor of what goes on. The new member dropout rate, if people are going to do it, they tend to just disappear after a few weeks. And so it does leave us in limbo. I always ask everybody, the best thing you can tell me if you want to quit is that you want to quit, or you can't work for a while, because then we know where we are. Otherwise, we can go a few weeks or maybe longer waiting for you to come back and provide the input that we thought you were going to. And that hurts when you find out it's not getting done. And let's see, yeah, variability in attendance, number of people. So, you know, the number's always going up and down. And the ability to produce, like I said, is always going up and down. So that adds a little extra problem to trying to adapt to new changes or to introduction of new projects with you know, they're exciting and everybody's got the desire to get that going. And a lot of times it just can't be met that way because we don't have enough people. The golf program net, this is something that I learned really bad analytics when I went to school. So Fox 1 was AMSAT's first CubeSat, 1U, 1.3 kilograms. AMSAT Golf now is a 3U CubeSat. So roughly 3 times as tall, 3 times as wide because of the solar panels, 4 to 5 times as massive. We can go up to 5-6 kilograms. I don't know the golf tee will. And we basically got 3 times the amount of space, right? Because you have 3 1Us. But that points to the fact that you ought to be able to put 3 times the stuff in it, right? And that's where my really bad analytics gets me, but that's not true at all. I mean, theoretically it's true, but you also have the fact that it's 3 cubed or 27 times as complex. And that's actually way undershot, even times 10. I think sometimes it feels like it's all 270 times as complex. Because we have that much more room to put in it, and because we are who we are, we need to find out certain things, ADCS, and you know, the GPS and all of those devices, but we always want to pack more radios in it than you can shake a stick at. So I'm going to show you the 3D print. Kirsten was going to focus for me, but I'll just try it and see what happens. Ah, there you go. Thanks. Oh, you're kind of spooky. So, just this is largely for the people at home as well. So I'm gonna hold this up here and see if it looks in focus for them.
It's too dark. Here, give me a second. Let me.
Back to
Turn it sideways where the colors are. That's the back side.
well, I wanted to show the
All right.
wings first.
Oh,
but
yeah.
There you go.
I will turn it. I will turn it. Thank you. So this is looking at basically the back solar panel, if you will. This is the front with the wings deployed. And of course, there's nothing covering it for demonstration purposes. I'll go over all of the parts inside, but you can see even in my hands, it ain't that big. You know, you think 3U, boy, that's like a lot of satellite, but it's not. And Tom Karnauskas, our mechanical engineer, has been printing these as we go along, so that, and we work out the ins and outs of how to fit everything into the space crate. We had PDR for that about what, a week ago, 2 weeks ago, and moving on. Then I asked him to go ahead and add some real metal rails to this one as a look toward fit check. Fit check's very important to get this thing into the dispenser. It has to be within millimeters or less of tolerance. And so this is not probably the flight stuff, but actual aluminum rails. And there you go. The kind of a peek inside the entire bird there, which I'll go through in just a minute. That's in the spokes model. One good for him. Not lovely though. Hey, I can take it. I can take it. If I was lovely, I wouldn't walk into glass walls and get a black eye. Golf, the greater orbit, larger footprint. The idea with the Golf satellites, series of satellites to test flight testing and qualification of stuff that we need to be able to get into higher orbits, ultimately HEO. Golf, I don't see Golf itself going to HEO, but developing the systems and the skills to do it is the plan. We started out with the idea of increasing orbit heights, where actually Golf T CSLI was submitted, being technology exploration environment. Because all this stuff's going to be new, deployable panels, ACS, the radiation tolerant IHU, and the SDR microwave, these things are things that we want to have to carry on with Golf. So Golf T is the first flight to see if we can make that happen. The increasing orbit heights would have been that Golf 1 would go up to about 1,200 kilometers is what I asked for. And actually, we could have gone there, short of the fact that there is no approved way for us to deorbit from that altitude. And that was back when it was a 25-year deorbit rule. And now comes the 5 years, and that makes it even, way more difficult. Plus the addition of maneuvering and such. When we did some modeling for, okay, how high can we go with Golf 1? It all depends on the orbit. It depends on the orbit and the attitude of the satellite. Because if the satellite, say, wings out, is, flying right down the orbital path, it has very little drag. And so about 625 kilometers would be the max. And that was to stay within 25 years when we did that. If you come at it, with the panels full on, then it's going to drop that lifetime a whole lot. What we don't know then is what orbit we're going to get with the CSLI until we're, approached with that launch altitude. And we may wind up, in order to get best sun, pointing into that orbital path a lot of the time. We may wind up going sideways or end on. So that's what keeps us low. We have to be able to deorbit by natural decay, because we cannot otherwise maneuver or cause ourselves to deorbit with any approved devices. So the increasing orbit heights part, the Golf program is kind of stalled in that essence, because we can't reach those higher orbits until we have added and master even a little bit higher ones. Added and mastered the ADCS propulsion and other really neat items that you need in order to survive in today's world above 500 kilometers, basically. And so what we have is the opportunity to develop stuff in the LEO orbit that we can use on future satellites. And the ADCS, for example, radiation tolerance, the radiation tolerant IHU, we don't know what it's good for. Certainly probably not HEO, but the idea was 1200 kilometers would be a good place to test it. 10 and 5 gigahertz, and also 2.4 was added because of the QO100 and all the equipment and interest that's generated. That will fly on Golf T, but not necessarily be used. The 10 gigahertz down will be used. Now the thrust and propulsion is where we get to what we have to know to go higher. We have to be able to maneuver. You have to be very, very careful, because if you get out of one guy's way, you might be getting into another guy's way. It becomes very complex to do that. And if you can't point and maneuver accurately, then you're a great hazard. And Robert has said he doesn't want to crash into any satellites. More than just one person said that. So these things are things that we can still work on in LEO. We have a team working in Ascent on propulsion, and there are promising inputs and outputs coming from that we would be able to test in LEO with future golf missions, and hopefully intended to build up a trust and reliability that we can control our satellite at higher orbits, even with our own propulsion. The commercial stuff's going to be really expensive. The ADCS is expensive, and you start buying a bunch of them, and then commercial propulsion and stuff, which is what we would have to use right now to go higher. That gets to be, well, a decision for AMSAT about what threshold are we at for trying to make these ventures higher. But still, we have to be able to control this. We have to learn how to point and drive it, if you will. The Golf T then carries the deployable solar panels designed. It's a fixed panel design, as you saw, where they do deploy, but they're not steerable otherwise beyond that. The whole satellite has to steer it. It's got the cube-space attitude control system now, because the original attitude determination control system, Ragnarok, being provided as a that originated with the Heimdallr CubeQuest Challenge 6U satellite that we partnered with them. And so it gave us an opportunity for a low-cost entry into ADCS flight test for them, but they failed to deliver it, so we had to go looking for commercial, which is also why Golf T was on a launch, but had to be withdrawn from that because we could not make it. And the ADCS was required. I had to, eventually, we de-scoped the ADCS, and it didn't cost us any fine to be taken off that launch because it was ultimately Ragnarok's fault. So you can get, if you get NASA looking for a launch for you and you get manifest on a launch and you don't show up or otherwise pull out, you can be liable for the money that they've spent to get you to where you are. The radiation tolerant IHU I mentioned, that's something that came out of Ascent and is promising to be able to go to higher orbits with still COTS parts. There are a lot of SDR that you can use. I think some of them are very tolerant on their own. I'll get to that shortly. So LEO 550 kilometers, that's something that's accessible by CSLI, Alana launches, which is what we have. Both Golf T and Golf 1 were selected. It's got a Vanderbilt ISD experiment. They've been on all of our Fox flights, all but one. Good radio footprint, I mean, you know, it's 500 kilometers. And it is orbital debris regulators friendly because it will decay, especially at this point in the solar cycle, real fast, just a matter of years. The milestone real quick. We've got the PDR I mentioned, we just completed PDR. Or, sorry.
PDR.
That's what I said. I'm sorry, if I didn't say it, I did. I meant preliminary design review. And the last one, now we've got the engineering model stages I mentioned, we've got 5 months on that for our schedule, so that we have to build it, test it, and determine that that's what's good enough to fly before we have our critical design review in March. And at that point, if we all agree that it's good enough to fly, then we go into the build of the flight model, building, testing, and qualification. In the meantime, that's the point basically that NASA starts looking for a launch because they know we have or are going to have a flight satellite. It doesn't necessarily guarantee when it will be, but I think that it'll be fairly close that we'll be able to get one fairly quickly, just based on what has happened with Golf T and Golf 1 prior to our halt. So once we go through that, this tick here is just to talk about the ground station. We don't really do the hardware of the ground station. We're talking about the command and control software that the Drew and the ops use to control it. So that is written by us. And final date for, can't read it. The handover, yeah. December 1st, 25. Readiness for handover. That means it's been through environmental, it's all the qualifying tests, and we're ready to say, all right, we'll put this on a rocket. And then that's the point. It could match up when we get a launch. It may be a few weeks. I'm guessing that we could probably, if we make this date, be good for first quarter of 2026. A little note at the bottom with the blue block there, that's our schedule margin we have built in. And it's been shrinking, but what it's there for is because to try to capture any slips we have without pushing back our promised date to do it. Then Golf 1 follows Golf T in more or less 12 months. I mean, that's just kind of a starting target date. We want to find out, we're learning a lot building Golf T and designing it, but also we want to see it in flight because Golf 1 depends on solar panels, ADCS, RTIHU, although that was not 100% because we still have the LIHU for backup, and the SDR to function nominally so that we can make a mission out of, like most of our missions have been, which is a combination amateur radio and education. We'll be carrying a STEM experiment, camera experiment for a San Diego high school. And we'll be able to open up full 5 and dime 2.4 and maybe 1.2, although might keep that for a command channel or something. And then it does have the standard VU repeater built into the LIHU if we fly that, but otherwise it will be handled by the SDR. So it's still VHF, UHF, but getting microwave opportunities there for everybody. Like I said, higher than LEO right now, or even high LEO is out there on the horizon. We can look for companies who are developing commercial deorbit devices and such for CubeSats now. They weren't when we first got that launch for Golf 1. That's why, you know, there was no suitable device. Hopefully we'll be able to buy one. Maybe we can still go higher. We'll see. And we'll move on to the rest of the slides. But again, it's just all about developing for the HEO ride. So I took the Golf T model here, which is very fine. Took some pictures inside and take a quick look at what's in there. On the top, we have the CubeSpace ADCS, and it's got 3 parts essentially. A magnetometer, so a little bar on top, which you can see. Might see it sticking up there, but you can see it on the model. The magnetometer will extend, and that's an aid to the ADCS. And you've got the Cube ADCS, the actual attitude control unit with reaction wheels into it. And it is coupled to the Cube computer, which is the flight computer for the ADCS that we interface to with our IHU. We've got the central or common interface unit. I'm not sure what they call it now. It's kind of cool. Okay, flopping back and forth, but this is a board that is the solar panels, antennas. There's just all sorts of stuff that's routed and to control the burn wires to various places outside the satellite. And this is the junction for that to bring signals in or send signals out and to otherwise distribute all this stuff between various connectors and buses. It also has another function which you'll see shortly. Now we get down to the maximum power point tracking unit, which is the device or the system that maximizes the power that can be drawn from the solar panels based on voltage, temperature, and current. And Kip, you in here? There you are. You want to talk a little bit about it? Come on. Sure. I'd like to hear you, have you talk to that, and then also anything you can to the battery tender system. Yeah, and the battery cells. Have at it. Maybe I'll flip some screens while you talk.
Okay,
Kip,
so
I think he's I don't want to call off him, but he's working on the MPGT and our electric power system.
I'm AE5IB and currently living in near Dallas, Texas, in a little town called Lucas. So yeah, so the oh, okay. The blue little board there is my maximum power point tracking. I've got we've got 4 of them going. 2 for the or 1 for this double set of panels, 1 for this set of panels. There'll be 1 on the front, and then we'll do the 1 on the back. So there'll be 4 MPPTs. That was kind of decided for me ahead of time based on what they did with Ragnarok. I basically took over this after they bailed. So MPPT, if you know anything about solar cells, they have a certain curve. And if you're at one end of the curve where you've got no current, you've got a lot of voltage. On the other end of the curve, but so no voltage plus a lot of volts is no watts. If you go the other end of the curve, you have current, but no voltage. So again, no voltage times times current still is no watts. So somewhere in between there is a peak, and that's what we call the maximum power point, where you get the maximum wattage out of those solar panels. If you go either way from that point, it's less than optimal. And so that's the maximum power point. And that point can change by a bunch of different things, like your attitude towards the sun. If you're facing right at the sun, it's different than if you're tilted a little bit, because the radiation energy isn't as direct on your panels, and so it's lower. On the ground, a cloud can come by. You can get obstructions. So all those things make the maximum power point change. So that's why they call it maximum power point tracking, is you keep track of where that is as life happens. And so that's what I have. The circuits on this board is trying to maximize the power from each one of those sets of solar panels.
Yeah, that's
Pardon?
talk about it.
Yep. Okay. The next, that next one. No, that next one is actually, it's called a PDU. And that's the power distribution unit. And that's the one that takes, out of my MPPs, I go with 19 volts. It's just a number I picked because of components, and it had to be above what the batteries needed. So, from the 19 volts, then I generate the 12 volts, the 5 volts, the 3.3 volts, and on my unit, I am also using the same processor that they're using in the IHU, and that one also needs 1.2 volts. So I get all those from that 19 volts. That's an improvement over the other ones over previously, where they used to just convert everything to 5 volts. And if they needed 3 volts, then they'd have another converter that would convert the 5 volts down to 3, and then another converter that would convert the 3 down to like 1.2. So each time you do that conversion, you lose power, I mean, from the inefficiency. So it's easier to go from 19 to 1.2 than to go from 19 to 5 to 3 to 1.2. So that's that's what that is. The next board is the is that red one, and that's got the battery and the battery management system. There's not a lot of chips involved in the battery management system, and I believe I can get all that circuitry on the spaces in between the batteries.
Yeah, the red board there.
The red board, yeah, that one there. So we have 2 independent battery systems. Each one has 4 18650 batteries, and but they're independent of each other. So we can be charging one or discharging the other. Well, that's never going to happen, but anytime our voltage is above 16 volts, we can be charging those batteries. If we ever can't provide enough voltage, it'll drop and the batteries will supply the power, but the MPPT will also adjust down to that lower voltage and try to add as much power as we can. Even though it's not enough to completely do it, we can offset the need for the batteries. So that's what we do with that's one of the advantages of the MPPT system that I've designed. Yeah, well, we've actually got 4 in series but 2 separate systems. A lot of times 4S4P means that we have 2 in parallel and 4 in series, and it's all one unit. That's not what we have.
Yeah, that's my mistake.
Yeah, that's
okay.
Thanks. So
That's what I got. There's for that part. Any questions for Kip there?
Oh,
certainly. Come back over here by the microphone.
I read, and I'm not a battery expert at all, but I read past a study that said you get significantly longer life out of these lithium batteries if you run them from low and nominal voltage. That's something you look at.
Okay.
If the answer is yes, that's enough. I don't
Yeah, well, a normal
I was going to say,
battery.
73 seems to put it right. So make sure you learn from them.
When you think of normal lithium batteries, if you charge it to full and discharge it to full, or discharge it all the way down and then charge it up again, you get about 5,000 or 500 charges. We're not doing that. Based on our calculations, we're only using about 20 or 30% of the battery. So we're not going to charge it all the way. We're going to charge it to maybe 75% and discharge it to maybe 40%. And that way we're not stressing the battery, and we're hoping to get 29,000 charges out of this thing. And that's how we're going to do that. Yes.
With your maximum power point tracking algorithm, how many times do you do that per second?
Okay. I've got 2 parts to this thing. I've got a normal power supply, which is running at about 400 kilohertz. But on On top of that, then my processor is going to be checking all that on the order of either, I haven't figured out whether it's going to be 25 or 50 kilohertz. So I'm checking it really often because once you get past that power point, your power supply wants to try to increase current. And all of a sudden, you're diverging. You're hitting that far rail, and we don't want to catch that. So I have to keep on top of it really closely. Okay? All right.
We are a little short on time. So if you have more questions about this, we're gonna be around tonight, and I've got a little special invitation at the end if you will. I'd like to get through the rest of these systems, and then also Bill Reed, like I said, with the AMSAT has a few things to say. So to finish off the rest of the stack here, we're looking the blue area, not the little bump, is the solid state power amplifier, and I'll have a different view of that shortly. And then we have, okay. In the center, that bump, which is obviously there in the 3D much better, that's the sunsets that the ADCS uses to figure out which way the sun is, essentially. Part of its orientation. Down below that, we have the really fancy GPS that Joseph has been playing with, so to speak. There's if you have a commercial off-the-shelf GPS on the Earth, it's got limits of what it can do or how fast or how high it can go, so that somebody doesn't build a missile or something like that. So we have to special order this, and then I sign my life away that they're going to be good, and that'll give us the opportunity to get those calculations that he explained earlier, or have access to the GPS portion of it. That's. I think my mouse pad is going to punch it. Below that, then, now we're looking at the end of this. In this photo, we're looking at the end of the transverse stack. So I'll explain that a little bit more in just a moment. And down at the bottom area, which I colored kind of blue because I didn't want it to be looking like the rug. That is open right now. It will have the 10 gigahertz antenna there, but it doesn't want to take up a portion of it. We have to have an Earth sensor, Earth horizon sensor, as part of the ADCS as well. So that will be peeking out through the bottom. And we're working on what angle or how it's going to do that, but that's what that space is for. In addition, that imager, the camera from San Diego Golf 1, keeps that area unassigned, if you will, so that we have the opportunity to add imaging devices and other such things. And then that 10 gigahertz patch array, which I don't have a picture of, it's a four patch. That's just flat on the bottom panel. And it's got about a 90-degree beam width. I mean, maybe not all a 90, but Kent has said that, you don't really have to be pointing right at Earth, obviously. And so you could probably even work it for sun pointing, and you're off the right end of that, so to speak. Well, this could cause a problem because I got to reboot that. Whack the thing, you could hear it in the microphone. So looking at one of the sides here, this gives a little peek inside the SSPA, that hole there. Just the point being that the SSPA system is inside of a box for shielding. And the SDR. So the SDR is what causes the problem that causes the transverse stack. So the SDR along that side, the Edison 310, we could not modify it to be able to fit on a smaller circuit board that will go on our nominal stack. So primarily Bob Davis originally came up with the idea of how we could get our stack in there and get the new stuff, if you will, with the batteries. We had not flown these lithium ion before. We did nightcats at Fox. Get the batteries, battery management system, all that stuff in there in the ADCS, and have it in two different stacks. So that's it there. Then right above it, or connected to it, is the transverse stack. It's got the blue parts, I think, are the Vanderbilt experiment, radiation experiment. And then, not necessarily in this order, it's got the LIHU, the LTM, which consists of two cards as the command receiver, and the and the transponder and the GPS mount interface, right? That goes to help hang the GPS, which is pretty much hanging off the side there. Sorry, let me go back. I want to point to that real quick, 'cause see, I pointed out the GPS before. The way the GPS is mounted, it's actually kind of stuck to the side of the transverse stack. So there's the board in there that provides that mating for it. Excuse me. Looking at the back, which is what you originally looked at, because I'm stupid, but that's the one of the fixed solar panels. There's 7 cells there, as there are on all of the sides and wings. And then there's a little orange area peeking out there. This is our access port to be able to charge the batteries, to be able to talk through an umbilical to the IHU, load software, test things, and as well as having an LED and a buzzer that when the satellite goes active, having been in a safe state, that the quiescent state that you put it on the deployer, if during testing and such, vibration test or what have you, the satellite goes active, then that will start beeping and flashing. And so that gives the people on Earth up through integration the opportunity to realize it's something working quite right in the process there, and halt the process by putting the RBF pin back in. So of course, once it gets to space, nobody can hear it scream. So, but we don't have hard evidence on that because nobody was able to get to a Fox to find out. And the deployable fixed solar panels, of course, one of the showcase things. Since they don't stand straight out, I showed it in the process of deploying. Yes, those will fold open. Dwayne Mobert's been working on that, and it's tricky. It's very tricky to get the hinges and the wiring and everything, so they're tied down against the sides of the satellite, and then they unfold, not quite like that, or like that, out from the satellite when they're released without snapping into place and crashing into things. One note that you may not be aware of, and that is that we can't litter anything in space. So if we burn a wire, a fishing line, it's got to stay attached at both ends, and whatever ends are left free. So we also don't want solar panel bits snapping off. Probably end my career. So go into the Fox Plus satellite real quick. Hopefully a lot of you were here, or most of you, for Mike Moore's little quick presentation yesterday. He was actually only given about 2 days notice. So if it seemed a little quick, blame him. But they found a spot for him. So I called him and said, "Hey, Mike, you know you're on." He came through. From my point of view, if you will, looking at the timeline and such for the Fox Plus, it's about 44% completed according to Gantt charts, 37 tasks in it, but notice only 8 people working on it. And some of those are maybe in working on golf as well. That's like I said, we're thin. We have people working on 2 or even 3 things sometimes. So the overall timeline is the upcoming PSR a week from, it'll be November 6th. And this is a preliminary status review because everything is new there, and including the team. Mike wants to take a look at, is everything coming together? Is everybody in place? And do we have, the team that we need and such to proceed? And that simply precedes the PDR preliminary design review, which is currently set for a month later. Then that gives 22 weeks for the engineering model for the critical design review. Now, a lot of Fox Plus is purchased. Only the LTM, essentially, the IHU, improved command receiver, and the transponder are of our own making, if you will. So the rest of it comes from Ice and Space, the antenna, the solar panels, the frame, the EPS. And yeah, I think that's kind of ambitious, but Mike's new, so you gotta learn. Then we get down to the final projected finish date, which he mentioned actually when he did his presentation. This one, I asked him for Gantt. He gave it to me a week ago or two maybe, but October 19th, I think. And he had September 1st, 25. And I think you said, more like December yesterday or something.
Yes, everything should.
So we'll have a little race between Fox and Golf. So I mentioned all the innards to that and the radios. It's a VU LTM transponder. It was originally made, expected to be an FM transceiver to replace Fox. The idea was because Fox had a great FM radio, but most of the parts were defunct on some of the companies' work, that it would require a whole redesign, rebuild, still using the same idea. We did not have anybody free that could work that RF situation. And so it was, in order to look at the rapid deployment piece of the Fox Plus program, in other words, to keep a series of LEO satellites up with ham radios, we decided to go with the LTM, which is already operating and used, in order to get to launch sooner and have a ham radio in space. And then Fox Plus B, I expect a series of them, haven't asked the board yet, but that would have an FM radio and also PACSAT. PACSAT's a project that's been working out of Ascent and recently moved out of Ascent, if you will, to be ready to fly on this flight, the Fox Plus B. And with that, quick mention the fact the LTMs that we manufacture, PACSAT, the SDRB, which I really don't have time to talk about. Ray Roberge, who did the EDIS work for Golf T, has gone to Ascent in the quest to make that 4-inch by 4-inch board, if you will, SDR, to be able to fly Golf 1 and such. We'll take all of those, but we can manufacture a minimum 5 for starts to be able to fulfill these random launch opportunities that come up to fly wherever as a hosted payload while we work on the rest of the satellites as well. Some of those higher to get to the MEO or even the HEO orbits. Now LTM, PACSAT, who knows how long it'll last, but if people are working on it for a week or 2 or 3 or something, they're going to be happy. And so we want to have a bunch of those to be able to just deploy while we do the satellite work. And that stock can be replenished or even updated, but to keep engineering from having to maintain all that, it would just be outsourced essentially. Yeah, somebody's got to help put it on the rocket, but we get out of the integration systems business specifically and the requests people make. So Bill, if you would please, we got about 8 minutes. 8. Well, do you see that big hook come out here? I'll duck and you can go, right? You can just push the space bar? Yeah.
Thank you, Jerry. I'm Bill Reed, NX5R, and I want to tell you a little bit about PACSAT. We started back in July of 2022, and this was the vision that I had for PACSAT. It's very basic, with a TMS 570 CPU and 4 AX5043 receivers receiving on VHF, and 1 AX5043 transmitter transmitting a downlink on UHF. So pretty simple concept. And we wanted to move forward from this. We thought this would be the easiest thing for hams to get on the air and use and play with. That was very important to us. And so we wanted to start with this concept. We actually went through several steps. We had an issue where we wanted to use a TMS 570, but back in 2022, TMS 570s were not available. Well, we found a TI launch pad that had a TMS 570 on it, and we used that to start our development. We moved from that to a full prototype. We called it Blinky because we added an LED on there that blinks when you get a good software load, and sometimes it's hard to tell when you get good software load. So that's why we called it Blinky. And we did a lot of work on software, courtesy of Chris Thompson. And the ground station uses Chris's ground station software, and all that is working at this point. but it is a proof of concept. It was an AMSAT program. Just show you a couple things. This is the launch pad we started with. They were $60 out of TI, and we added a daughter board on top of that to make it a full AMSAT prototype, but it only had one downlink transmitter and one receiver, so that was good enough for our testing. And it had the FRAM on it. You can see the FRAM up here in the upper right-hand corner. And this is the transmitter and the receiver. And then we just connect it to the launch pad. We also have a console port on there connected to USB that we can use for testing. We have 100 different software commands for testing, so we have quite a bit of capability there. We ended up with a full prototype then. And this was our prototype. We finished this late 2023, and we've been testing it and working with it. We have 4 AX5043 receivers, a AX5043 transmitter, power amp, and we have a splitter circuit to take one antenna to feed 4 receivers and a preamp. Here's the FRAM memory, and of course the TMS 570 processor, and a PC 104 bus. We're currently working with this and testing different problems we found with it, but it's looking pretty good. It does work, but we're fine-tuning amplifiers and preamps and power supply circuits. So as I pointed out earlier, this was our concept, and we moved from that to I2C running to the memory, watchdog timers, sensors, a real-time clock, and of course filters and amplifiers. So we filled out the design, if you will. But, and I want to thank the previous description of FreeRTOS and how it might be used on a satellite. We kind of copied that design from Gulf. What I found is if you take a bottle of Jack Daniels and you take a couple of shots, and then you spend some time staring at this document. But this is an amazing document done by Chris and Burns, and it describes the tasks and the timers and the cues that are used for the PACSAT software operating system. Here's the file system. We can have potentially some interface to experiments. So we could take their telemetry and add it to our file system and put it on the downlink. So we could probably spend a couple of days looking at this document, but this is amazing. And it's pretty much fully implemented at this point. You have any comments, Chris?
No, that's good.
Lots of hours spent though, right? Are there any questions? That's basically PACSAT, hardware and software. We're at a stage now where we're no longer a prototype. We've been asked to fly on Fox Plus V, so we're taking our hardware and we're converting it to flight hardware, which is fine-tuning and cleaning up, and we're actually changing some components that we don't like. And I have one other thing that I'm wondering if anybody is interested in helping us with, and that is if I go back to that original launch pad and those add-on circuit boards, I'd like to replace that single board with 3 boards. A digital board that would have the MRAM on it and some of the digital functions, CAN bus, for example, an RX board and a TX board. And the reason for that is that the basic design we have is a very good one. But it uses AX 5043s, which are no longer generally available. So that could be a potential problem down the road. And we want to experiment with SDR and advanced protocols and techniques. So that's kind of a two-step program now, the moving towards the flight model and going back to the ascent program and developing some more advanced capabilities. That's all I got. Any questions?
Thank you, Bill.
Good. What was the purpose of having 4 receivers?
Yeah, we really don't know how many receivers we need. It's that was based on the original designs started back in the 80s by Harold Price. So we think that's a good number, but we really don't know because we don't have a lot of flight experience with it. And back then there weren't a lot of users either. Before, Chris, you want to comment on that?
Well, I was going to say probably the same thing, and that is you can multiplex the downlink. You can't multiplex among multiple users.
Okay.
So going up.
That's one good thing. We can also configure the receivers, AMSAT command receiver, gives a video, well as something that's just used to download files. So we can get them different uses as well.
And different frequencies.
They're all on different frequencies.
And we can turn them on and off. So we can fly with less.
So it's mainly just to deal with congestion.
Thanks. Good question. I'm not going to butt in here because we're going to get thrown out.
Okay.
Thank you, Bill, though. And I think also based on what you just said, I would say that, there he is. Robert's out there. Get these 2 guys a bottle of Jack, man. So I was gonna have an open discussion here. We got short on time because of running late and such like that. But also to include the idea that after the banquet and every night so far, we've been hanging out in the patio area out there or veranda or whatever you call it outside there. And if y'all really want to come outside and sit around the table and just talk about stuff, it's a great, that's one of the best opportunities of Symposium. Whether we talk about engineering stuff or we talk about UFOs or airplanes, you know, it could be, it's just fun. It's eyeball QSO, right? So I'm going to have to close with that because we need to move on to the general meeting. And I really hate rushing. It gets me all nervous. You can probably tell. Thank you very much.
I'll tell you what, we have a break right now, our scheduled break, so let's take 15 minutes. I've got 3:52, so I'll tell you what, how about 5 minutes after 4? Come back, all right? And we'll start the general meeting. Thank you very much.
I had to stand up. I couldn't stay another minute longer. My back was killing me. Oh, no. Multiple back surgery thing. I didn't bring my own pillow, you know. Forget it.
So, we were our company.
Your call. I grinned real big when I saw your call. I go, I know what it means. Sorry. Yeah. Oh yeah. Yeah.
But we started showing MRI machines because and so
I'm gonna be that much short.
Protocols, and after a while, you can't, follow one.
People.
So, okay, Tuesday. Oh my God. Right, I inherited something. I inherited.
Okay.
The other thing,
Oh my God. So you MRI.
I go in there, and I
Snore.
3 hours later, they say, come on out. I feel, get a lot of radiation.
Yeah, so you got juiced up.
Yeah, that guy was an X-ray.
Yeah.
So we.
That's cool. That's cool.
Now,
Yeah, I've been sat here staying.
Oh, the point of that thing is a pleasure. Basically, the art team. Yeah, so it's there. Yeah. I come out of there one day, they sound like that's why I had all that back trouble. It's all gone. I said it's gone. I got the picture.
Thank you very much.
Expensive diagnosis.
Yeah.
Oh, one of these.
So in Fargo, about an hour.
We have 49.
Actually, no, I met a South Dakota application, put in this principal, it was rejected. And you know why? We've had empty student involved from homeschool to kindergarten to
We've probably got to get you on
South Dakota Space Grant, and I had 3 different facilities and clubs.
I've been trying to figure out.
It's not like it's doing yours. Don't have that anymore. They said, there's some action classes from all summer explorers. I'm like, WTF, I went to the space grant.
Did I tell you about my slideshow? I had the part that I was briefing to do, so I thought, well, let me go in and read it out. So that when I do personal stuff. How many times did I would go in there and trying to adjust them? It kept flashing. This is working off Microsoft 365 and plus I wanted to take some slides from last year's. I ended up having to rebuild the entire.
No. Oh, that's horrible. That's horrible.
I guess I'm going to have to switch to a PC laptop. Instead of trying,
Oh, yeah.
instead of trying to do it all over, to the end of Microsoft 365, I'm just over. I've had that laptop since 2015, so it's almost 10 years old. So I'm joking.
Yeah, my little ThinkPad gotta be over 10 years old. Recommended decaf.
Here, she's saying, you do straight laces and she's got the green can. I was like,
It's kind of like a mullet. Business in the front, party in the back.
well, except for here it goes all in.
Well, now she puts it over her shoulder.
Yeah.
Which is about how she gave her talk. I didn't see it during the talk.
No. My wife likes
Oh, funny.
And so there's this girl. Gets the case anyway. She is 114, 4'4", and prior to military, she was a body. So she's short and very hard looking. But she keep doing she doing these two challenges around.
Yeah.
And you get done 30 minutes.
Yeah.
She's, put your head back and do it.
Oh, yeah, yeah.
Don't forget that I got the field day.
Yes.
Certificates.
I looked for you earlier and didn't see you in the crowd, but you are here now. Okay. I'm gonna do that in between when I talk about. I've got a gap. And I'm talking about now. So you put them in those two. Where is the, that's live right now. It's at the one in the back.
The audio advisor.
Okay.
Carson had come back and started.
I wasn't sure what this laptop was.
That was for if people didn't have laptops to do presentations. Are you gonna be at the podium or?
Yeah, I shifted it over there because my cord wouldn't fit in here.
So it'll just be the screen on.
Yeah,
On the screen.
that's why I moved away from the screen.
So maybe
Barbecue. I thought you said, barbecue chicken and pork ribs and potato salad and so whole buffet.
The,
Thought it was 7. It should look 7. I think no, you're right. Yeah. And they're gonna serve at like 7:30. Oh, okay. Yeah, if you want to put them around the corner in there, yeah.
That's why you sit down the lounge.
Get a cardboard box, maybe.
Except, Ešte základ jsem číl se dá. Žijím čajný.
Really seems a little boring. But take the bolts down and leave it there. Yeah.
They asked you soldering iron. So this is
Oh, it's gonna be late.
No, you're always
You happy?
Oh, yeah. So, I had a little issue with my presentation, but I got that fixed up. All right, if you can start moving to your seats, please.
It's all
That wasn't an engineer or. Yeah. I suppose it's a question of how well does it work compared to someone. Yeah, it's still interesting. I still not really study either. For what power?
Everything is okay. Job. So I can actually have the display.
Still be interesting to see.
Let's see.
All right, before we get started, I've got a little public service announcements. I'm gonna ask Linda to come up and she'll share that with you. Thank you.
I don't really need this because I can be astoundingly loud. But I just wanted to let everyone know, if you've got anyone interested in taking a test and they can't find an in-person testing session, my husband and I host VE sessions, and we use Zoom, which means that we can test anyone all over the world. Anyone interested can hit me up. I've got my contact information. I don't have a card, but I put it on my phone, so you can just, copy what you want to. And we test most Mondays through Thursdays at 7:30 p.m. Eastern Time. And you can find me on the league, but it's gotten a little tricky because when I put remote sessions up there, they disappear. And they have a separate site for remote sessions, but you won't find me unless you go to the length of doing a search for my call sign. So it's easier just to give the information out to you and anyone who would be interested in that. So thank you very much for your attention.
Thanks. Thank you.
And thank you.
Thanks. And we're back. All right. So at this time, I would like to end the symposium. This is what our 42, 43? 42. So our 42nd symposium. That does not fit in there at all.
Nope.
There we go. Let's go like this. So I can unplug it. All right, so our 42nd symposium. First and foremost, I want to thank all the presenters. It's still a phrase from our UK personnel. I was gobsmacked by the depth and level, and entertainment in the presentations this year. So thank you so much, especially those that traveled. We had Romania, Dr. Tutu, is that correct? From Romania with his card set, fascinating. I had the opportunity to spend a little time back there and look at that. Michael, sharing the AMSAT HB, they're doing some great stuff over there and just really rapidly rising to the occasion. And of course, AMSAT UK, thank you very much for your participation. Bruce, oh, they're back there in the corner there. It's almost, we have a phrase down the south, the Baptist road. It's usually the back chairs, and I see that they're adapting well. And to all the other presenters, thank you very much for your time. It's important that we have this opportunity to come together and share ideas. We tried that virtually during COVID and stuff, and it's not quite as efficient as in-person events. So for those that attended, thank you very much. Those attending via virtual, sorry you couldn't be here. Hope you can make it next year. So with that, I will call the first or the annual general meeting for AMSAT to order, and we'll get to the stuff. Of course, we're in Tampa, Florida. So I've got two parts I'm going to cover. Number one is the state of AMSAT, and then as an intermission break in between, we'll have Bruce come up and talk about the awards for the events this year. And then I will talk a little bit about the future. So thank you for attendance. Okay, so let's first go over, so make sure everybody understands our board of directors. We've got Mark Hammond, NAMH, Bruce Page, KK5DO, Paul Stetzer, NAHM, Barry Baines, WV4ASW, Jerry Buxton, N0JY, Drew Glassbrenner, also our chairperson for this year's symposium. So let me thank you very much for that. Most of the companies myself, I know exactly what he's going through, and I've seen him slip back over that couch every once in a while trying to catch his breath, and it deserves the least though. So thank you, Drew. Zach Messenger, who attended remotely this year due to a previous commitment. And then Douglas Tabor where Douglas is over here inside. Douglas is a new addition. He's our first alternate. So welcome aboard. Glad to have you. Look forward to working in the future. And of course, Frank Karnauskas, who he brought a note from his doctor that he couldn't come. But he did attend remotely to the board meeting and was very active. So thank you, Frank. I assume that he's watching virtually. If not, we'll make sure he knows. So that's the governance, our board of directors. Now our leadership team. You're going to notice that some of these names appear again. So of course myself as president, our executive vice president, Paul Stetzer, vice president of engineering, Jerry Buxton, who just filled us in on the golf and Box Plus and Ship programs. Oh, that's an old slide. I'll be honest with you. So at lunchtime, I went upstairs to my room to check my presentation. Noticed I needed to make a few tweaks, and the whole thing crashed. So I had to rebuild it and took part of last year's, and that part straight on there. Jonathan, though, is on the ASCENT team right now, a volunteer for the ASCENT team. Vice President of Operations, Drew Glassbrenner. Of course, he's supported by Mark Hammond. Both of them working together to keep our satellites functioning the best they can in space. Dr. Alan Johnson, VP of Educational Relations, and all the great work him and his team are doing on the CubeSat simulator. VP User Services position is vacant. I was the last person to hold that. I think about 2019. If you're interested, I'd love the chance to talk to you. VP of Development is Frank Karnauskas. That is a word, if you don't know, it's kind of a marketing fundraising person. So that's what they do to develop funding sources. Our secretary, and look, there's that new name again, Douglas Tabor in 6UA, as well as our treasurer, Steve Belter, who also provided a note from his doctor why he could not be here. Now, working behind the scenes, most of the time, Joe Kanowski has been our editor since I've been involved with AMSAT. He's doing a great job making sure that I get my Apogee View letter in every other month, usually at the last or maybe just a couple days past the deadline. AMSAT News Services, led by Mark Johns. That's a team of 4 people, and they tirelessly work throughout the week to produce a news bulletin each month. And if you haven't noticed, before it was the old 80 character column width to fit the BBS format. That has since evolved. So we've modernized another feature at AMSAT. It is now HTML, which means we can include pictures and everything. So great job on that. And getting started guide, notice that it says vacant. So again, there's another opportunity for you to step up to the plate. Even our last getting started guide was published in 2020. So it's now 4 years old, a little bit long in the tooth, but it still sells like hotcakes. We switched away from the printed version. We only do digital right now until we get an updated version. So we were looking for a new editor. I did have a volunteer last year step up. Unfortunately, he became a silent key. So we wish him Godspeed as he moves forward, and we'll carry on. Our director of AMSAT ambassadors, Bo Lowry, W4 FCL, he's out of Kentucky. Contest award, Bruce Page, there's that name again. Our webmaster position is vacant. That again has been vacant since the beginning of the time. A lot of stuff is handled by Paul Stetzer. I think Frank Kronowskis puts a couple things in there. Bruce every once in a while tweaks something. When they let me out of jail, I sometimes update something, but I try not to get in there too much because I get yelled at. And then our IT team, of course. Online store manager, Bruce Page. Information technology, Matthew Alberti. They've got a team, mainly it's him and Joe Fitzgerald. And they've decided to switch off every few years as the information technology manager. And then our orbital elements manager used to be Ray LaHode. No, just Ray Hode. Okay. So he has stepped down. He's been doing it forever. He stepped down 2 or 3 years, almost 4 years ago.
No, he's done it for 40 years.
Oh, 40 years. Anyway, so he decided to step down. He and Joe Fitzgerald stepped up and is doing that. And I understand he's got some students that are helping him do that calculation and everything. So he is making sure that that service continues. Okay, so let's talk about where we are at as an organization. So our membership, before we used to have a whole database, DB3 or something like that. It was really ancient. It had it was like pre-Windows 3.1. And it was always a challenge to know what membership levels we had. And now that we've moved online, which we did that in May of 2020, thankfully we had started that before the pandemic kicked off, and we were able to get that flowing. But I know second to second where we're at. Unfortunately, that means I know second to second where we're at. And that number fluctuates, one person renews, one person's time expires. Before everybody used to renew, there were annual memberships at the end of each month, because that's when Martha, she'd collect all those for the month and she'd put them in a basket on the last day of the month. She'd process them so everybody had the same date. Well, now it's real time. So when you do it almost to the minute, and then 12 months later, you'll get, or 11 months later, you'll get a reminder, and then your membership expires 12 months after that, or 1 month after that. So as I looked at this before I came down here, we had 3,993 current members. With about 1,900 are annual renewals. Another 1,945 are lifetime members. Our students, last year was 26, has increased to 41, so that's a good sign. And it fluctuates on what we're doing, what we're able to accomplish. So specifically, and, I believe like when we were launching all the boxes, those numbers were up a little bit higher. They're up to about 5,000. And then when we did AO40, the lead up to AO40, those numbers were really huge. And of course, in between those times, it dips down a little bit. Since we moved over to the new membership platform, it's been hovering around 4,000. So a nice steady membership level, and we're happy to see that. But we want to see it grow a little bit more. Okay, where we're at now, there's a big number for you. $1.9 million in net assets, what we have right now.
And that's liquid.
That is cash and available for sale investments account. I can call the Merrill Lynch account, say, cash it out. And probably the next day I could get it. So, what's helped us get to that is number one, our cost reduction measures that we've made over the past 3 or 4 years. We used to have a physical office. Martha was on payroll. And there was a couple other things that we had, like rentage of postal meters and stuff like that. So we trim the fat as much as we can, and at times I believe too much.
Yeah.
But this year we were, despite the economy, and it was a tough year for everybody. We ended up with $317,000 of money coming in, $306,000 going out. So our operating part was 10,000 to the plus. So it helped a little bit, but not as much. What really took a big bump was our investments. So the fair market value of our investments increased $202,000 last year in 2023, and it's went up even a little bit more this year. I hope that trend continues. Okay, so organizational services. I talked about us cutting costs, and that's kind of reflected in this next slide here. So we continue to have staffing shortages. This is an all-volunteer organization, and we rely on our volunteers. Our engineers, our informational people, our education people, even our office and administrative and leadership team, they're all volunteers. So we rely on them. And as you saw during the first few slides, a lot of people have multiple hats that they're wearing. I can tell you we're stretched really thin. This is a member organization, so we rely on the members to staff our organization what we want to do. Yes, ma'am.
So as I understand it, Martha was not paid staff.
No, Martha was.
She was. So when you lost her, why wasn't she replaced?
There was no office. That was part of the downside.
Number one, we did not have an office. So we stupidly believed that we could absorb everything that she did.
I think it's stretched.
Yeah.
Thank you.
And it has. But we have people who have stepped up to the plate and have covered all of her stuff. But we've learned our lesson a little bit. We're going to search for options to increase that.
You could hire someone to work remotely, couldn't you?
Yes, we could. The key factor is we don't want to get into employees. We want to find someone who's contract, because employees adds a whole level of complexity to the organization, and we're a small staff organization, so we want to keep everything as smoothly running as we can. So we're providing almost the minimal services, and I hate to admit it, it's sometimes not stuff that's not standard. Not only to our members, but to the amateur satellite community. I can't get on there, get somebody on there to share all the stories that we have going on. The engineering team, they're so overwhelmed that they don't have time to write articles and press releases and stuff. So we need to work on that as an organization. How I see that is member management, our website, and our online store order fulfillment. So right now, the website, we have a info@amsat.org email address. And then all our orders, although we have no physical inventory that we sell, when we get an order, we will have to forward it to somebody else to fulfill that order. And member management, right now that's all being handled by one person. And so to make sure that if that person gets sick or God forbid something else, maybe he gets mad at me, walks away, that we're covered and we continue to be able to serve our membership. So we'll be focused on those. And the important part to remember is that people will support us as long as they perceive that they're receiving value.
Right.
And we want to make sure that we provide that value to our membership. Okay, so our satellite program, Jerry and his fine volunteers come over and talk about that. So we're continuing our golf team, Golf Plus, and the Studio Ascent program. We've had some good, great work come out of that. So it's not as progressing as fast as we would like it to be. However, there have been extenuating circumstances. We had COVID. We had to learn, even though we were displaced and remote, working remotely already, we had to deal with new supply chain issues, and even loss of vendors. So we had to learn new stuff. We're coming out over the hump right now, and I think it should progress slowly. We're looking a little bit more quickly. I expect we're hoping for the end of 2025, but please be patient if it becomes early part of 2026. Education program, we had Alan Johnson talk about his CubeSat simulator program, and then throughout some other presentations, I also heard the CubeSat simulator being brought up as a role model, and that it is. It's a great opportunity for this organization. We can reach out to people, help fulfill our mission of educating or improving space education. So that is a great thing, and we will continue, not just rest on our laurels and just continue with what we got. We're going to keep pushing forward. Our ambassador program, which it started out as, where's Barry at?
Field operations.
Okay, field operations, and then it went to, what was it called?
AMSAT ambassador.
No, area coordinators.
So field operations consisted of area coordinators.
Oh, okay. And then the ambassador program, and I think, let's see, what was that? I was given the AMSAT ambassador program. It says, oh, by the way, you're the VPA user services. Here you go, take over. And so I tried to get it off, and then I became president, and it was just too much for me to do. So it took a little hibernation, and now Bo Lowry has stepped up, and they're starting to tweak that. I believe the update we got on the board, there's about 40 active ambassadors working right now, and that number will continue to grow. In addition, we have the youth initiative, which is still in this development program. And I think the mission may have been tweaked a little bit, but hopefully we'll be hearing something. Frank Kanowskis is, and his team are running that, and we'll hear more about that in the coming future. Okay, at this point, I'm going to stop and get Bruce to come up here and present some awards. And this is for field day.
Yes.
All right, here's the microphone.
There. All right, thank you, Robert. All right, every year we have field day and I get to score all those results. Not bad. We're not like the ARRL, we get, like 5,000 entries. We, this year, well, last year we had 19 stations reporting. This year we had 21. So not bad. There were 3 stations from Japan. Last year we had 2. That's growing. And I'll bet you if I move over here, those guys over there can see me. Yeah, perfect. Okay, that way they don't have to look at, the screen with no animation. We have 15 satellites. Now, not 15 physical satellites, but I count a satellite as to the modes. So if a satellite has UMV and then it switches to maybe LMV or UNS and whatever, those would be 1 or 2 different modes, meaning 1 or 2 different satellites, because you could operate it either way. IO 117 did an incredible amount of work. 269 QSOs were put through that during field day that were reported. That's not even counting all the ones that people were doing just to have fun on their normal operations. Okay, so for our certificates this year, for those operating from home on emergency power, Randy, WI7P, had 134 points. And for those operating from home with commercial power, we had David, W2GDJ. I think he had it last year as well. For the operating club stations, in third place, the Huntsville Amateur Radio Club, K4 Big Fat Turkey. They participate almost every year and have for a long time. They were in second place last year. They had 119 points. Then in second place, we have the Holland Amateur Radio Club, KADAA, with 163 points. And first place, which is the same club that had it last year, is the Lafayette DX Association, W9LDX, with 381 points. And you know where almost all those points came from. Green Cube.
Green Cube.
Yes, sir. So a quick thank you to those in Japan, Nobutataka JK2XXK, Masa JS1LQI, and Tasahiro JH1NHK. Now, was anyone here from any of those clubs that I mentioned that can take their certificate? Otherwise, the U.S. Postal Service will be happy to deliver it directly to them. That's it.
Thank you, Bruce, and congratulations to all those that participated. The number one Green Cube isn't right now, so all those teams will need to strategize how they're going to make it happen next year without Green Cube, unless it comes back. Cross your fingers. In addition, the Huntsville team, which was in first place, they were second the previous year. Tim Cunningham, who was one of our AMSAT ambassadors, normally leads that effort. He was out of country, I believe, over field day. And so he had talked to some guys from Athens State University in North Alabama. They had graciously decided to bring their little trailer. They have a little emergency comm trailer that has satellite operations. They brought that and they operated from there. I'm glad to see they came in first place. And also that they have as Athens State University, they have a fledgling CubeSat program, and have already reached out to for some possible linear transponder module systems. So we wish them well in the future. And speaking of the future, let's talk about charting our path forward, which includes both satellites and education. So, you know, in my free time, which isn't very much, every once in a while I browse through some old statements to see, hey, what was AMSAT facing back at the time? I ran across at the 2009 AMSAT. Apparently, AMSAT had a next-gen satellite development team that they had put together, and Alexander Hardichuk entering the results of that study. One of the things that caught my eye is that, you know, if you have a slide that said AMSAT needs to increase the number of orbit spacecraft, leverage current designs, creatively approach launch opportunities, maintain experimental edge, and provide a stable technical program. And that just smacked me upside the head because every one of those statements is still true today. Those are the things that we would focus on. So, as I see it, this is my opinion. May not be shared by all, but I believe that our focus as we move forward is to continue our experimentation efforts. So we still need to find new ways to communicate, find new ways to make the satellites more efficient and more long-lasting. And it is also an important development tool for our engineers. We need people to think outside of the box. And so whatever we do, we need to keep that effort going and fully support. Second, I would like us to consider satellites as a service. So there's a lot of, you know, I started out going on a little expedition down to St. Croix, and somebody asked me to bring some satellite equipment, and there was a little HT and a handheld antenna. That was my start. The FM satellites, with the, some people like to call easy sats, they're a gateway to the atmosphere satellite service. We need to make sure that we fully support that as we move forward. By a continuous stream of FM satellites. Low Earth orbit is fine. They don't mind running out in the backyard, putting an antenna in the sky. It's in context of the unit, 10-minute window. So we need to make sure we do that. It's also important at community events, whether they be amateur related or non-amateur related, to get out there and provide demonstrations of satellite communications. It will greatly, number one, does it not only raise awareness of what we're doing, it also will help recruit the next generation of AMSAT volunteers and members. And then the last thing is to take advantage of any rideshare opportunities. And I guess, we've been doing rideshare since the very beginning, where we catch a ride on somebody else's rocket. There have been, of recent years, multiple opportunities, although they were short time, to hitch a ride on something. And because we didn't have something that would meet their, that would be able to get meet their needs in less than 6 months, we missed that opportunity. So I think we need to focus on positioning ourselves as we to take advantage of those situations, whether it be 6 months or even further. But if we have something that's flexibly designed to meet those needs and sit on the shelf, we can do that. Any opportunity to get more amateur radio in space is a win for all. Okay, a couple things to think about that we may want to do is number one, one of the things that I was concerned about is it seems that each of our satellite programs, from the very beginning till the ones we're working on now, they all have kind of their own peculiar connection system and stuff. That we may look to standardize our connectors across all the boards, so that when somebody comes to a sentence, say, from the sentence says, I had this great idea, we can say, okay, here's the connectors, an ICD, design around that, and then you're ready to go. Part of that design, as we advance and move forward, before we've always survived just on a microcontroller. But when we start getting into more ambitious satellite projects, we're going to have to consider that we need high-speed processing, not only for navigation, but star tracking and possibly SDR, as well as, of course, all the other related support systems. Now, this gets back to that promise that we made to our members into the satellite community, is to provide a continuous stream of accessible amateur radio satellites, and that's as a service. So we always think, hey, when we build a satellite, we're always looking for that next new innovation and stuff. We need to think about, hey, we need to consider it also as a service to the AMSAT satellite community. I'm impressed by the work done by AMSAT UK. They have what they call a KISS-SAT or a simple SAT, very basic stuff. The more complicated you get, the more opportunities there are to fail. So we need something that's simple and robust with multiple backups and safeguards. That was an important slide. Very touch keyboard. And one of the big issues right now is that we don't have an FM repeater. So it's important that we have a continuous stream of FM repeaters, but we don't have one. So in the short term, there are a couple off-the-shelf, commercial off-the-shelf items that are. They're very power hungry, not as flexible as we'd like to be. So we may look at either what do they call it? Technical espionage. We're going to steal the AMSAT UK designs, or we're going to come up with our own. Something simple that we can just quickly. And then because right now we've got SO50 that's up there. We've got AO91 that works, it doesn't work. And then what else is there? Yeah. Yeah, PO 101, which is on schedule, ISS, which is on schedule. At one time there was like 4 or 5 on there, which made it nice. I started out my amateur satellite career as a rover. So I traveled all throughout the Southeast, and it was nice to be able to hand out grids over FM satellites to everybody. Most of them are just using a homemade antenna and a house phone. So it creates a lot of excitement about amateur satellite service, so we need to look toward that. One thing we learned from the Fox 1 series is FM satellites are very popular in demand. It would just suck the batteries dry. And that's what led this, we believe, to some of their short life of the batteries. So putting it through U package makes a little bit more sense. We've got more solar panels to generate. But also kind of like the RTIHU dual processors. So what we need is a lot of redundancy and safeguards in there. Dual processors operate in parallel. Backup communication system. So if you got the room, why not put 2 radios in there? When one doesn't work, the other one jumps on. And then active battery backup. That's critical. It's usually a second thought, but that needs to be moved up to the front. AO73 is, look how long it's been up there. It has a specific schedule how it operates for amateur satellite use. It's when it's in eclipse and for students at schools during the daylight. So an active our schedule so that people know when it's going to be available and it's not, and also onboard safeguards to help prevent damage to the batteries. And then here's a little system diagram. So there's not much to it. And it's got 2 radios, 2 antenna systems. Simple. Okay, so here's what I like to call HARP. That's because I'm prior military, I like acronyms. So we hosted amateur radio payload. We need to have something ready to go that is we can slap on take advantage of a ride share opportunity. Here I just threw up a SDR that offered multiple bands, and that's one thing we have to be flexible. We never know what we're going to be on, what frequency restrictions we have, what power supply they may have. So we need, a power condition distribution. Really, condition is probably power is probably going to be fairly clean, but we don't know what voltage it's going to be. Could be 28 volts, could be 3.3 volts. And then more importantly, with any software-defined radio, you need the ability to externally interact with it in case the computer locks up. So we need a reset receiver and an external watchdog. Okay, let's talk about education goals. I've been praising Alan and stuff. And to me, we've got 2 missions, right? Number 1 is build, launch, and operate amateur satellites in space. And then number 2 is space education. So to me, the CubeSat program should be our primary focus as we move forward. There are other educational efforts, our ambassador program, youth initiative, still good ideas, and they can still make a difference. But as we continue to develop the CubeSat simulators, I think that's going to be our best bet to ensure we're meeting our mission requirements. And then lastly, for our education goal, is we need to do a lot better job of sharing the AMSAT story. we've done a lot in the past. We've made some great accomplishments, and now it's time to set our own limits. So, with that, I believe that's it. Oh, forgot this one real quick. Part of our original document talks about that we're going to share what we learn with the world. And, somewhere along the line, ITAR, EAR came about and kind of put a damper on that. But we've got a great program policy now that will allow us to re-engage the world and share what we've learned. So whether you call it make it publicly available, which is how ITAR or EAR define it, open source or open access, open projects, whatever it is, we need to, our primary effort should be to make that publicly available. The exception, and as long as I'm president, the exception has to be fully supported as to why we wouldn't be. Now, of course, there are certain things like we get a ADCS system from a commercial vendor, and we're not, it's proprietary, so we can't show what that is. We can just put a block, put their name on it, what their part number is, and we've shared what we used, and it's available to them. But everything else should be going out. What the area we need to focus on is there's all different ways to share information. We got some on our website, we've got some on GitHub. All of the satellite work is on Alan Johnson's GitHub site, and he has a wiki. So that's fine that they keep those there, but we need to find a collective place to mirror that information, so that we become kind of like a one-stop source for information related to amateur satellite efforts here in the United States in our organization. All right, subject to your questions, because I'm going to open the floor. What do you want to talk about? Yes, ma'am.
In terms of making the public more aware and attracting the young more, you have to go where they are, right? So I'm wondering if we're doing enough on social media that young people are part of. And I also wonder if we could get teachers involved in spreading the word, or even visiting schools and having presentations to attract students.
Okay, some great points. So first of all, we do have efforts. Our ambassadors are going to makers fairs. They're going to science events. There's one it's in Dallas. I forget the name of it, but he does that every year. What? Boom Day. So we are reaching there's always a tendency to withdraw back and do if you're comfortable with the past handfests and tailgates and stuff like that. And yeah, there's some kids there, but not as much.
Yeah.
So we do need to think outside the box, and we have quite a few volunteers that are doing that. Education in schools, that's a tough one. As many of them will attest, it's hard to get into school. And usually you can get into a school when there is already a ham present. But as soon as that ham leaves, then poof, the support for that program is gone. I've seen that a lot with school amateur radio clubs, high altitude the launches, all that sort of stuff, IRS contacts. They start out strong, and then it just kind of fades away, and then you've lost that opportunity before. Yes, sir.
What's that about Aerosmith?
Yes, that's what Aerosmith should for the outreach. But I think our best bet is, and the last year about social media. So we do have a social media account. Of course, it's a bunch of old guys monitoring it. So Paul, he's younger than I am, but he's still not one of the young hipsters. So maybe there's a possibility we could do that to be a little bit more young and hip in how we speak. YouTube, that's another challenge one. There's a lot of people who make videos and post them on YouTube, and I've never seen. I don't know how many times I've been researching a topic and you find something that's great, and it's got 12 views. And, oh my God, what a waste, you know, how come other people don't know about this? So that's a little bit hard to break, and if we could find somebody that's, what do they call themselves, content creators. Been a few of them, there's some great space science, content creators on there. And maybe if we can get them to get some arrows off, that would help. Yes.
Robert, I was just add, Eris is a key to educational outreach. I mean, what Eris has been doing the last 40 years is amazing.
Right.
And AMSAT's been part of that. And I see them as the leaders that have the influencers on their team and their ability to go in and do the grants and to get contacts. That's amazing. I think we're talking about a second area, which is getting individual involved with amateur radio in general, or being involved with satellites. That's where AMSAT might want to focus more in terms of what we want to do internally, but that's a very difficult nut to crack.
Yes.
Yeah.
So Eris needs to be credited for doing an amazing job, as we've seen the last 2 days.
Definitely. Is anybody over at the small satellite conference this weekend?
This weekend. That one I didn't know about. There's a small sat conference that we went to, and yeah, small sat.
Yeah, so there's actually two conferences. So Mike and Diana are there, but it's actually for small satellites. This is a perfect opportunity to have some go to KSC right now. To be given a little booth and I don't know if you are. I know we are. So, but we also there's a small satellite thing on Utah every year. You know,
We attended.
We attended that. Do we have an official booth there?
We did not have a booth there this past year or two. We have it in the past.
I think those are two good ones. Besides,
Yeah.
Yeah, so Frederick on my team is presenting on the CubeSats, yeah. I think he's presenting as well. This is presentation.
Right, yes, Rachel.
There could be some good collaborations between ARIS and AMSAT. For example, once a school has a contact, what's after that? You know, how do you keep that school involved in something new? I mean, I don't know, and please forgive me, I don't think we can be talking with an astronaut, but maybe they could talk to a satellite and that.
When they say they'll just, they haven't followed on what
They do, but the teachers I've been working with their ARIS contacts, they don't feel as invested. So just from looking at it is an individual thing, but what if we create more materials that we can actually provide them? Or we create, curriculum that we can give to ARIS? That
Eris is here.
Yes, Linda.
I chaired the Arts and Letters Committee at Embry-Riddle, and as part of that, we invited all kinds of presentations, including scientific presentations, and we did, by the way, have an astronaut, and we had one of the red tail pilots, and I'm thinking that there's got to be something comparable at other schools, and if you get in touch with the chair and make it known that you're interested in doing a presentation, that might be a way in. And if you get the students excited, show them something that will gobsmack them. And if you get enough students excited, they will look for a faculty member to sponsor their club. And faculty members, as busy as they are, will bite at that because it's service, which is part of what you have to do, as a professor, as you probably know. So that's just one idea.
And of course, obviously, I've gotten some feedback there. Whenever you have a young group and we're putting forth a new program, they always notice, and that's a bunch of old white guys.
Yeah.
They came up with this idea. So we do need to inject more the younger generation to participate in the decision-making process. Make sure that we're accounting for new trends and stuff. What worked for me, I've got children and grandchildren, but that doesn't mean I'm an expert on what me. So we do need to work on that. Now, remember also,
this organization is full of great ideas, but we're a small organization. And, you know, there's every day I get a recommendation. Hey, why doesn't AMSAT do this? And I think, that's great. We're ready to start. Because even though it's great and I love to do it, I don't have. So, I'd love to hear your ideas, but just remember that I'm going to ask you to come join us. That's how I got started here. I wanted the host. I wanted AMSAT to host a symposium in Huntsville. And guess what? You know, after 20 years in the military, you figure I'd be able to watch out for traps. And that didn't work.
Didn't they tell you that?
Yeah, never volunteered. Any other questions? Okay, so let's talk about tonight to close out this joyous event. We have social hours starting at 6 o'clock. And then the banquet officially starts at 7. I believe they're going to start serving 7:30-ish. But we'll see. As soon as the food's ready, we're going to start serving the folks. Although it's a buffet, so I guess I don't have to send any bucks. There is going to be door prizes. So I will be passing around some tickets. There'll be 2 tickets with the same number on it. So you keep one and you take the other one and you'll put that in the although I don't have a bowl yet. There'll be some sort of bowl or something for you to put in that. So you can put all these prizes on. All right, thank you very much for attending. Yes, Luke. Okay. Yeah, in the room that we were in, board room number 1, which is right next door on the other side of the restroom. And last questions, last call. All right, for those attending remotely, thank you for attending. And with that, I will adjourn this year's the 2024 annual